I warmly welcome you all to the University of Helsinki, and it's very nice that you have made it here and are participating in this conference. Our university is, if you don't know it, it's the oldest university in Finland, founded in 1640 by the Swedish Queen Christina, and has since then belonged to 3 different countries, but the university has been going on, and it's actually, after the church, we believe the second oldest institution which has been continuously running in Finland. We have a long history, as you can tell, of some of these buildings, but nowadays we are of course very much living in the current day. We want to be a top research university, and we are a top research university in the best 1% of the universities in the world in all university rankings, and we have way more than 100 European Research Council grants and many other research merits, and we are working hard to try to get even more research merits to and raise our level as a top university in research and education. My main responsibility is Vice Rector in education. We very much want to work hard to be at the forefront of education, and just in the last couple of years have spent a huge lot of efforts into taking into use modern AI methods, generative AI, into our education. And actually my last meeting was about that. We are doing a lot of there and are really at the forefront up to the point that we are developing our own methods which are better than the commercial methods available and in use. But regarding the topic of your conference, Physics and Reality, very happy to see that this is organized, and thanks to Paavo and all the other team who have been made this possible. This is a very interesting and timely topic, and also in this field we actually have a good deal of background. You may not know it, but one of the first theories of relativity was developed about more than 100 years ago by a Finnish scientist, Gunnar Nordström, who developed a relativity model. Well, it turned out his model wasn't quite as good as the one developed by another guy called Einstein, so we know Einstein better, but some elements of Nordström's idea live on in physics. And later on, the professor who brought quantum physics, quantum mechanics into Finland, K.V. Laurikainen, later on in his career, he switched on to thinking about the philosophical aspects of quantum mechanics, and founded a society working on this. And now, as you will hear during this conference, we are other prominent Finnish physicists who are working on these philosophical aspects, and of course many philosophers like Paavo, who is very well recognized all across our university as one of the leading quantum philosophers. In physics research, I also like to mention that we are very much in the core of the quantum information theory. We have professors in this field, lecturers in this field are just now opening a new professorship position in quantum information theory. We are one of the 2 core universities in the Finnish Quantum Institute, and also in a brand new flagship, which gives a very significant funding in Finland to research on quantum information theory, quantum computation, quantum technologies. I'm a little bit, if I wouldn't be Vice Rector, I would be doing more research on that topic, but my research group is actually also involved in possible materials physics solutions to quantum information theory. And we are also working quite actively, people working quite actively on black holes, black hole information paradox, and related fundamental topics of black holes and cosmology. So with this brief introduction, I warmly welcome you. I hope you have a good conference. It looks like you are lucky about the weather. It will be a bit cooler than it was last week, so you don't have to suffer too much in the heat and can focus all your talks really on the fundamentals of physics and reality. So all the best, and have a nice conference, and see you around on campus in the next few days. Thank you.
Thank you very much. So this is a little warm-up talk for much, I think, more difficult things to come during the 3 days. I won't, of course, discuss the entire set of philosophical options, but I say some things to get started. And just to, perhaps for some of those, if you have some philosophers here not so familiar with this quantum theory, there are just some quick ideas about the sorts of features that are typically the philosophical relevant one. So there's, of course, the uncertainty principle, which says that we cannot measure, for example, position and momentum accurately simultaneously, and that implies that we cannot predict the behavior of an individual quantum object. And if you look back at the history to the 1920s and so on, so many assume that this unpredictability, which might be epistemic, about our, if you like, our limitations or our experimental limitations, would imply objective indeterminacy of the individual process, which makes it like more ontological and is thought to be, if you like, more metaphysical and profound. Another feature is this wave-particle duality, where this idea is that a single quantum object, like an electron, would exhibit both wave and particle behavior in a single experimental setting. You know, like in the two-slit experiment, particles leave, the object leaves as a particle, it arrives as a particle, but somehow we see statistically how it's the mathematics of waves that we can use to calculate the pattern, and also even for the single particle we can calculate probabilities. But it's not clear what the wave function represents. Here's something from Tim Maudlin. And so, you know, some would say that the wave function represents some physical feature of individual quantum systems, often called the quantum state. Some say that the wave function only represents the statistical features of collections of physical systems, but nothing about single systems. And then yet others would say the wave function represents nothing intrinsic about any physical system at all. So it's more about the agent state of information, state of belief. I mean, this idea was there already early on, but it's kind of revived a neo-Bohrian view called cubism. Oh, I spell B with the small letter. I apologize, because when I asked Chris Fuchs to be on the program committee, he said on one condition, that you learn how to, you know, spell cubism, and I'm sorry about that. But now you remember that, yeah. Later on it will be. Anyway, but these these are incompatible accounts of what the wave function represents, but people usually agree about which mathematical wave function ought to be associated with the system in a particular experimental configuration. And maybe in that sense, also, it might be one reason why, you know, physicists feel, well, the mathematics, at least up to a point we can agree about, so let's focus on that. And of course, now this is a table of the interpretation, various interpretations of quantum mechanics. It's in the Wikipedia, so anybody can go and have a look. I won't go through, but it's just to show the variety of, and these are in a way physics options. I mean, these are interpretation of quantum mechanics, so they're not, their aim is not philosophical primarily, but as I will be talking about some of them, and we can see that they actually do have various philosophical implications. Famously, the Copenhagen interpretation, which kind of goes sometimes even toward anti-realism. There is the de Broglie-Bohm, where you might have like this pilot waves guiding particles, which is kind of quite strange if that would actually be taking place. There is the many worlds interpretation that David Wallace maybe will tell us a bit later today. And there's various other ones. Consciousness causes collapse. That's a very cool, goes back to Wigner, von Neumann, something David Chalmers and Kelvin McQueen have kind of revived and explored today. And finally, there's cubism on the bottom, which is this neo-Bohrian thing. Others as well, but I really won't. One feature which often comes with quantum mechanics is wholeness. And this is actually the way David Bohm tried to summarize his understanding of Niels Bohr. You see, there's one challenge to understand quantum mechanics, but there's also a challenge to understand Niels Bohr, who was a subtle thinker. So you could say that the form of the experimental conditions and the meaning of the results is an undivided whole, which is not further analyzable. So in an experiment in which we can accurately measure the momentum of a particle, it is meaningless to talk about its position and vice versa. And this, of course, I actually realized when I was reading this, this is like the verification theory of meaning in positivism, saying the meaning of a sentence is its method of verification. If there's no method of verification, it's meaningless, it's not wrong. Only to realize that somebody like maybe Fine and Beller had actually written an article about it, so anyway. But this is one. And then, of course, there's this famous thing, you could call it non-locality, which came in 1935 with Schrödinger and Einstein, Podolsky-Rosen, or EPR. And in a very simple way, we could say that if quantum objects A and B are entangled, by measuring the position of A, we can accurately predict position of B, and same for momentum. And this happens in a way that there is, there's no time for a light signal to go and tell anything to the other particle. But the way EPR this is just a very, very simple summary. EPR figured it, well, if this is the case, that I'm here with A and B is far away, I can decide, measure position and momentum, it's up to me. Surely B must have a well-defined position and well-defined momentum simultaneously, waiting to be revealed by whatever I decide to choose. I can't reveal them both, but I can choose which one. And this would be against, this kind of ontological view would be against typical Copenhagen views, according to which the state of a quantum object is indeterminate before measurement. And of course, the idea there with the EPR was that quantum mechanics is incomplete and that it's likely that there are these hidden variables. Okay, about hidden variables, people mentioned that. People might think about David Bohm, who Mario Bunge characterized as the David who faced the Goliath of quantum indeterminacy. And of course, he's well known for proposing in 1952 the first consistent realist hidden variable interpretation of quantum mechanics, which was anticipated actually by de Broglie's pilot wave theory in the 1920s, but Bohm discovered that independently and, for example, he did the measurement in a theory in a proper way there. And of course, this is supposed to be impossible, so that's how Bell wrote that in 1952 I saw the impossible done, because there were all these impossibility proofs. Actually, Bohm himself had argued against hidden variables before. And this is a nice summary of this, if you like, more recent developments of these Bohm's hidden variable, or they call it ontological interpretation, just showing that, these are possible trajectories for individual particles. So depending on where the particle enters, it will take one of those. And the thing on the right is the quantum potential, which is it's energy. It's a bit like a mountain, and the particles are coming toward you from those holes, and they don't like to go up there. They go where this potential is flat, and that's reflected on the picture on the left. But I want maybe Basil will tell us how he can look at this thing. Later today, Basil will talk to us, and he may show how in this algebraic version, this thing, the quantum potential may show up. Basil always likes to find the quantum potential in all various historical discussions, and so be prepared. Some of the other things may be difficult to understand. This will be this afternoon. But anyway, what I wanted to mention is that, you see, right before this 1952 hidden variables paper, Bohm actually had published 1 year before a 646-page textbook quantum theory, which he wrote. He says he wanted to try to understand quantum mechanics. He was teaching it maybe with Oppenheimer and some of the others. And you may be using like Oppenheimer's course when Oppenheimer went to Los Alamos. And so his aim was to make explicit what kind of notion of physical reality is implied by the usual Copenhagen interpretation of quantum theory. So it was very different emphasis, still our aim from, let's say, something like Niels Bohr was trying to do at the time. It's actually a bit more like what Wolfgang Pauli was doing, because Wolfgang Pauli liked the book. Bohr didn't even comment. But anyway. Now, if you read the book, there's a lot of kind of philosophical stuff there, and also Bohm's answer to this question of, well, what is reality? Involves some metaphysical notions. For example, he would say that the electron essentially involves incompletely defined potentialities. And there were some other pretty curious claims, observations. For example, at the very end of the book, he is telling us that quantum theory actually presupposes the classical level. So it doesn't give us the classical levels of special case. So let's have a quick look what happened there, because these are maybe a bit less known than. So anyway, so here is some metaphysics. Bohm is claiming that quantum theory leads us to a new concept of the inherent properties. I don't know if we would call them even intrinsic properties of an object to replace the classical concept. And I already mentioned these are these incompletely defined potentialities. And then the actualization of these potentialities depends on the system with which the object interacts, as well as on the object itself. So you get this kind of picture. And so if you, for example, as an example, you could look at an electron with a broad wave-like packet of definite momentum and therefore of a definite wavelength. And such an electron is capable of demonstrating its wave-like properties when it interacts with a suitable measuring apparatus, such as a metal crystal. The crystal is a bit like, the slits in your two-slit experiment, so it will give rise to this diffraction and interference. But then the same electron is capable of developing into something more like a particle when it interacts with a position measuring device. I don't know, photographic plate, or some of you know better examples. At which point these wave-like features become less important. But it goes on. Even when it's acting more like a particle, you could go back to being more wave-like. And so the idea there is that the electron, the object, is capable of undergoing this continual transformation from wave to particle, and vice versa. And again, it's the kind of apparatus with which the electron interacts which would determine which of these potential aspects prevails. And again, we can see here already that Bohm was thinking ontologically, because he would say this also applies in situations outside experiments, like interaction with the metal crystal at the bottom of sea. So there's no need for human observers or human consciousness in this way of thinking. Whereas like in typical textbook Copenhagen, they always talk about, if you like, the measuring apparatus, but Bohm is here already like trying to think more generally. And so these are some interesting features. He would also say that this idea about that, the properties of the electron are incompletely defined potentialities is mathematically reflected in the fact that the wave function doesn't completely determine its own interpretation. Because before the electron has interacted with the measuring apparatus, see, the wave function defines two important kinds of probability. The probability of a given position and the probability of a given momentum. But the wave function by itself doesn't tell us which of these mutually incompatible probability functions is the appropriate one. This question can be answered only when we specify whether the electron interacts with a position measuring or a momentum measuring device. And now we get the sense that, okay, a lot of people, of course, debate free will, and some people say, well, there is no free will, and superdeterminism. Maybe Tim Palmer will tell us about that on Thursday. But anyway, just naively, we say, well, experiments with free will, we can decide which device to use. Is that outside of physics, or do the laws of physics determine our decision? Which laws, quantum or classical, and so on and so forth? I mean, this is kind of, but it's just showing that there's a kind of role left for the experimenter here. And you see, because it's very common to assume, people say things like the wave function contains the most complete possible description of a quantum object like an electron. But Bohm would claim that this description is incapable of defining the general form in which the electron will manifest itself, whether it manifests as particle or wave. And so the Schrödinger equation, which governs the time evolution of the wave function, will not tell you how the electron will manifest. Of course, now there is the Any-World story as well, which might say something different here. But this was like way you would think in kind of Copenhagen ontology from 1951. That's the way you would say. Anyway, so this is it. So we should, just to summarize here, we should interpret momentum and position, and thus wave and particle aspects, as these incompletely defined potentialities, which then we actualize with measuring apparatus. But you see, so we could have, well, does this really work? Because consider again this statement that I just read. We could ask that, doesn't the measuring apparatus consist of objects whose properties are also in completely defined potentialities, if it's made of the quantum particles, right? And the question is, how can sets of incompletely defined potentialities actualize incompletely defined potentialities? How, where do we find the thing that can really actualize anything? Why isn't everything just potentiality? And here, this is in the very final part of the book, like page 6 to 7. Well, we've been told this. What is the role of the classical level in measurement? So typically, the way these people were thinking at the time, they would say that the physical interpretation of the wave function is always in terms of the probability that when a system interacts with the suitable measuring apparatus, it will develop a definite value of the variable that is being measured. But the last stages of a measuring apparatus are always classically describable. Like they're not in a superposition I mean, this is the assumption here, right? And Bohm would claim that it's only at the classical level that definite results for an experiment can be obtained. Okay? And so this means that without an appeal to classical level, quantum theory would have no meaning. And therefore, he would conclude that quantum theory presupposes the classical level and the correctness of classical concepts. It does not deduce classical concepts as limiting cases of quantum concepts, which you can see elsewhere in physics. Okay, and so if we want to interpret the wave function, we must at the outset postulate the classical level. And the correspondence principle is a consistency condition. It's a requirement that when you go to the so-called limit of high quantum numbers, simple classical theory will be obtained. But it doesn't really, it doesn't really deduce classical physics from quantum physics at some limit. So, and now we come into this picture that large-scale behavior of a system is not completely expressible in terms of concepts that are appropriate at the small-scale level. As we saw, the quantum concepts would be these incompletely defined potentialities. And as we go from small to large scale, new classical properties appear, which cannot be deduced from the quantum description in terms of the wave function alone, but which must be consistent. So whether this would, I don't know if one could today try to use emergence here, or how would one put it? And you could say these new properties manifest themselves in the appearance of definite objects and events which cannot exist at the quantum level. Again, I can see that many worlds would tell a different story here, but then there's a price to pay there as well, because then you have to assume the many worlds. And so this kind of connects it to Niels Bohr in the sense that this large scale and small scale are complementary, and so because it's only in terms of the classical events that we can realize quantum events, but it's kind of reciprocal interdependence, because it's only in terms of quantum theory of its component molecules that the large-scale behavior of a system can be fully understood. So there's something quite funny going on here. And this is something that Bohm is struggling to keep together, as some sort of ontological version of the Copenhagen here. Okay. So this is just this quick summary. And if we think of in terms of laws of nature, we could say that in this picture it's the Schrödinger revolution that governs the wave function, but this does not as such determine what is observable for us. So we could ask some of these questions again about whether there is some sort of new role for the observer in quantum mechanics, because it's the classical that actualizes the quantum, but we get to decide which classical situation prevails for this particle, or this quantum object, or these quantum potentialities. So there seems to be this role of the experimenter in an interesting way here. And of course, if we look at some of these philosophical options that are being discussed, then some other ones, I mean, I just briefly talked about this Bohm's Copenhagen, which is not necessarily that well known, but which actually I find quite interesting to consider as well. You can see here some of the other ones we will be hearing, at least I think from the Everett view later this morning. And of course, there are other ways of trying to get a reality out of it. And of course, then we have the cubism spelled correctly over there, right? Okay. And just very quickly about the many worlds. This is from David Walden's, actually, I would say, excellent book, Philosophy of Physics, A Very Short Introduction, where the idea would be that if we take quantum mechanics literally and realistically, the world we live in is one of an innumerable greater plurality, all existing in parallel with one another, each one constantly branching from the others. All right, thanks. And hence, the better known name for the Everett interpretation, the many worlds. And we could look finally quickly a little bit of an anti-realist option, cubism. It's a neo-Beerem. Of course, I think Chris Fuchs likes to call it participatory realism, maybe because nobody wants to be an out-of-the-closet anti-realist anymore. Everybody wants to be a realist, right? But still, maybe there is a just stronger justification for using realism here. And this is from Vox, where he was chosen as one of the future perfect 50. And Chris actually was supposed to come to the meeting, but he had too many things. So we discussed a little bit, and he actually sent me this thing that one of his friends had asked ChatGPT, how would you summarize cubism to Chris Fuchs himself? And Chris thought it was a pretty good answer, so I'd taken some stuff from there. So you can see the emphasis here on the the wave function will represent agent's personal belief or information, and there's a connection to Bayesian probability. And again, in qubits, the act of measurement is not just about uncovering pre-existing properties, but it's fundamentally about updating the observer's beliefs in light of new experiences. And so the quantum mechanics is really it's a tool for managing subjective probabilities. And finally, there is the idea about the quantum world being somehow deeply intertwined with agency, choice, and experience, namely us, right? And this would require a profound rethinking of the role of science. And also there is this idea of the active participation of the scientist in shaping the very phenomena. Okay, this is just very quickly to give you, and this, of course, various different people like different interpretations, and maybe Avril will tell us later why in his talk. Well, he will talk about modern relativity. Anyway, so you see, coming to close here, David Bohm actually visited Finland, Joensuu, in 1987, and in a panel, I think he said, people were talking about very fancy theories, and then he said, well, he feels we still do not understand non-relativist quantum theory. How are we going to understand all the more fancy? I don't know what is something about strings or whatnot. And of course, we could ask, well, how are we doing 37 years later? Do we understand things better? Probably yes, but still, I think maybe by Thursday we have a final panel. Maybe we can discuss some of these questions. I mentioned also here that in this conference we'll be exploring a different way of understanding relativistic phenomena cosmology, the dynamic universe model, based actually on a couple of Feynman's idea and then explicated by the Finnish physicist Tuomo Suntola, who's also generously funding our project, physics, appearance and reality in physics and beyond. But anyway, so this will be a topic. And very finally, I just recently heard, we asked, well, where is physics going? Somebody asked once Duke Ellington, where is jazz going? And he said, well, man, if I knew, I would be there already. But anyway, recently I noticed that the ERC has awarded a big grant to this project, Universe Plus, Positive Geometry in Particle Physics and Cosmology. What they're trying to do is to create a new mathematical language to describe physical phenomena on all scales. And so the thing is that the idea here is, which you may have seen in many other places, but things like space-time and quantum mechanics might turn out to be approximate notions that ultimately must arise from more basic concepts. And this is actually something that people like, of course, John Wheeler talked about pre-space, David Bohm and Basil Hiley in the 60s, they talk about the implicate order. Penrose was part of those discussions. And I told this to Basil, we had a Zoom a few weeks ago, and he was quite excited to see that something like this is also going on. The basic idea here is that because relativity and quantum mechanics, their axioms, if you like, are in contradiction. So you can't just force them together. You have to go to a deeper ground from which you derive them in special cases. This is in a way maybe also the idea in this dynamic universe model, that how you could do things. But anyway, so in this, I won't go into it, to just show that they have these novel geometry shapes called positive geometries, and the idea that these would be show us how the principles of space-time quantum mechanics can arise from more basic mathematical principles. They want to find the geometries relevant to the real world, including gravity and the expanding universe. So, and this is how it all looks like, right? It's in the middle is the positive geometry, constructed purely from the energies and moment of the external particles and makes no reference to the evolution in space-time, okay? Anyway, but just to show that while we are doing what we're doing, actually this project is starting like in June right now. They had a warm-up meeting also, and in the website there are these PowerPoint present, 100 pages of mathematics, so it's beyond me, but if anybody's interested, go and have a look. Anyway, there we go. Thank you very much. I think we can just...
Oh, thanks. Thanks, Paavo. It seems that we have time for one question.
What you just said about Universe Plus, so Daniel and the other people in the project are actually proposing this positive geometry program that, however, wants to go beyond. So they want to create new objects precisely to go beyond our spatio-temporal description of the dynamics. So it also means that we have to change radically if they prove to be successful. We have to radically change also our view of quantum mechanics, and even the problem of unifying relativity and quantum mechanics disappears because we will have a new theory. So
right.
It's really revolutionary what they are doing. Let's see if they succeed, of course.
Yeah, thank you.
Do you agree with that or not?
Yeah. Well, anyway, let's move on so we'll have time for discussion later on, but so that we just keep the schedule. So.
When Paavo asked me for a title, I gave this, and then I started thinking about the problem, and then I toned it down a bit, and I put reviewing. Okay, so There is two novelties here. One is that I'm talking about this work for the first time. Second is that I'm using these handwritten things. So this is okay. This is for me. I'm very happy to be here, and thank you, Pavel, for inviting me. I'm a theoretical physicist. I've been working most of my life in machine learning, and now the last 5 years moving back into the quantum world, doing quantum control, and that's related to what I'm going to be talking about. So the topic is reality and physics, and I will give you my thoughts on that, on quantum and classical. And then the outline of the talk is that I will talk a bit about quantum physics, about the unitary physics of closed physical system, the non-unitary stuff about open quantum systems, systems in interaction with an environment, and then about unravelings, which are stochastic simulations of measurement outcome. And so this will also be a message about, you know, is the world deterministic or is it non-deterministic? So my notion of reality is what is out there, and sorry, I move on to the next slide. Sorry about this. So I want to show this slide. So my notion of nature is what is out there, and then reality is, for me, is what we can perceive, so what we can measure. And as far as I understand it, this is the classical world. What we measure, what we observe, position, momentum, these are classical concepts. The physics is what we can describe in mathematical terms. So this is like quantum mechanics. And these are not necessarily observable things, because maybe the wave function is not an observable object. We can measure implications of the wave function, like a position measurement or any other observable, but we cannot measure the wave function itself. If we try to measure the wave function, it disappears, it will change into something else. So that's the physics. And so I look at it in the way of this triangle. So the physics can describe part of nature, I would say. People who propose theories of consciousness, mathematical theories of consciousness, I have a hard time understanding that, and I'm not quite convinced that that is possible. And so there is part of reality, so I grant that there is part of reality that may be not describable by physics, but that's okay, because there are other things that we can describe by physics, and we'll stick with that part of it. So there's that. And then also you could say that reality is part of physics, because reality is what we measure, and there may be an underlying nature out there which is bigger than what we can measure, and that is what we model with our physics, with our quantum mechanics. So in particular, we can ask about the reality of a wave function. I mean, if you have a single particle, you have, it has 3 coordinates, x, y, and z, and time, and it's a complex number everywhere in space. Okay, well, we can call this thing real, but if we have n particles, this will be a 3n dimensional complex vector living in space, and saying that that thing is real, for me, becomes a meaningless kind of a question, right? So it's a concept that we use in our modeling, but maybe it has nothing to do with reality. Okay, so if we take physics as a basis, then we start with the Hilbert space, which is a very big space of quantum states. And in these states, there are also classical states. These are here denoted by these x, for instance, a position eigenstate. So the classical states, which are the localized states, are a very small fraction of all the states. And those describe classical reality. And this is a particular set of states that do not satisfy superposition. So the rule is, for all quantum states, you can consider superpositions, linear combinations, but not for the classical states. If we have a Schrödinger cat, it can be dead and alive, but we cannot, it can be either dead or alive, but we cannot take the linear combination of these two, right? Okay. And then there is a problem which is very much emphasized by Bohm in his 59 book on causality, where he says that whatever we do in physics, if we model physics, we're always looking at a part of the reality, part of nature, right? By necessity. If we describe the motion of the Earth around the sun, we ignore remote galaxies, we ignore the mass distribution within the planet, we ignore quantum effects. So we have a limited view on the reality, and we think that that is sufficient to describe this entire reality. And that often works well. So we have a system, S, we have an environment, and so there is an interaction principle. So we're leaving things out, right? As in this example, this Newton mechanical example. So we either ignore the environment, like we do if we talk about the unitary evolution of the Schrödinger equation. We say it's an isolated system. We ignore E. Or we have a simple interaction model, which is adequate. For instance, thermodynamics, where we have the environment, which has some sort of a temperature effect on it, and that is how we deal with this. But the key point is that whatever we do in physics, we're never looking at all of physics at once. We look at a subsystem, even if we look at the whole universe. Because, yeah, so we have a whole system. Okay, so I want to talk about, so for instance, so there is an intrinsic uncertainty, and I want to illustrate that with Brownian motion. Suppose that I have a smoke particle that is kicked around by air molecules here on the left. The initial position is 0, and the particle moves around on this red trajectory. Is there a pointer? Does it work? Huh? No, it works. Oh no, this is. Which is the? No, which is the pointer? Sorry. Which is the one?
It's here. That's a pointer. Left, right.
Okay, sorry. Yeah. Okay, so here's the particle. It's moving around, and after some time, it is here in this position here, and we can describe this by this stochastic differential equation, where there is some deterministic motion, a sort of a trend, and there is a random motion. And the random motion is, on average, is 0, but it has a certain sense, a certain strength, which you can call C. If C is 0, it's just deterministic motion given by this, right? So the position at time t is given by mu times t, which is the deterministic part, plus the integral of all the noise contributions. And so we can look at the average position. It is mu times t, because this is on average 0. And we can look at the fluctuation, and it is given by the square root of c times t. Right? The uncertainty increases with the square root of time. We can define a momentum, a typical velocity, as saying, okay, we have this distance traveled, and we divide it by the time, and that is our velocity, basically this. And the uncertainty in the velocity is basically the uncertainty in x divided by t, so we get this. And if we now look at the product of the uncertainty in x times the uncertainty in t, we get that the product is c. Right? So we get an uncertainty relation. But this is, so we get this, but this can be controlled by us. We can say, okay, this C is because of the coupling with the environment. If we do our best, we can make C smaller and smaller and smaller, and we get better controlled experiments. And if we get C to 0, if we isolate the system. In quantum mechanics, we have also such a relation, which is given by Planck's constant. It has to be larger than that. But we cannot make it smaller. It's fundamental. There's something we cannot go beyond. Okay, so this is a double slit experiment. And it exemplifies also this uncertainty. We have an electron source. The electron is going through one slit, or going through another slit, or going through both slits, and then it hits a photographic plate. We all know this. And then you see a little dot there. And if you repeat as many times, you get this kind of interference pattern. Right? We know that. Okay, so what's happening here? So there is the Schrödinger equation, which is doing the wave propagation here in this part. Then there is the interaction. So the Schrödinger equation by itself doesn't say anything about whether we're going to get a dot on the screen. The dot on the screen comes about when we consider the system in interaction with an environment. In this case, it's a measurement apparatus. So the interaction with the environment leads to a probability. Okay? This is a closed quantum system. This is an open quantum system. But the open quantum system by itself just gives the probability. It doesn't give the outcome. It doesn't tell you whether the particle hits anywhere here or there. It just gives you this red interference pattern. It tells you there it's going to be, but it doesn't tell you where it's going to be. So then there is a third point, which is actually, what is the outcome? How do I get the outcome X with this probability? Right? So those are the 3 steps. And I'm going to go through these 3 steps in this talk. So the Schrödinger equation. So the Schrödinger equation is a unitary rotation in Hilbert space. So think of a space, a vector space with complex vectors. And what a Schrödinger equation does is that there's some operator, which is, you can think of a matrix, you can think of psi as a vector, and it just does a matrix rotation of this vector. It's a rotation because the norm of the vector stays a unit length. Okay? So this is a linear. That means that if we have, it's linear in the sense that if I take a linear combination, I get the linear combination of the solution, and it's deterministic in the following sense, that it's deterministic like a density evolution. If in the classical case, if you would have a Brownian motion, say, here's x space, here's time, you start with some particle here, it diffuses all over the place. That is not a deterministic motion. But if you describe the mean behavior as a distribution, then the initial distribution will be very peaked, and the later distribution will be very broad. And the evolution of the density is deterministic, right? And in the same way is the evolution of the Schrödinger equation deterministic. It describes the evolution of the tendencies, and the tendencies are probabilities, and they evolve deterministic. Okay, so deterministic dynamics. But this system is embedded in a very, very large universe, and it is almost impossible, it seems, to isolate it completely from that environment. So how do we deal with that? And the measurement is related to this coupling of the system with the environment. For this, we need the notion of a density matrix. So we have the Schrödinger equation here. Now we define a density matrix, which is just the outer product of 2 vectors. So you have a vector, row vector, and a column vector. No, sorry. You have a column vector and a row vector, and you multiply them, and you get a matrix. So you get n times 1. That's the vector, and you get 1 times n. You multiply them, you get something n times n. Right? That's what this thing is. This is a matrix. And this matrix, you can also write this dynamics in terms of this matrix, and you get this dynamics, where this is the commutator. And this row is called the pure state. So we haven't done nothing, we just introduced some notation. This is the density matrix. Okay, the density matrix, we can use something we call mixed state. So suppose that we have 2 particles that can both have 2 properties, namely black and white. So we have white 1, black 1, and we have white 2, black 2. So the total state vector can be in an entangled superposition if particle 1 is white, particle 2 is white. If particle 1 is black, particle 2 is black, right? So this is a superposition that we consider. This is a pure state, and this is the density matrix. So total system is in the pure state. Now we're going to put a line here, and we say we're going to only look at part of the system. That's the left part. And we look at this system, and we average part 2. Right? And this averaging is technically called a trace operation. what it does in this case is that part 1 will be an equal mixture of white and black, because this one can be white and it can be black. And by the averaging, you get this. This is a mixture. And the mixture, so this is a mixture of white and black. This is a superposition of white and black, and it's different. So just to emphasize that point, if a pure state is always one vector, so for instance, I can have two vectors here, and I can make a pure state as a linear combination of that, so that's a pure state. I can also take two vectors and make a mixture in the following way, right? That's a different thing. That's a mixed state, okay? Pure states and mixed states. So the idea that we now get for the physics is that we have a universe which is given by some very big wave function, which is the pure state, which is the entire universe, and it consists of a system and a bath. So this is the system, and here's the bath, and the total system is in a pure state, and our subsystem that we are interested in is the average over that, which is the mixed state. It's an average of a pure state, okay, where we trace out the environment. So a little bit on how this average occurs. So we have a state, a system, and we have an environment, and they have an interaction. And the interaction, they singles out that there is a certain states of the system, and there are certain operators on the system, and there are certain operators on the environment. So the details of this is not so very important. If you don't get the math, it's okay. It's just there's an interaction between system and environment. It's given by Hamiltonian. That's how, over time, initially the system and environment are uncoupled, and over time they start to couple through this interaction. And so the initial state of the entire system, system plus environment, is in some, the system is in some linear combination of these system states, n, and the environment is some initial state, and they're just a product state of this. And over time, you get a coupling, and so the environmental states, n, get coupled to each of these n states of the system. You get this kind of a coupling, and that's the result of this interaction over some finite time, okay? Now, under certain conditions, it turns out that this, and that's quite technical, that if you now take this pure state and take the trace over the environment, take this average, that the remaining that you have in the system can be written as this mixed state. So it's a mixed, it's like the previous mixed state where we had here this mixed state, a sum of two terms. Here we now have a sum of n terms with different coefficients. So it's an average. This is an average of terms, because these coefficients, their sum add up to 1, so we can interpret them as probabilities. So we have here an average state, a state which is an average, and this is an average of individual outcomes, which are these terms, each of these terms, with probability that. So we can say, okay, we have this description as an average, or we could have, say, stochastic interpretation, say, okay, there is different outcomes, and they each occur with that kind of probability, right? So that's where we are. But note clearly that at this point, we have this description, so the system has interacted with the environment, we get this reduced state. The interpretation would be, we observe this outcome with that probability, but that last step, this stochastic element, is actually not in the theory, right? So we have to sort of add that still. Okay, so we did Schrödinger equation, we did open systems, so how do we get now the random outcomes?
10 minutes.
10 minutes, that's good. So you can describe the dynamics of the system and the environment by something called Lindblad equation. And it is an evolution in the density matrix of the reduced system. So we have the system, it's in contact with a environment, and the evolution of the density matrix has this first part, which is the unitary part, which you recognize as a Schrödinger equation before, for the isolated system, and then there is this second part, which is the coupling to the bath. This first part is unitary, this second part is not unitary. Okay? But the normalization of the density is preserved here, and note also that this equation, well, it's not clear from this, but this equation is also linear in the density matrix. So, okay, this This is a dynamics that holds for a system in contact with an environment in the limit that the coupling is not too strong. And it describes the average, it describes the evolution of the density matrix. And the density matrix, as I said, as I emphasized, is the average behavior, right? So how do we go beyond that? There's something called unravelings. And these unravelings, they are a stochastic process, a classical stochastic process, like a diffusion process, like any process, but a stochastic process of wave functions. So we have a wave function at time t, it goes to a wave function at time t plus dt, which has a certain increment, and this increment has deterministic elements, which is from the unitary dynamics, and it has stochastic elements, which come from the environment. And then we have classical variables, so this is our quantum variable, this is our wave function, and then we have classical variables, which are like observed quantities that are influenced by this quantum dynamics, and they also evolve according to a stochastic equation. And so this psi is now the wave function, but it is a stochastic quantity, and we can look at the average of this outer product, and we can define that as the density matrix. And there is a theorem, so when these two equations satisfy a continuous classical stochastic process, so continuous but not differentiable, so these are jagged trajectories, it's a Wiener process, and if the dynamics on rho and x is autonomous, so rho is this average quantity, that means that I can predict the new states of x and rho based on the old state of x and rho. Sounds like innocent enough, but this is what you need. This is actually not so trivial. So then these unravelings are unique, and they describe these Lindblad equations. Okay, so let's see how this works. So we have an electron. It is described by unitary dynamics of the Schrödinger equation. We get the influence of the environment. It gets a Lindblad equation, which tells us the prediction that here the particle should land somewhere, but now it's going to land actually here, and how we're going to get that. The way that this unraveling dynamics works is that there is a dynamics on the wave function. So the wave function starts out as a uniform wave function over space initially, and then it evolves and it collapses over time to either a wave function here or a wave function there in different realizations. And this is the dynamics equation of that wave function. And then then we can look at the average position of the particle as predicted by the quantum mechanics. Now this is the normal position expectation value, and so this is the explicit formula. But note that this psi is a stochastic quantity. So this thing is also a stochastic quantity. And this thing is influencing the measurement. That's this second equation. So the measurement outcome, was the second equation on this previous slide of the unraveling, is given by the mean prediction from the quantum theory plus noise. And these two dynamics, they both have noise in them. And this noise is correlated with a certain size, and this size also makes it possible to observe this classical process. If these two noises are uncorrelated, this gamma is 0, and there's no way for the classical world to actually observe the quantum effect. So that's essential. So, and here you see how that then works in simulation. Here's time, here's space. We see the x bar, which was this quantity, I repeated it here. You see in an initial, it goes from an initial value 0, it goes to this case, or in another run, it goes to this case. We have the m, which is the observed quantity. It is the integral of this thing, the thing that we classically observe. It starts out with a very bad estimate, which is the yellow line, and then it converges to the quantum prediction exactly. And we have the red line, which is the uncertainty in the position estimate in this case. And you see that the uncertainty in the position estimate goes to 0 as this, and that means that the wave function sharpens up to a position measurement. And you see the position in action. Okay, this is the end of my talk. Physics is our description of nature and is quantum. Reality is what we observe and is classical. Any system is limited and therefore non-deterministic because of its interaction with the environment. The non-determinism can be described as a classical stochastic process. Thank you very much.
Thank you, Bert. We still have 5 minutes for questions.
Hey, hi, my name is Uzi. Just a quick question about the uniqueness of the unraveling. So you said that unraveling results in a unique result, but usually uniqueness in differential equations also depends on the boundary conditions. So in a way, the boundary conditions should give you the
I don't mean
uniqueness.
uniqueness of the solution.
Okay.
I mean uniqueness of the unravelings. So there is different. So given the Lindblad equations, there is different unravelings. You can do Poisson processes. You can do unravelings that preserve the norm of the wave function. You can do unravelings that don't preserve the norm of the wave function. But if you insist on continuous paths and you insist on a coupling to classical variables, then it is unique. Then the formalism is unique. Yeah.
All right. Any more questions? So everything is clear.
That's good.
Well, thank you very much, Bert. The next speaker is Tarja Kallio-Tamminen from Physics Foundation Society, and she's also a vice chair of the Finnish Society for Natural Philosophy.
Okay.
And the title of the talk is The Content of Planck's Constant. What does the connection between Planck's quantum and Maxwell's equations reveal?
Yes, thank you. I'm very pleased to talk about this finding of Tuomo Suntola related to the Planck's quantum and Maxwell equations. Historically, Planck's quantum was the starting point for quantum mechanics. It led to the idea of wave-particle dualism and caused problems when interpreting quantum physics. As we do not have a common interpretation, we no longer know what reality really is. To uncover the factual character of the quantum would be important for creating an understandable conception of reality. At the beginning of the 1900s, the interactions between matter and radiation were studied in more detail. All material bodies emit electromagnetic radiation at wavelengths that are characteristic for them. It was measured what kind of radiation was born when metals were heated. What kind of radiation, for example, was emitted from iron when it first turns red and then white and bluish-white. It was noticed that the emission spectrum depends on the temperature, but not on the emitting material. The experimentally observed intensity distributions for different materials were well known for different temperatures at the end of the 19th century. And several researchers tried to find out what was happening in this phenomenon, which, because of the experimental setup, was called blackbody radiation. There were distinct approaches. Wilhelm Wien applied the thermodynamic approach, where the frequency of radiation in a closed space is proportional to the kinetic energy of the emitting atoms of the walls. Thus, Wien supposed that the radiation spectrum is determined by the emitters, which fitted well for high frequencies. Lord Rayleigh applied a different reasoning, which he had previously used for sound waves. He supposed each blackbody harmonic frequency, that is all the standing wave periods that are formed inside the cavity, contain same amount of energy in average, which means that radiation spectrum would be characteristic of radiation. And this fitted well for low frequencies. Max Planck came to the conclusion that radiation is emitted as wave packets whose energy is proportional to the frequency, with the vector h, which is known as Planck's constant. He presented a well-known formula, E equals F, which stated that radiation is quantized and quantum is a property of radiation. With this postulate, he was able to reconcile Wien's and Relay's approaches. The first signs of particle nature of radiation were thus found. Electromagnetic radiation was born in packages whose energy was the frequency F times constant h. By assuming this, the correct result was obtained, but the reason for this quantization was not clear. And now we come to Tuomo Suntola's antenna model, which gives an accurate approach to the quantum. According to the reasoning of this millennium-prized Finnish radio engineer, the smallest amount of radiation should be the one emitted by one electron when oscillating once in an antenna. Antennas, like all bodies, emit electromagnetic radiation at their characteristic wavelengths. And the vibration of single electron in a dipole antenna is the lowest possible radiation dose, the smallest amount of energy it can transmit. To verify this hypothesis, Suntola tried to derive the Planck's constant from the Maxwell equations. And he succeeded in this mathematical proof. The calculation also revealed that the constant h, which Planck discovered, includes other well-known constants, c, e, and mu0, as its components. In plain language, these symbols are velocity of light, elementary charge, and the vacuum permeability. Thus, the Planck's constant can be reduced. You can take speed of light out of it. Oh, sorry. Sorry. So, we are now. So, he noticed that Planck's constant can be reduced. You can take the speed of light out of it and get the intrinsic constant h0, which still contains elementary charge to the power of 2 and the vacuum permeability mu0. So, according to Suntola, the quantum is property of the emission and absorption process. And I hope you got the basic idea of this, because next we are going to talk a little bit about the history of waves and particles to get a better understanding of the meaning of Suntola's finding. Classically, it was thought that matter consisted of particles and radiation of waves. The particle was a distinct local object, while the waves were connected with electromagnetic fields that extended throughout space. In 1905, particle properties were more closely related to radiation when Einstein used Planck's idea of quantum to explain the photoelectric effect. And in 1924, de Broglie added wave properties to particles, which we will soon talk a bit more. But in 1926, quantum mechanics was born. Heisenberg first introduced matrix mechanics and Schrödinger soon after wave mechanics, which two theories were found to be different presentations of the same formalism. It's well known that this abstract theory is extremely difficult to understand, to interpret, many phenomena seem to be contrary to common sense, which of course is affected by Newtonian ideas we are so used to. 100 years of interpretation debate has not led to a generally accepted understanding of the nature of reality. Initially, Schrödinger tried to create a wave interpretation, but the complex and multidimensional waves, which depended on the chosen set of observables, could not be interpreted as waves in three-dimensional physical space. And in 1926, Born presented his probability interpretation. The square of the wave function gives the probability that a particle will be found in a certain location. And this kind of wave-particle dualism is nowadays generally accepted. Admittedly, the definition is quite abstract, but it is a practical necessity. Both concepts are needed to explain all the observations. De Broglie and later David Bohm were not happy with this kind of dualism, but sought for an alternative interpretation in which both the particle and the wave would be real. In his dissertation in 1924, de Broglie tried to generalize the wave-particle duality that was observed for radiation to material particles as well. He said, when I conceived the first basic ideas of wave mechanics in 1923-24, I was guided by the aim to perform a real physical synthesis of the coexistence of the wave and the corpuscular aspects. De Broglie derived equations for the wavelength and frequency of the particles, getting lambda equals Planck's constant divided by the momentum, P, and F equals the energy divided by Planck's constant. This kind of wave, however, does not correspond to the movement of the particle, and it does not fit into the quantum mechanics or the probabilistic interpretation of wave function. The wave packet usually breaks up because its group velocity is not the same than the velocity of the particle. But in light of Suntala's antenna model, the problem follows from the coarseness of Planck's constant h. When the speed of light is separated from h, what did it now? It don't move forward anymore.
Sanotaan, onko tämä oikein?
Okay, we are here. The problem follows from the coarseness of Planck's Weinstein. Yes, and when the speed of light is separated from h, the interdependence of mass and wavelengths becomes visible. So this is the real important finding. Mass and wavelength are related in Planck's constant, and the c can be removed from it. And according to Suntala's findings, we can separate the speed of light from Planck's constant, thus substituting h0c for h. De Broglie's equation can take the form lambda divided by h0. Lambda equals h0 divided by m, and f equals energy divided by h0 times speed of light. And this kind of waves can easily be interpreted as describing mass waves traveling at the speed of light, kind of Compton waves. And further, for the energy in the antenna, we get, for the energy of one electron transition, we can see, if I am able now, I don't dare, because then I may also mix it up again. But this equation in the middle is very important one and interesting. It gives that the energy of the radiation and the rest energy of the mass are equal, and they can be expressed in terms of each other. So the theorem of de Broglie is fulfilled. All waves contain mass that equals the intrinsic Planck's constant divided by the wavelength lambda, and any amount of mass can be expressed as a wave whose wavelength lambda equals the intrinsic Planck's constant divided by the mass. For this to be possible, the mass must be something else than solid particles. In the process of emission and absorption, mass and wave number can actually be transformed into each other by using the equation mass equals h bar 0 times the wave number k. So, a kind of genuine duality of mass and wavelength seems to prevail in nature. Probably Bohr was anticipating something like this when he emphasized the complementarity related to quantum phenomena. This kind of duality, however, does not prevent to describe all with waves, as Schrödinger maintained. The wave becomes much more real than just a mathematical tool for calculating probabilities. Particles can be described as closed mass wave resonators, and their momentum gets differentiated into something more tangible than just speed. The momentum of the moving particle manifests itself as a de Broglie wave, which is formed as the sum of the Doppler-shifted front and back waves of the resonator. Now we will see how this kind of particle, the Compton mass wave resonator, a kind of standing wave, should behave in a double slit. At rest and in the rest frame, the particle's momentum p is always 0. But when the resonator moves at velocity v, a new sum wave, de Broglie wave, is formed due to the Doppler effect in the laboratory frame. The wavelength of the front wave decreases and that of the back wave increases, so that a new wave moving at velocity v is formed. This de Broglie wave passes both slits and creates the interference pattern. The trajectory of the particle between the slit and the screen is determined by the probability, which is determined by the intensity of the interference wave. In addition to providing a new kind of explanation for this double slit experiment, there are further implications when removing the speed of light from Planck's constant. Now, when the wave description is carried through by using the intrinsic Planck's constant, that is by separating c from the Planck's constant h, many problems related to the interpretation of quantum mechanics disappear. The indivisibility of the wavelength gives a natural explanation why arbitrarily small amounts of energy or radiation quanta can't be generated. Because emission and absorption of radiation, they always occurs in whole wavelengths. And maybe Heisenberg's uncertainty principle also could be related to the perception of only entire wavelengths. Also, Suntola has shown that the discrete quantum states of the atoms can be seen as the minimum points of energy of the resonance condition of the de Broglie wave, this momentum wave. And probability could also be described using the energy principle as in thermodynamics. Also, the Schrödinger and Klein-Gordon equations can be expressed in a simpler form. So many of the mysteries discussed in the interpretive debates, they disappear by becoming comprehensible. What now happened? Now we can ask, why did it take 100 years before it was noticed that atomic emission, like blackbody radiation and antenna emission, behave in the same way? Maybe the mistaken idea that particles and waves are separate entities misled the research. Maxwell's equation was thought to describe continuous fields, but had the Planck's equation be written in the equal form, energy equals h divided by period, it would have been easy to see that it means the energy emitted into one cycle. Also related more to philosophy and psychology, the lack of a clear overall picture probably prevented focusing on the right things. Science, like all human action, is guided by the established concepts, ideas, and ultimately the whole worldview. That turned out to be limited along quantum mechanics. In such a situation, physicists and philosophers would have supposed to join forces in understanding reality. But the interpretation has not progressed much during the whole century. Maybe physicists and philosophers could cooperate better were we not just humans. However, now we have got a comprehensive theory that could offer a new worldview. Tuomo Suntola's dynamic universe is a unified theory of physics, a holistic, comprehensive paradigm that covers the different branches of physics. The findings we have discussed related to the nature of quantum can, in principle, be derived without the postulates adopted by dynamic universe theory. But in case we were ready to accept also the new, extremely plausible postulates of the theory, much more about the nature of reality would reveal. As Thomas Kuhn stated, a new paradigm means a new basic postulates and a new perspective within which some of the earlier problems turn out to be illusory and others may be approached in a new way. I hope Kuhn was not right when anticipating that a new generation of scientists would be needed before a change of this scale can be accepted. Thank you.
Oh, thank you, Tarja. Now we have 10 minutes for questions. And Mr. Kaplan.
Hello, thank you for the talk. So the M that appears
that's the mass. Right?
Yes.
So it's a mass of. So what happens in the case of massless particles if m goes to 0? Like photons.
They just then have the wave aspect. But it all comes from the theory. It is possible also deal with massless particles. It's no problem. And actually, because I didn't now go to the details or the more into that theory, it really is able to deal very well with all kinds of particles. No
Because you
problem
have the
with that.
mass is proportional to 1 over the wavelength.
Yes.
So if the mass goes to 0, the wavelength goes to infinity. But it seems for massless particles, like photons, you have...
Then you don't need that equation for that case.
But is there sort of a... How do you make that transition from massive to massless?
Well, maybe Tuomo can answer this.
Mikä oli, what was the question?
Massattomat hiukkaset.
Well, if we look dimensional analysis, we can see that energy is kilograms times meters per second, second to the second. So we can see that the nature of mass is more like a substance for the expression energy. So it's not a form of energy as we are used to state in physics in general. And it means that mass as an abstract substance of energy, it's similarly available in particles which can be described as mass wave resonators, Compton wave resonators, and it's available in electromagnetic radiation as h0 divided by lambda. It has dimensions of kilograms, so we call it mass equal. That's the substance of expressing energy times c to the second, which is the velocity to the second.
So in your theory, the photons have mass.
Well,
in that sense.
Well, photons. The energy of the photon needs mass as the substance for the expression of the energy, which needs both the velocity, which in the case of photons it's c, of course, and then it has the wave number type property. So h0 bar times k, which is the wave number, has the dimension of kilograms. So the kilograms describes the wave number of the photon.
Say that again?
Yeah, please state your name.
Okay. David Wallace. So I'm thinking of the section towards the end of the paper, of the talk, which considered the quantum measurement problem. Now, there's a standard concern about attempts to think about particles in wave terms in the measurement problem, which is that in the space of multiparticle, in the context of multiparticle entanglement, the wave function doesn't live in three-dimensional space. It lives in a high-dimensional configuration space. How do I fit that fact into this kind of approach to the measurement problem? I mean, it's a standard concern that's driving Schrödinger, that if wave functions lived in physical space,
Yes.
we'd have interpretive options available that aren't open to us because multiparticle entanglement doesn't allow us to think of wave functions in physical space.
I have not been dealing with this theory related to quantum mechanics so in detail, and I only gave the broad approach to it, and also what has actually not been done, I guess also either by Suntola or others. It is just on the more conceptual level that we can see that there is this connection, and it can be studied in more detail also in this new framework, but it is something that should be done in the future.
Going back to the expression quite early in the talk, which is effectively relating Planck's constant to, appropriate units, it relates Planck's constant to the fine structure constant. And I'm interested in the accuracy of the expression. I mean, in the current SI system, the value of Planck's constant is exact, and the value of the fine structure constant is known to 10 significant figures. So is that formula there accurate to 10 significant figures?
I guess that is, but Tuomo of course knows better how he found this, but he did very detailed calculation and was able to find out that it is really possible to yes. So you just have to be familiar with the antenna equations and all this, which is familiar for him, and that's why he succeeded in this derivation, which many people, I think, have tried over the years, but not succeeded.
So I'm not sure I heard the answer to that. Is it accurate to 10 significant
Well,
figures?
yes. Whether Tuomo would say, is it accurate, this value?
Yeah, the expression for the energy, which we can see here, it can be obtained for simple solution of dipole antenna. We need a little bit radio engineer's thinking in order to find out the result, and it's also very helpful to know what we are looking for, because as Tarja stated, it's first important to consider that we have to solve the energy emitted into one cycle of radiation, and certainly the smallest amount must be what we get out of one transition of a unit charge electron. And then it's useful to, or it's necessary to relate the length of the dipole to the wavelength emitted. That's something that radio engineering automatically does. And then we have the geometrical factor, which this case is 1.1049, which describes about antenna which emits energy into all three space direction. We can think that a point emitter can be considered as a dipole in the fourth dimension. So it has extension c times dt, which is equal to one wavelength. So it means that any point emitter can be considered as a one wavelength antenna. And then we need to match the electrical constant. Instead of epsilon zero, the vacuum permittivity, we need vacuum permeability, mu naught, and after that we get simply the simple result, which tells that there is C inside H. And that's very important, for example, for the reason that any atomic emitters emit radiation which is mc to the second divided by h, and when we divide or notice that c is also in h, we can find that any emitters are directly proportional to the velocity of light, which also guarantees that velocity of light measured with atomic clocks gives almost the same result. Thanks.
Okay, I think let's thank
Thank you.
Well, thank you very much. Okay, so welcome to the next session and our first keynote talk. And it's a great pleasure to introduce David Wallace. We actually met, there was this very nice philosophy of physics meeting in San Sebastian, Spain in October, where David and also Silvia Devianti. And I thought it was so good, and it also was so nice discussing with them. So that was one of the actually inspiration for this conference. And then we had, of course, our own project here. So somehow I felt that maybe if we can keep that that spirit of dialogue and discussion here. That would be great. And also, I felt that David he's a very knowledgeable person among many other things. So, you know, if you get a chance, ask him questions, and I think you'll enjoy. So you won't be at least for me, you won't be the smartest person in the room. But anyway, we'll see how it goes.
No pressure. Thank you for that unnecessarily generous introduction, and thank you for organising this lovely meeting. It's a pleasure to be in Helsinki. Okay, so as Paavo set out in the first talk, then the quantum measurement problem has this fairly bewildering sprawl of structure and collection of approaches and ideas and ways to handle it. But in the last sort of 30 or 40 years of philosophy of physics, never say philosophers reach a consensus, but there's the kind of next best thing philosophers tend to get to a consensus, which is a fairly widespread agreement on the starting point of the problem, which I want to make some trouble for in this talk. And that sort of rough consensus on the problem kind of looks like this. It says, firstly, there are what you might call anti-realist ways of thinking about quantum mechanics, but we should reject those approaches on sort of general philosophy of science grounds. I should say, to pick up on something Paavo said, I think it's absolutely right that a lot of people in various bits of foundations avoid saying anti-realist because realist is seen as a kind of virtue term. Chris Fuchs is absolutely explicit if you ask him that the reason he doesn't want to say anti-realist is because everyone hates anti-realists. I'm not actually using the term pejoratively. I think realism is a way of thinking about the interpretation of scientific theories. I'm inclined to think the correct way, but philosophers of science should, in my view, absolutely take seriously the idea that the quantum measurement problem points us towards rethinking how we conceptualize a scientific theory. And it's worth remembering that the basic mathematical structure of quantum mechanics has remained fixed for about 100 years, and philosophers have changed their minds at least 5 times about the best approach to scientific theories during that period. However, notwithstanding that, the kind of conventional wisdom in philosophy of physics has tended to be that the problem with the anti-realist approaches is straightforwardly that they're anti-realist. I'm not mostly going to talk about those approaches in this talk. I mostly want to talk about the second pillar of the conventional wisdom, which basically says there are 3, or at least 3, different approaches we've come up with to solve the measurement problem in a realist way. And those ways are, broadly speaking, the ever-at-many-worlds approach to quantum mechanics, hidden variable theories exemplified by the de Broglie-Bohm theory, of which we've already heard much, and dynamical collapse theories in which the collapse of the wave function becomes some physical process triggered not by measurement per se, but by some macroscopic scale of the system. I say there are at least 3. There are a bunch of other things people have played with. We could talk about retrocausal approaches. We could talk about certain modal approaches. Arguably, we could talk about various consciousness-based approaches, although they tend to fall in a slightly different space. But at any rate, there are at least 3 programs, according to the conventional wisdom, all of which solve the measurement problem in a realist way, all of which make the same predictions, either in principle or at any rate in practice, and so all of which are empirically equivalent in the usual philosophy of science sense. So here's... At one point, I could see the view on the screen there to avoid craning over my neck. Can I get that back? Yeah. Meanwhile, I'll turn to the screen and look across. So here's, just as an example of, that's perfect, thank you. It's an example of that conventional wisdom. Here's Dennis Deeks. The different interpretations of quantum mechanics that we have sketched can be taken to be empirically equivalent in a strong sense. No future macroscopic observations can be expected to be able to distinguish between them. As a quick caveat, he's being a little careful about that because he's aware that in principle, theories of quantum mechanics where the wave function collapses dynamically make different predictions from standard quantum mechanics in exactly those cases where the collapse happens, or at least if you can isolate it from ordinary measurement contexts. He's working on the assumption that's also, I suppose, part of the conventional wisdom that
in the foreseeable future, experiments simply won't actually allow us to distinguish these theories, even if they could be distinguished in principle. That, I think, is also wrong. I'm not really going to talk about that, but the experimental progress on dynamical collapse theories has been very interesting. Ask me about it over coffee sometime. In any case, the second pillar of the conventional wisdom leads to a third pillar of conventional wisdom, which is that since we have these three, or at least three, interpretations of quantum mechanics that are all empirically indistinguishable, then the measurement problem is a special case of the classic philosophy of science problem of the underdetermination of theory by evidence. In other words, of what we should do when we're confronted with multiple, logically inequivalent, metaphysically inequivalent scientific theories which are nonetheless empirically equivalent. This is an issue that philosophers of science have bashed their heads over for 50 years. According to the conventional wisdom, the measurement problem is revealed as an aspect of the general underdetermination problem. Or at least, whatever else it might be, it's at least partly an aspect of the general underdetermination problem. Again, just an example of this in the literature. Here's Matthias Egg. Choice between different quantum ontologies is underdetermined by the scientific evidence. Underdetermination occurs between the different responses to the measurement problem. These are sometimes called different interpretations of quantum mechanics, but it's more appropriate to view them as predictively equivalent rival theories, which makes them an instance of the well-known problem of underdetermination by theory by evidence. Anyone I'm quoting here, by the way, I think is interesting, worth reading, and says sensible things. When I quote here, it's not to criticize these positions exactly, but just to demonstrate their presence in a very mainstream part of the philosophy of quantum mechanics literature. Okay, so supposing that's true, supposing it's right that the measurement problem is a special case of the general problem of underdetermination, what would follow from that? Well, at least for philosophers, there are three main things that you can pick up from the literature as being said to follow from that. The first is that underdetermination is real. So one of the classic questions in the philosophy of science has been, is there any underdetermination in the first place? Are there really cases of scientific theories where there are multiple theories and the theories are empirically equivalent, not just right now, but in principle? You'll recall, if I ask what killed the dinosaurs, well, we know that there was an asteroid impact at 65 million BC, but we also know there was a lot of volcanic activity. The causal chain from the asteroid impact to the extinction process isn't completely clear. So at some level there is, or at least perhaps things have improved recently, perhaps there was underdetermination as to whether the cause of the death of the dinosaurs was the asteroid impact or the volcano trap effect, or maybe some mixture. That kind of underdetermination is innocuous to science. The way you solve it is, of course, you just do more science. It simply shows that at any given point we might not yet have collected enough evidence to know. The kind of underdetermination that matters for philosophy of science is underdetermination that's not going to be solved either in principle or even in the long run in practice through just collecting more data. And it's been controversial whether that actually happens. Some of the examples philosophers give are the sort of toys that one can't really take seriously as science. So, for instance, there's underdetermination between general relativity and the theory that nothing exists outside the solar system, but everything looks as if general relativity is true. That kind of underdetermination in practice doesn't tend to worry us. Or there's underdetermination of a kind of subtle metaphysics side. So maybe there's underdetermination between the general theory of relativity understood as a story about curvature and the general theory of relativity understood as some kind of field theory involving a spin-2 field. That kind of underdetermination tends to be an underdetermination of the verbal glosses we put on our theories. It's not an underdetermination of the kind of mathematical formalism of the theory. The kind of really substantial underdetermination would be a case where we had formally inequivalent theories that were nonetheless empirically equivalent. It's been contentious whether that ever happens in philosophy of science. In fact, the measurement problem itself is usually the classic example given to argue that it does happen. And so a key aspect of whether the sort of underdetermination thesis and the measurement problem is true is, do we indeed have underdetermination in philosophy of science? So that's the first aspect of the philosopher's response to underdetermination. I'll skip Calendar's quote there. I think it's just for evidence. Second response to underdetermination, when we're debating the quantum measurement problem, it's going to be debated in a quintessentially philosophical way. In the philosophy of science literature, the classic way that underdetermination is said to be resolved is through so-called extra-empirical virtues. So it might be that two theories are empirically equivalent, but one is simpler, or one is more fruitful in its development and prospects for future theories, or one of them explains more or explains better than another does, or one of them is more, more intuitively reasonable, if you think that's a good condition for a theory. So according to that aspect of the response, then the way we should discuss the measurement problem would be about comparing these kind of philosophical virtues of the different theories and weighing one against another. And indeed, you see this in a lot of the philosophy of quantum mechanics literature. So here's a nice sort of review of the measurement problem by Acuna a few years ago. He says, the predictive equivalence between quantum theories implies that a choice between them is underdetermined by the evidence, ... Both in physics and philosophy of physics, there are several parties which defend one or other of those theories, so it's obvious that some philosophers and physicists do make a choice. Such a choice is based on non-empirical considerations, pragmatic, epistemic, ontological, and metaphysical criteria. These non-empirical factors, though subject to controversy, are not arbitrary, and so he optimistically concludes, evidential underdetermination notwithstanding, a rationally supported choice between quantum theories can be made. So corollary of this, if you've got philosophers arguing in favor of one or other interpretation of quantum mechanics, as I've been known to do myself from time to time, then those philosophers aren't irrational, heavens no. But since the theories are since there's underdetermination between the theories, they clearly can't be arguing about anything empirical. They must be arguing about something extra-empirical. And again, you see this in the measurement problem literature. How do we choose between interpretations of quantum mechanics? Do we use probability? We can't justify interpreting Everettian mod-squared amplitudes as probabilities. No, actually, we can justify it better than that. The Everett interpretation proves our philosophy of probability. Or people could talk about redundancy. The particles in Bohm's theory are epiphenomenal. They just wander along, tracking where the wave function goes. No, the whole point of the particles is that's what phenomena supervene on, and it's a virtue of Bohm's theory that it gives us a genuine, ontological reality. Or Occam's razor. Many worlds is wildly extravagant. Yes, but Occam's razor is about simplicity. We don't care about how much stuff there is. We care about how simple the theory is. Sometimes people want to talk about the unitarity of the Schrödinger equation. It's inelegant and empirically unjustified to add a Klotz rule to quantum mechanics. No, it isn't. You can see the structure of that way of thinking about the measurement problem running through a lot of the philosophy of quantum mechanics literature. And that sort of brings us to the third philosopher's response, which is that if that's right, there's a kind of continuity between the choice of an interpretation of quantum mechanics and some sort of more general questions in metaphysics. So there's no fundamental difference between what's the right interpretation of quantum mechanics and should we be eternalists or presentists about identity of objects over time? Should we be mereological nihilists or selectivists or universalists? Should we believe in tropes? Should we be Humeans about causation? And so you might think that the measurement problem has kind of matured into being one of these classic philosophy problems that will just be with us forever. That sort of brings us to the physicist's response that I think you get if underdetermination is the way to think, which is, broadly speaking, shut up and calculate. There's a sense, the Philistine physicist who says shut up and calculate is sort of excoriated by philosophers of physics as not caring about what's going on in deep reality. But there's a sense in which if the quantum underdetermination idea is right, then the shut up and calculate physicist gets the last laugh. Because if really the alternative to shutting up and calculating is just getting into a completely interminable, never to be resolved clash of intuitions as to which of in principle, empirically inequivalent theses are correct, then maybe we should shut up and calculate. So anyway, quite a lot then is hanging on whether the quantum underdetermination thesis is true. If it's true, rather a lot follows. And the main thing I'm going to say in this talk is it's not true. There is no indetermination of this kind. It is not correct, when we think about it more carefully, that we have underdetermination. And so anything that follows from that claim is false, or at least not justified by that claim. And to be slightly more clear about the claim here, the way we set up the idea of underdetermination here is an underdetermination not between interpretations of theories, but between theories mathematically formulated. So the theories I have in mind here are, firstly, unitary quantum mechanics, the Schrödinger equation, no collapse of the wave function, model everything dynamically, model the classical to quantum to classical transition through decoherence theory and as a dynamical process. Unitary quantum mechanics versus theories that supplement unitary quantum mechanics with hidden variables, which are required as part of the structure of the theory to be that on which experience supervenes, versus dynamical collapse theories, which don't simply supplement the dynamical equations of quantum mechanics, but modify them and explicitly introduce stochastic terms into the equation, not simply as an unraveling of the dynamics, as in the very nice talk we saw earlier, but as a genuine posit that is supposed to supersede the Schrödinger equation in certain situations. So that's the supposed underdetermination I have in mind here. You can roughly track it as an underdetermination between many worlds and Bohm and GOW, but I'm not going to argue in this talk, for instance, that the only way to make sense of unmodified unitary quantum mechanics is Everett's way of doing it. I just want to talk about the mathematical formalism that underlies Everett. And because, in fact, I think that the Everett interpretation is the only, or at least the most defensible way to make sense of unitary quantum mechanics, I'm sometimes going to slip between saying unitary quantum mechanics and Everettian quantum mechanics. But what matters for my purposes here is the sort of mathematical core of this and the use of and the core role of decoherence theory as the route from the quantum to the classical. Okay, so what's going on when I claim there's no underdetermination? Well, here's a warm-up case. We've talked about possible interpretations of quantum mechanics, which the Everett interpretation, the hidden variable interpretation, the dynamical collapse interpretation. Here's a much better interpretation, all of them, the classical mechanics interpretation of quantum mechanics. So according to the classical mechanics interpretation of quantum mechanics, classical mechanics is true. And this is great. This theory has no action to distance. It has a separable ontology. It has a primitive ontology. It's got a clear path from theory to observation. It's extremely intuitive. And it's not ontologically profligate. There are no many worlds in classical mechanics. Right, why is classical mechanics not a satisfactory solution to the quantum measurement problem? I take it the answer is kind of obvious. It doesn't reproduce any of the data. The problem with classical mechanics is simply that there's a whole bunch of quantum phenomenology that it just doesn't get right. And so obvious, I mean, that should seem so obvious as to be scarcely worth saying, but it's surprisingly easy to lose track of it. What we want more than anything, before anything, in a, quote, interpretation of quantum mechanics, in a solution to the measurement problem, is the ability to reproduce the quantum data, which classical mechanics can't do. But there's then a qualifier to that, which is sometimes when people want to reproduce the quantum data, what they mean is something like this. We should have a theory that can reproduce the key distinctively quantum features of quantum mechanics. In other words, we should have a theory that can reproduce the superposition principle, can reproduce quantum entanglement, can violate Bell inequalities, can do all those kind of things that we think characterize quantum mechanics qua quantum mechanics. But I don't think that's the right way to think about the underdetermination problem, or more generally about the measurement problem. And incidentally, we'll freely concede that we certainly have multiple theories that can do this. Here's what we actually want from a solution to the measurement problem. We want it to do it all. We want a theory that can actually reproduce all the things quantum mechanics actually predicts, which sure includes all these nice, quote, distinctively quantum phenomena, but it also includes the BCS theory of superconductivity, the spectra of the atoms, the reaction rates we find in nuclear processes, the cross-sections for scattering in quantum electrodynamics, the anomalous part of the electromagnetic moment. We want to understand the electroweak symmetry breaking in the regime that gets probed by the LHC and the restoration of that symmetry in the early universe. The reason we liked quantum mechanics in the first place was it's the most amazingly successful predictive and explanatory theory in the history of physics, and arguably challenged by the theory of natural selection in the history of science, full stop. If we can't do those things, we haven't actually reproduced the predictions of quantum mechanics. And so only if we have more than one formally distinct theory that can reproduce all of that stuff, do we actually have underdetermination theory by evidence? And I want to say that unitary quantum mechanics can absolutely reproduce all that stuff, and indeed was the framework in which all that stuff is done, and that other approaches, to the best of my knowledge, all other approaches that actually try to kind of naturalistically modify the quantum formalism, I'm again putting aside something like, say, consciousness-based approaches, all modify the formalism, supplement the formalism approaches, have yet failed to do that. We do not have a mathematically formulated alternative theory that can reproduce the whole range of predictions of quantum mechanics, or indeed very many of the predictions of quantum mechanics. So let me give you an example, the eponymous example of my talk. I'll come back to that point. Actually, sorry, I'll skip back to my here. Here's my eponymous example. The color of the sky is, you know, I'm British, so one sometimes needs sort of theoretical observation to pick this up, but the color of the sky is blue. Why is the color of the sky blue? Because the relevant scattering process that controls the color of the sky is the scattering of light off air molecules. That scattering involves radiation of a wavelength much larger than the wavelength of the objects off which it scatters. The relevant scattering is Rayleigh scattering. Rayleigh scattering preferentially scatters towards one end of the spectrum. That gives us the fact that air is blue. That gives us the result that the sky is blue. This is a prediction of quantum mechanics. Qualitatively, you might say it's a prediction of classical mechanics, but if you want to know just how blue the sky is, it's a prediction of quantum mechanics. It's outside the scope of any theory other than unitary quantum mechanics that we have so far. Okay, but to fill in the detail of that and expand it, let me go back, because I put that slide in the wrong place, and just cash out a bit more what the form of the claim is going to be. So here's a part of what I'm going to require for a theory to do to reproduce, to counter-reproducing the quantum formalism. It's going to be necessary that a quantum theory models the phenomena and models the measurement process by which the phenomena are measured, at least in idealization. So in other words, if I want to explain, say, the two-slit experiment, to which we'll come back, my theory is going to have to describe the particle that passes through the two slits, but also the detection apparatus that picks up the particle. I don't think it's a general requirement for the interpretation of a theory that theories are required to model their own measurement processes. General relativity, for instance, basically never models its own measurement processes. General relativity, for instance, contains gravity waves, but the devices that detect gravity waves are quantum devices that general relativity can't model. But solutions to the quantum measurement problem have to model their own measurement devices, at least realist ones do, because, well, the clue's in the word measurement in the measurement problem. All of these various approaches are concerned with how the formalism handles the scaling from the microscopic to the macroscopic, how it goes from a microscopic theory in which we just have a primitive Born rule to an actual set of probabilistic claims about measurement devices. And incidentally, I mean, here's Tim Maudlin, just to show I haven't just dumped the requirement to reproduce the measurement process on my critics. Here's Maudlin in his recent Philosophy of Quantum Mechanics book. He says, a precisely defined physical theory would never use terms like observation, measurement, system, or apparatus. It would say precisely what exists and how it behaves. If the description's correct, then the theory will account for the outcomes of all experiments, since experiments contain existing things that behave somehow. Applying such a physical theory to a laboratory system would never require one to divide the laboratory up into system and apparatus, or to make a judgment about whether an interaction would count as a measurement. The theory would postulate a physical description of the laboratory and use the dynamics to predict what the apparatus will or might do. So Maudlin, as an advocate of hidden variable theories, is very much on board with the idea that modeling the measurement process is a requirement of what we're supposed to do in a solution to the measurement problem. Okay, so let me spell out in a bit more detail the quantum underdetermination is false claim I want to make. So the focus of what matters here is interacting quantum field theory. So a quick reminder or quick refresher or quick lesson, if you don't know, the sort of shape of quantum mechanics as a scientific discipline, stepping aside from the measurement problem. The thing one learns in an undergraduate first course in quantum mechanics is generally what gets called non-relativistic quantum mechanics, which is the theory of atoms and nuclei and electrons moving at speed slow compared to the speed of light, and interacting by effectively action at a distance interactions with each other through electric charge, for instance, or with background electric and magnetic fields. Beyond non-relativistic quantum mechanics, you get quantum electrodynamics, which is the theory that then includes light. Light is modeled in quantum mechanics by photons, but photons are not treatable as particles in the way undergraduate quantum mechanics treats them. The photon is a quantum of the quantized electromagnetic field, and a full and consistent treatment of the interaction of electrons and nuclei with light requires that quantum field theory. And indeed, in quantum field theories, even the matter particles become reinterpreted as excitations of certain quantum fields. And quantum field theory is the general language in which we do relativistic quantum mechanics, in which we do particle physics, increasingly in which we do solid-state physics, in which we do, well, increasingly everything, frankly, but everything in quantum physics outside the highly important but relatively narrow space of non-relativistic quantum mechanics. And the claim is going to be that there are no fully worked out versions of collapse theory or hidden variable theories or anything else I know other than unitary quantum mechanics itself that can apply to the domain of interacting quantum field theories so as to reproduce the empirical predictions of quantum field theory. QFT is quantum field theory. And there are also reasons to expect that's not just a trivial matter, that it's going to be very difficult to construct theories of that kind. And even if exotically we decide we don't care about the predictions of relativistic quantum theory, and we look at the supposed predictions of non-relativistic quantum theory, only a tiny fraction of even those are reproducible inside these modificatory approaches, largely because of the need to model the process of measurement. Let me cash that out. So let's go back to the sky is blue starting example. So the actual physics of the color of the sky involves the cross-section for scattering of photons off atoms. That's clearly a quantum electrodynamic process. To model it, we need quantum field theory. Second example, the spectra of the atoms. You know, one of the key pieces of quantum mechanics that sort of got the subject going and drove the original calculations even before the theory was fully worked out. The calculations we do for the spectra of the atoms are actually non-relativistic calculations, at least modulo some higher order correction terms. We take for the spectrum of hydrogen, for instance, we take an electron and a proton. We solve the non-relativistic Schrödinger equation for that system. We observe energy is quantized, and we look at the energy levels. But what we actually observe, literally observe, from this atomic spectra are lines of emission light in the radiation given out from a heated hydrogen gas. What are we seeing? We're seeing photons. Why are we seeing photons? Because thermal processes will excite a hydrogen atom from its ground state to its first excited state. It will then emit a photon and drop back down again. That is a quantum electrodynamic process. Its full description requires quantum field theory. If you study this as an undergraduate, but never got as far as QFT, if you look back at your notes, you'll find a little bit where you waved your hands in the direction of the Einstein A and B coefficients and kind of finessed it out. But if you want to do that analysis properly, you're doing it through quantum field theory. Think about the two-slit experiment. Again, in a certain sense, canonical example of non-relativistic quantum mechanics. Well, of course, the original two-slit experiment was done with photons. Photons are pieces of quantum electrodynamics. You get how the story goes. We sometimes do the experiment with particles. The most common ones we do have involved electrons and neutrons. Interference processes involving electrons and neutrons are modelable inside non-relativistic quantum mechanics. The way we detect electrons involves, in most of the experimental physics methods we use, involve various kinds of excitation processes where the electron will excite a system to release a photon of light. The way we tend to detect neutrons is through various radiation processes that, to model them fully, require fragments of the nuclear force and pieces of quantum field theory, even outside electrodynamics. So again, although the physics of the two-slit experiment itself is modelable non-relativistically, then the detection process is not. So quite a small part even of the kind of core of, quote, non-relativistic physics is fully modelable without using quantum field theory. As a digression here, I mean, you can sort of tell from the history of quantum physics, this came out in Pave's presentation, that the issues of the quantum nature of light were foundational to the subject right from the beginning. The reason we don't teach that to undergraduates straight away is just because it's difficult. You know, the reason that one learns as undergraduate non-relativistic quantum mechanics and then by and large doesn't learn relativistic quantum electrodynamics until late in one's undergraduate career or in grad school isn't because somehow there's a really delineated domain in which photons don't matter at all. It's just that it's much harder, and one needs various steps of sort of mathematical maturity to manage it. But I think because of that, one can fool oneself into thinking that there's that the whole experimental domain of non-relativistic quantum mechanics is self-contained. It doesn't require call-outs all the time to our theory of electrodynamics. And this is without even starting on the actual phenomenon of interactive quantum field theory, I could say, and all the stuff that's found at CERN and all the stuff that's seen in the cosmos. So here's the basic shape, sorry, that's first like I've tried some reason. Here's the basic shape of the framework, the subtle new philosophical notion of a challenge, which is extremely like a challenge, but is subtly different in ways I'll try to demonstrate. Or possibly I've misspelt it, I'm not sure which. So here's, what I want to explain is now why it is that one should think not just that we don't, right this minute, have quantum field theory versions of our Bohmian hidden variable theories and our dynamical collapse theories, but that it's going to be very, very hard to get them. So I want to give you a sort of elementary picture as to why that is. So, because, I mean, a natural response one might have here is, okay, fine, there's obviously a technical problem that the physicists need to solve to have a hidden variable theory of quantum field theory or a dynamical collapse theory of quantum field theory, and we philosophers haven't got much to contribute to that project, but, you know, I'm sure they could find a rainy afternoon someday and knock it out, so we can more or less assume it's done and get on with things. It's going to be way, way, way harder than that. And here's why. The kind of modificatory theories we've got at the moment in the non-relativistic particle domain, so Bohm's theory and dynamical collapse theories like the GRW theory, for instance, the way those theories work, by and large, is they rely on the fact that position has a special dual status in non-relativistic quantum particle mechanics. What do I mean by that? Well, firstly, position is microphysically central. Position is playing a sort of foundational role in the theory. Well, often one even formulates non-relativistic quantum mechanics in terms of wave functions on position space and only learns about the sort of abstract Hilbert space way of doing it later. Even if one isn't taught that way, then position is showing up centrally in the way you state the observable algebra for the theory. It shows up in the representation theory of the framework. It shows up in the microphysical forms of the potentials, which are expressed in terms of functions of position. So position is kind of, in a philosopher's sense, fundamental in non-relativistic quantum particle mechanics. But it's also related directly and simply to observations of the macroscopic. It's not indefensible to say, as many modern Bohmians say, that the fact about where this lectern is can be understood simply as a sort of agglomeration of the facts about where all the particles in the lectern are. So you've got a simple story that takes me from the particle data of the theory to the observable content of the theory. There is no such dynamical quantity in quantum field theory. The empirically relevant dynamical quantities in quantum field theory, the things about, you know, the positions of the non-relativistic particles that eventually emerge as an approximation to quantum field theory, maybe the strength of the classical fields that emerge as an approximation to quantum field theory, those things which subserve the macroscopic, those things are dizzyingly indirectly related to the microphysics, derived in a complex, indirect, approximate, high-level way. There's a kind of chain of derivations and approximations and coarse grainings that take us from the true microphysics of quantum field theory to the observed physics. And conversely, the microphysically central dynamical quantities, you might think, like, where are the bare particles, the true microscopic particles? What are the expectation values of the bare fields, the things that are put in the microphysical statement of the theory? Those things bear no simple or transparent relation to observation. And those observations, although they're not normally talked about in these terms in the quantum field theory literature, are central in the kind of revolution of our understanding of quantum field theory that's happened in the last 50 years. And for those who've looked at this, I'm thinking of the sort of move to the understanding of renormalization through Wilson's work and the development of the effective field theory paradigm in the 80s. So let me cash that out. I'm not trying to assume any knowledge of quantum field theory here. So take some sort of classic, quantities in a quantum field theory, the charge of the electron, the mass of the electron, how many electrons are there? Well, parameters like charge and mass in the Hamiltonian, the dynamical equations of quantum electrodynamics, they're what get called Baire parameters in the QFT literature. They're not directly measurable. They're related to measurable parameters extremely indirectly. The measurable quantities are non-fundamental, they're dynamically mediated, they're highly dependent on the energy level you look at it. And to give you a heuristic picture as to why, you can think heuristically that a real electron, if you look at it super close together, is generating a very strong electric field, it's polarizing the vacuum, in quantum field theory, particles can be created out of, in particle-antiparticle pairs with enough energy present, so you can think in a certain sense of the space around an electron being permeated by little virtual pairs of electrons and anti-electrons. When two electrons collide, you can think about the collision process as involving an interleaving of that cloud. What one electron sees as it approaches another electron is not the bare electron, it's the blob. How much of the blob it sees, how close it gets to the bare electron, depends how hard you hit them together. Exactly when you say this bit of the blob is part of the observed electron, this bit is stuff the observed electron interacts with, is somewhat arbitrary. There are useful conventions for various calculational purposes, but nothing deep that tells you where to do that. All of those terms are heuristics, by the way. I mean, underlying that is a whole bunch of Feynman diagrams, but the heuristic is a good way to visualize what's going on. And likewise, when I've got a state that's a detectable particle, the particle that turns up as a click on my screen when I do the two-slit experiment with an electron, that particle is a really complicated quantum superposition of the various Baire particles in the underlying theory. It's got all of those particle-antiparticle pairs floating around in some chaotic, weird mixture, or superposition, rather. That's not the worst of it. Let's talk about quarks and protons. There's no non-arbitrary definition even of the detectable mass of a quark. That parameter is a very theoretical parameter. We define it somewhat conventionally. Quarks are bound into protons. Protons are complicated, dynamically defined, emergent excitations of quarks and gluons. You learn in high school that a proton is made up of 3 quarks. That's something between a massive oversimplification and a nice story to tell children. The proton is a weirdly complicated and still only very partially understood dynamical excitation of the underlying quark fields. That's not in any simple way, just 3 quarks together. So the dilemma if you're writing a hidden variable theory, well, the fundamental parameters of the theory are going to be in terms of the quarks. The observable phenomena of the theory are going to be in terms of the protons. If I write my theory in terms of the protons, I haven't done what we want of a microphysical solution to the measurement problem, which is to write down a piece of fundamental physics. I've directly called out to some high-level, dynamically mediated approximate idea. If I formulate my theory in terms of quarks, I'm just not going to reproduce the macroscopic data, precisely because there's no simple way using the microphysical language of quarks to describe what's happening at the macro level. It gets worse. Huge amount of the phenomenology of particle physics is to do with what's called spontaneous symmetry breaking. Various symmetries in our exact and approximate symmetries in our best theory of particle physics, the Standard Model, are spontaneously broken, which means that although the laws obey the symmetry exactly or approximately, the vacuum state, the lowest energy state, does not obey the symmetry. So what that means is what's actually in the vacuum in empty space is a complicated mess, to use a technical term. Some kind of excited condensate of quark-antiquark pairs, some kind of excited condensate of the Higgs field, something whose structure we still only partially understand, but something that's very, very far from empty space. The, quote, vacuum is highly excited, extremely complicated compared to any of the bare degrees of freedom that appear at the fundamental level. And again, the empirically relevant particles are determined by the modes of excitation of the vacuum. Again, they're dynamically mediated. They also depend on how hot it is. They depend on sort of classic macrophysical parameters of that kind. And the overall shape of all of this, and the sort of the reason why all of this is so problematic, is that these days we're used to thinking about quantum field theory in terms of what are called effective field theories. You know, for 40 or more years, the consensus has been that the low energy degrees of freedom in a quantum field theory, that is the low energy meaning large length, meaning macroscopically accessible degrees of freedom, just largely float free dynamically from the microscopic degrees of freedom in high energy physics. The form of the low energy physics is fixed by only very broad and general features of the high energy physics, such that the dynamics will just sort of sort it out and give us the appropriate low level, low energy collective degrees of freedom. And that means the whole structure of modern quantum field theory is just really badly suited to any approach that's going to say we're going to build a physical theory by starting with a fundamental theory, expressing a fundamental ontology, and then supposing that we can relate that fundamental ontology in anything but the most indirect and dynamical way to what we observe at the macro level. And the whole structure of the hidden variable approach to solving the measurement problem, or the dynamical collapse approach to solving the measurement problem, trades on that idea. It tries to start with the fundamental theory, and then write some kind of collapse law or hidden variable law in terms of the fundamental theory that's then supposed to transparently deliver us the macroscopic theory. And the lesson of quantum field theory since the 70s has been that's not how the theory works. You could incidentally say, well, that's a problem for quantum field theory. People will say, well, if that's all physics is going to give us, then physics has just gone off the rails and we want something better. Well, maybe. But look, it doesn't matter how much you hate quantum field theory, you still can't calculate the anomalous magnetic moment of the electron. So the underdetermination thesis, the claim that you can reproduce stuff, doesn't go away if that's the case. You can't produce empirical predictions from your preferred theory by pointing out a problem with another theory. I mean, you could say the same if you're being a bit more explicitly Everettian. It doesn't matter how good your conceptual objections to a many-worlds theory are, those conceptual objections by themselves will not allow you to calculate the anomalous magnetic moment of the electron. So, if one thought it was, after all, possible to build a modificatory theory of quantum mechanics that did handle quantum field theory, if you thought all of my arguments here are too pessimistic, if you think it can be done, if even you think it has been done in outline, you can sort of put it as a challenge. Pick an empirical prediction of QFT. I mean, better, pick a sort of representative sample of empirical predictions of QFT. Actually reproduce them. Actually do the calculation. And that means you need to at least model the outline of the measurement process, for the reasons we've discussed. And here's a technical observation. It means you better work to at least one loop order in quantum field theory to make sure you actually have to get down and dirty with all the issues of renormalization that have driven all of the structural revolutions in understanding quantum field theory. Or, and this in some ways comes to the same thing, start with your preferred modificatory theory and fully derive non-relativistic quantum mechanics inside it as an appropriate regime. And confirm that the variables which non-relativistic quantum mechanics requires to be definite indeed are definite. To the best of my knowledge, and I'm fairly confident, no one has done that. There is no actual soup to nuts derivation of any of the substantive results of QED, let alone the standard model, to loop order, I mean, rarely even to tree order, but to loop order inside any modificatory program. And that's the challenge that needs to be met if one wanted to claim, yes, we have an empirically equivalent theory, or something that's even a candidate for being empirically equivalent to quantum field theory. Again, in loop order. Okay, let me wrap up. Most even of the predictions of non-relativistic physics, let alone all the relativistic stuff, can't be reproduced by any modification of quantum mechanics. The space of concrete empirical quantum phenomena for which the modifications of quantum mechanics solve the measurement problem is not large. If you look hard, you can see the occasional experiment in non-relativistic quantum mechanics where the detection process also looks modelable in non-relativistic quantum mechanics. I don't think that set is empty, but it's pretty small. And so the measurement problem is not, in any meaningful sense, a case of underdetermination of theory by evidence. And so if there's an argument for modifying quantum mechanics, it's got to come from the impossibility of solving the measurement problem inside unitary quantum mechanics. In other words, the right position for thinking one should modify the measurement problem, modify quantum mechanics to solve the measurement problem, shouldn't be the sort of complacency of saying we've got lots of options and I find this option nice. It should be something like we have only one option and it's unacceptable, and we have no way to make sense of unitary quantum mechanics, so notwithstanding how super successful it is, we're logically forced to change it. Help, that sounds really hard, but we have to do it. And from that point of view, it's great that we've got dynamical collapse and hidden variable theories that are proofs of concept, because at least they do provide toy theories that reproduce the, what I was calling earlier, the sort of core, specifically quantum features of quantum mechanics. So in other words, if you think that the measurement problem is insoluble inside unitary quantum mechanics, and I'll disagree with you, but it's a perfectly honorable thing to think. If you thought that, then that gives you motivation to try to approach this profound technical problem. But it's important to realize that there is this profound technical problem to solve, and were it not for the supposed impossibility of solving the measurement problem, one would have very little reason to think it's solvable, because rather deep features of quantum field theory just look inimical to the way in which modificatory strategies are done. And in fact, I think, if you force me to commit to trying to develop a modificatory strategy, I think the way quantum field theory works suggests that the whole way those strategies are written is probably off on the wrong foot and needs to engage much more with the sort of way effective field theory is structured. And I think the need to try to find an effective field theory way of thinking about hidden variable theories or dynamical collapse theories would be urgent if one was really trying that task. Okay, let me just finish with a little epilogue that links to some of the other themes that came up. I talked about a conventional wisdom that says there are anti-realist approaches, and the problem with them is sort of broad philosophy and anti-realism, and conversely there are underdetermination in various realist approaches, and again that's a philosophical question, and I've criticized that, or aspects of that. Here's an alternative way of thinking that I think I works better. Don't think in terms of a whole bunch of interpretations, all of which are empirically equivalent that we choose between philosophically. Think about strategies for doing quantum mechanics. So the first strategy is the way of modification, which is a research program to change quantum mechanics, which we've discussed. The second, which I haven't really talked about, and would be another talk, you might call the way of the lab, which is the ways of making sense of quantum mechanics, cubism being a modern example, for instance, the Copenhagen interpretation being a classic one, that tries to make sense of quantum mechanics in a process where the prepare the system, let it evolve measure of it is primary, is central. And the third is the way of decoherence. How do we make sense of quantum mechanics as in practice it's used? As a unitary theory, as a situation where we dilate to larger Hilbert spaces to handle external systems like measurement devices, as a setup where the quantum classical transition is a paradigmatically dynamical and not conceptual transition. And those three ways are not just different things philosophers might think, they're different ways of approaching quantum mechanics. The problems with the first approach are first and foremost technical. The problems with the middle approach are a kind of mixture of technical and conceptual, and the problems with the third approach are philosophical. And my kind of emollient ecumenical thing to leave people with is the idea that I think all of these are highly motivated ways of approaching quantum mechanics. And the highly non-emollient partisan thing I'll leave you with is that the full version of shut up and calculate is really shut up and keep using the Everett interpretation to calculate. Thank you.
Thanks a lot for the talk. And in general terms, I agree with the claim that, at least for realistic interpretations, the Everett one is the only one that is satisfying all these requirements. But let's say that I have an objection about what this tells us.
Sure.
Because the Everett interpretation is just building on 100 years of work by physicists who are just using essentially Copenhagen interpretation and unitary quantum mechanics to derive quantum field theory and BCS and so on and so forth, where essentially we don't care about the measurement problem at all. And the Everett interpretation is just building, let's say, some metaphysical explanation of why we don't have to care for the measurement problem. And this is why everything is so successful. First of all, historically, because, I don't know, 1,000, like there is an order of 3 orders of magnitude of the numbers of physicists who worked at the theory, I think, to develop this, while how many, with respect to Bohmian mechanics or collapse theories. And the other point is that the real difficult part is to describe, as you said, is to describe the measurement problem in quantum field theory. And for instance, if we consider the approach à la von Neumann to describe the measurement problem, which is essentially based on the Everett interpretation, let's say in the fully unitary description of the dynamics,
Yeah.
that is fully successful in non-relativistic quantum mechanics, but at the same time, it's extremely difficult to use it in relativistic quantum mechanics. So when we want to try to describe the measurement process, even in the Everett approach, so fully unitary approach, in quantum field theory, we get essentially the same issues we get for all the other descriptions, meaning Bohmian and so on. It's essentially for all the reasons you pointed out, like the importance of the position. So in this sense, I think it's not fully fair to claim that the Everett interpretation is superior in this sense. At least, at least it's superior. Like it's just that the measurement problem cannot be described in quantum field theory so far. It's not like the Everett interpretation per se. At least that's
Okay,
my
good.
point. Thanks a lot.
So there's quite a lot to engage with there. Let me just pick a couple of strands of it. So firstly, look, I absolutely agree that the work here is mostly being done just by the development of quantum mechanics. I regard that as a plus. I don't think, per se, if you like, the Everett interpretation is superior to the rivals. I think unitary quantum theory is superior to the rivals, and that's why we should be trying to make sense of unitary quantum theory rather than trying to change it. I don't entirely agree that the development of physics over the last 100 years is a development that's really just been exploring the Copenhagen interpretation. I mean, this would be another talk, but I think quite a lot of the evolution of how we've understood quantum mechanics has been a sort of move from the primacy of the way of the lab, which is sort of how von Neumann formulates things, how Dirac formulates things, very much how the Copenhagen school formulated things, to the way of decoherence. It's been a move away from the sort of essentialness of the classical description and the conceptual need of a classical underpinning that's really central to Bohr, to the gradual development through decoherence theory, through open systems theory, through the consistent histories program, of ways of just modeling the process of interaction with macroscopic matter in a larger scale. So that's, and I think that approach is one in which Everett's ideas personally and the ideas of people who are explicitly motivated by Everett actually play quite a substantial role. So there's very, I don't want to suggest that explicitly many-worlds ideas are the main component in the story that took us to the decoherence framework, but they're not irrelevant to it either. In Zay, for instance, is explicitly motivated by Everettian ideas. The other thing I'd say about how you formulate the measurement problem in QFT, well, as with many things, it depends what you think the measurement problem is. I think the problems you're bringing up are more problems with the normal way we put the measurement problem than with the actual problem itself. I think if you look at quantum field theory, I think you see the same interpretative issues we see in non-relativistic quantum mechanics, which is to say we have a kind of inchoate back and forth between treating the quantum state as physically describing goings-on. Paolo talked about some of this, describing the quantum state as describing physical structures that interact with each other, and treating the quantum state purely probabilistically. So how do we get answers out of quantum field theory? We end up in a regime in which we treat the quantum state as giving probabilities, even though it couldn't have been giving probabilities microscopically. And I think that's something we can understand through decoherence theory, and we can make sense of that understanding through the Everett interpretation. But it would be a much longer account to fill in the details of that. Perhaps we could talk offline.
Thank you very much for a very interesting talk. So my question is that when we apply quantum theory to cosmology and to the early universe, I think all of those problems become even more severe, right? So like to interpret the fluctuations in CMB and so on. And I wanted to ask if you think there is underdetermination there for like the quantum problem on the cosmological scale, because as I understand, you think that the Everett is the only basically solution for the cosmological scale of the like quantum theory application. Yeah, thanks.
Yeah, I mean, I could have given there's a whole different talk I could have given about interpreting quantum cosmology, which would, funnily enough, have the same conclusion. The way I put it is that the trichotomy I put here is quite useful for that. The way we do quantum cosmology it can't be done in the way of modification because the theories we're using are relativistic field theories. It also can't be done in the way of the lab because the cosmological context is not a context where the sort of prepare, evolve, discretely measure really makes sense. It's a context where we have a sort of gradual flow of quantum superpositions into sort of classical probability mixtures. I think the actual way we do cosmology and the way one makes sense of it when one looks in the detail is basically way of decoherence. It's considering the whole thing as unitary, and at the point at which the variables that we care about are not interfering with each other, we interpret those variables probabilistically. So the claim I think is sort of scientifically very strong. It's at least right at the moment. There's no underdetermination about formal ways of doing cosmology. It's way of decoherence all the way, baby. Whether in my view, that kind of unitary decoherence-based way of thinking about quantum mechanics, Everett is the only really satisfactory way of understanding it. But I'm less bothered about that claim than the prior claim that what we need is unitary quantum mechanics with decoherence and emergent classicality as the way to do it.
Okay, thank you.
Let's have one more short question from there.
Yeah, thank you very much for the nice talk. I have a short question that connects on both, I think. So basically, you're saying that if you go the way of the coherence, you have only philosophical issues. But for both, formulating the measurement problem and to apply the coherence to cosmology, you need a tensor product structure in your QFT, basically, which is known to be a very hard technical problem because you don't have tensor product in QFT. You have type 3 algebras and blah, blah, blah. So how is that not a technical issue in this case?
Yeah.
Thank you.
Okay, nice question. So the first thing I should say, I mean, when I say the problems are philosophical, I should be a bit more careful. I mean, a huge amount of the problem here are actually the application of the decoherence machinery and things internal to physics. So I suppose the more careful thing I should say is that the problems are either philosophical or they just merge into the general normal science research program of doing the quantum classical transition. As far as tensor product is concerned, though, I mean, let me disagree on two sort of technical sides. So firstly, I don't think the tensor product is conceptually central to understanding decoherence. It's important in a lot of our actual models, but what matters in decoherence is I have certain degrees of freedom that firstly obey autonomous dynamical equations, and secondly, those autonomous equations have the mathematical form of approximately stochastic equations. One very powerful way of doing that is to take a tensor product split and find stochastic dynamics for the degrees of freedom of a large system interacting with an environment of much smaller things. But it's not the only way, and I think we have, the machinery of non-equilibrium statistical mechanics is all about ways in which we do a scale separation and identify collective degrees of freedom whose evolution, which effectively obey dissipative, decoherent, irreversible equations mediated by the dissipative and fluctuative effects of the small-scale degrees of freedom, and those are not required to take the form of a tensor product decomposition. And the last quick thing I'd say is that I'm, in accordance with the other ways I'm talking about quantum field theory, the way I think about quantum field theories is they're effective field theories regularized by cutoffs. And those theories have perfectly well-defined tensor product structure. Some of the concerns you might have about that probably replicate, because if you try to disentangle states with respect to that tensor product, you'll get cutoff level energies. But at least at the conceptual scale, I haven't got any problem with that decomposition. I'm perfectly happy to say that I've got a tensor product between the degrees of freedom on this side of a line and the degrees of freedom on that side of a line.
Right. Let's thank Thank you.
Welcome to this afternoon session, which we will start right again. And we have first speaker, Vikram Attali, who is a physicist from Cummings College, Pune, India. And he works on foundations of physics, cooperating with experimentalists. Please, welcome.
Thank you. So thank you, Paavo, for giving me this opportunity to have this talk. And Also, thank you for having this talk immediately after lunch, because usually audience is agreeable after lunch. So I'm happy to know that. Actually, my talk is divided into 4 parts, I would say, 4 proposals of inquiry. The first one is the proposal of physics itself as reality. We can interpret physics as reality if we consider it as a universal, all-inclusive set of processes. The other proposal has to do with different quantum interpretations. I think they could be seen as complementing and cooperating with each other rather than they are rivals of each other. The third proposal of inquiry is going to be, I will discuss some components of a generic quantum process. What do the models and experimental setups imply? And the last one is, how about combining Born interpretation with Copenhagen, with pilot wave ideas, so that we can have a more nuanced, I would say, understanding of the reality of a stochastic process. So, the fourth part is going to be an application of what I'm trying to say here. So I begin with the first part, which is where I'm going to discuss physics as reality. I would like to bring your attention to some of the Feynman's remarks and Bohm's ideas. Everybody's familiar with the Feynman Lectures on Physics book. And in volume 1, chapter 3, Feynman says, physics is the most fundamental and all-inclusive of the sciences and has had a profound effect on all scientific development. In fact, physics is the present-day equivalent of what used to be called natural philosophy, from which most of our modern sciences arose. So already Feynman is referring to physics as not only most fundamental, but also all-inclusive. Let us look at what Bohm said in his metaphysical account of process philosophy. It is taken from Physics and the Ultimate Significance of Time. He says, with reference to Whitehead's notion of reality, he says that he's proposing that the notion of reality as process be extended to include even our own metaphysical notions about process itself. This brings us to a higher level of consistency in which what we say and what we are actively doing as we say it are coming into closer harmony. Otherwise, we are caught up in the inconsistency of saying that all is in a process in which everything changes except for our basic ideas on process itself. So I think both these, Feynman and Bohm, both these people are saying something, according to me, very deep. It is not just said, it has rather very deep implications when we pursue for universal consistency of understanding physics. I think let me take you from these remarks of Feynman and Bohm's ideas to etymology of physics. So if we combine Feynman's remarks and Bohm's ideas with the etymology of physics, I think I can say what I'm trying to say here. So etymology of physics, the term physics originates from the ancient terms such as physica or physica, respectively Latin and Greek, which means natural things, or even physis, which means nature. So I don't see any limitation of physics when we interpret physics in this way. If it is going to be natural things, if it is going to mean natural things or nature, practically, according to me, it includes everything. And by everything, it is like our thought processes, what we wish to do, what we do not wish to do, what is happening elsewhere in other galaxies, everywhere in the universe. If I also connect it with Feynman as physics as universal or all-inclusive set of happenings in reality, and what Bohm said, reality as a processes including our own metaphysical notions about processes as well. If I combine these 3 things, then I think for mutual consistency, whether it is logical or philosophical or otherwise, I would like to say that physics can itself be interpreted as the all-inclusive reality of all the processes. Now, from this part, I would like to take you to the issue of interpretation of quantum theory. And one of the central problems there is the observer-observed borderline. So I'm saying at the bottom of the slide that, okay, physics, if it is all-inclusive reality, then it must include both the observer and the observed as parts of the reality. But where is the borderline when it comes to modeling reality at the quantum level. Now, I'm going to present a few interpretations. Already since morning, we have been hearing about them from various speakers. There will be some overlap, but nevertheless, it will be useful for my further discussions. So I'm saying different quantum interpretations, not as rivals, but indeed they can be seen as complementing and cooperating with each other. Let us see how. So let's begin with the problem of observer-observed borderline as discussed by Bohr, Heisenberg, von Neumann, and Wigner. So, okay, when we talk about Copenhagen interpretation, usually people refer to the dialogues, series of dialogues between Bohr and Heisenberg. I would like to include in Copenhagen interpretation also what von Neumann said and what Wigner said. So we can term it like a Copenhagen plus interpretation. Bohr said that it is essential to have a distinction between observed and the measuring instrument. This is the only way one can functionally make sense of a measurement. Heisenberg's point of view was related with wave function collapse. He said that it is an objective physical process, although it couldn't be further analyzed due to its indeterministic nature. Von Neumann focused on the measurement process itself, and he modeled the object instrument entangled state as it is collapsing to a determinate state. He also mentioned about sort of distinction between, he said that we need to distinguish between the observed, the apparatus, and the observer. And if we are discussing the borderline, where is the borderline issue? Then he proposed two options. He said you can combine the observed and the apparatus together as one system, and then you can try to distinguish it from the observer. Or you can have observed as a separate entity and apparatus and observer coming together as a separate system. So, and Wigner had a very interesting point of view. He said that what causes a collapse of the wave function is the mind of the conscious observer. So these are the main actors of the movie who talked about Copenhagen interpretation, or you can say Copenhagen plus interpretation. We can revisit this problem of observed borderline with reference to Schrödinger's notion of the subject of cognizance as well. In his book, or rather those are lectures actually originally given, in What is Life with Mind and Matter, Schrödinger says that without being aware of it and without being rigorously systematic about it, we exclude the subject of cognizance from the domain of nature that we endeavor to understand. We step with our own person back into the part of an onlooker who does not belong to the world, which by this very procedure becomes an objective world. So I think this notion, the subject of cognizance notion, is also very important in handling the measurement problem. And what we can say is collapse. If I add what Schrödinger is saying to what Copenhagen is said, then collapse is a physical process, though its detailed causality is unknown yet. This is what I feel. It could be understood superficially because the causal details are not available. It could be understood superficially as the concomitant actualization of both one of the definite object instrument states and one of the definite cognizance states of the subject of cognizance. Now, if we expand the Copenhagen interpretation using Schrödinger's notion of subject of cognizance, we can go ahead. We can say that this way, the systems participating in the process of collapse and their initial states are, I would like to propose, we have a subject of cognizance in some arbitrary state, we have instrument in arbitrary state, and we also have object in superposition. Actually, what I'm trying to extend is, I'm trying to extend the von Neumann notion of measurement-like interaction, which I'm doing in the next slide. So this is going to be a proposal for the extension of such an interaction with the inclusion of subject of cognizance. So pure von Neumann measurement-like interaction is written in terms of the states of the object and the instrument. So the initially separable state, which is a superposition of some basis states for the system and apparatus state in arbitrary state, it evolves to an entangled state. So you will notice that after that evolution to an entangled state, even that phi for the apparatus, capital Phi for the apparatus, has a suffix n. So the apparatus is sensing the system state in that n-dependent manner. One can extend this measurement-like interaction by including subject of cognizance and propose that the initially separable state is not just that of the object and instrument, but it is object and instrument and subject of cognizance, and evolving to the entangled state in a similar way. So I am also adding that ket Sn to that superposition. The measurement outcome would then correspond to any of these n states quantifying as the actualized or the collapsed determinate state. So basically, I'm trying to say that the process of collapse is very much an epistemological element of quantum theory. And what I'm trying to say here is actualization is meaningless without any reference to the subject of cognizance's awareness, or without SOC as one of the participating systems. Then this is all about Copenhagen plus interpretation, including what Schrödinger tried to say. We can move to Born interpretation. Born interpretation, I would say it hinted at the connection between causality and probability. There is a very deep statement made by Born in his original 1927 paper on quantum mechanics of collision processes. The motion of the particle follows the laws of probability, but the probability itself propagates in accord with causal laws. So we already know the Born rule. We have the Schrödinger equation, and the psi of the Schrödinger equation is interpreted as probability amplitude. I'm just showing a very simple collision process where we have an incoming particle with psi in state, and we have several outgoing options. So we have a probability distribution for the outgoing states, and the probability amplitude psi is a solution to the Schrödinger equation. The Born rule is the corresponding probability density is proportional to the mod psi square. Now, actually, there is an extension of Born interpretation as well. In fact, if we combine it with what Einstein tried to say and what Ballantine published in 1970, so this is what I'm proposing as the Born plus interpretation, which is the so-called ensemble interpretation. Psi does not apply to an individual system, for example, a single particle. It is an abstract statistical quantity that only applies to an ensemble of similarly prepared systems. So this is a statement from Reviews of Modern Physics paper by Ballantine. It is called a statistical interpretation of quantum mechanics. So, okay, Copenhagen plus, the Born plus interpretation. Moving on to the next, we have the de Broglie-Bohm pilot wave, which is also causal ontological interpretation, proposed by de Broglie 1927 Solvay conference, extended by David Bohm, substantially extended, I would say, which has a formulation involving not just Schrödinger equation, but also guiding equation. I'm just quickly going through these things. Everybody is, I think, familiar. We have Schrödinger equation for n particles. We have guiding equation, from which we derive trajectories for the Bohm n particles. And the guiding equation has psi present. So basically, psi is deciding the trajectories indirectly, and that is decided through the so-called quantum potential, which I'm just calling many-body quantum potential energy, Q, which is derived from the amplitude of psi if you express psi in polar form. People also talk about force acting on the particle. A force, if we follow Newtonian physics, then that is just simply minus del V. We have minus del V plus Q. The Q is coming as quantum potential energy. So basically, as people say, quantum theory of motion of n point-like particles with definite positions in Euclidean 3 space at all times. This is what the formulation assumes. And also, the wave function psi, it generates a momentum vector field, del IS, for all the particles, guiding their motion along causally determined trajectories. Now, okay. So with this background, okay, we already discussed quickly some of the interpretation, leading interpretations. Let us think from an experimental situation point of view, actors that make the reality of a generic quantum process. I think we have subject of cognizance there, we have observer, which is apparatus, we have observed system, plus its local environment. So this is what I'm proposing. We have a way, I'm trying to depict it in a very simple manner. We have at a central thing, we have observer and observed system, and we have the interaction, apparatus system interaction. Observed system, for example, if we just have a, this is very abstract, but if we just have something in mind, like a nuclear magnetic resonance experiment, then we have an experimentalist who is putting some sample in test tube in magnetic field. So the nuclear spins are interacting with the magnetic field, which is local environment for those particles. So there is an influence of local environment, which is the V term in Schrodinger equation. And I'm also talking about observer or the apparatus influence on subject of cognizance. Thereby, the subject of cognizance is becoming aware of what's happening. Now, below this, if you consider the extreme right-hand side, just below this upper diagram, I'm talking about interaction, which is unitary, reversible, and isolated. And Schrodinger equation, Schrodinger evolution works fairly well, no problem. You write Hamiltonian for interaction between system and environment. It's a Schrodinger closed system evolution, regular. If you want to talk about measurement-like interaction between apparatus and system, you can go for Lindbladian-like evolution for density matrix, to be more precise, reduced density matrix, as we heard in the morning. So we have all these models. So basically what I'm trying to say is, if we have all these Hamiltonians, we can just notice the absence of the Hamiltonian between subject of cognizance and apparatus. Of course, it's a very difficult and challenging task, but this is just to complete the picture. This is what is not there, but somehow subject of cognizance is playing a role. Let us see how. Okay. So with reference to my previous slide, I'm proposing that a generic quantum process could be expressed in terms of preparation, evolution, detection, and reduction as sub-processes. So actually preparation, evolution, detection, this PED sub-process set is already there, discussed by Escher Perez in his beautiful book, Quantum Theory, Concepts and Methods. And using Schrodinger's notion of subject of cognizance, we can extend it to reduction sub-process as well. So basically we have state preparation, then, okay, the prepared state, due to some Hamiltonian, it evolves. So there is state evolution part. And suppose we are talking about something as observed on screen, then it is state detection. And suppose we are observing intensity distribution on screen, and the subject of cognizance is looking at a particular value of intensity, and there is an actualization of that state. So there is a reduction. SOC is aware of certain intensity value for a certain state. So this is the picture which we can try to draw. It actually involves cause, which is coming between state preparation and state evolution. State evolution will lead to chance, which is there on screen, which is reflected on screen, because the chance will take you to probability distribution, which is translated as intensity distribution on screen. So between cause and chance, we have potentialities. Between chance and collapse, we have two things going on: object instrument entangled state, and then actualization. So possibly I'm trying to say that a generic quantum process, if we interpret it in terms of PEDR sub-processes, then we can also understand the cause chance collapse picture together by including subject of cognizance. Let me apply it to stochastic process. Just to give you a very quick idea, stochastic process involves a time-varying sequence of particle positions, x at t1, x at t2, x at tn. So at a very simple model, we can talk about the process like this. With these elements, they are considered as actualized at the discrete time instants, t1, t2, tn. So they are actualized. And if it's a Markov process, then it satisfies an interesting condition. The probability that x at tn plus 1 happens, given that all the previous values have been actualized, is just equal to p, probability for x tn plus 1, given that x tn occurred. So it is only conditioned. So actualization of a state at tn plus 1 is conditioned on the one actualized at tn. That's it. That is a Markovian process. So, okay, this is stochastic process. Now the question is, okay, can we apply multiple interpretations to really make sense of the stochastic process fully. So let us see how. So this is the last part actually, where I'm going to combine the Born plus, Copenhagen plus, and pilot wave ideas, which I discussed. And this is what I feel. I think this is going to give us a more nuanced understanding of the reality of a stochastic process. Now, this actually, I would say this part is going to be also a speculation from for unscrambling the quantum omelette of epistemological and ontological elements. I think some of you already know what Jeans said in Probability in Quantum Theory paper. Let us go ahead. So quickly speaking, we have de Broglie pilot wave interpretation, which I am putting in the cause basket. We have the Born plus or ensemble interpretation, which I'm putting in the chance basket. And the third basket is the Copenhagen plus interpretation, which is the collapse. So these are the key takeaways. I'm not going to read it again, but just to move further. So this is stochastic process which we discussed. Now, could such a Markov stochastic processes be understood as an interplay between cause, chance, and collapse? We have three tasks. We have to compute the conditional probability. We have to understand the corresponding probability distribution. And can we also develop a possible causal picture of the reality underlying such a stochastic process? So this is what we propose. We propose a double slit model for understanding the underlying reality of a stochastic process. It is possible. So what I'm trying to say is the proposal it goes like this. Stochastic processes can be modeled in terms of the PEDR subprocesses with the stochastic outcomes forming a sequence of R processes. So I'm claiming that in the stochastic process, the actualized values are nothing but they are the reduction processes driven by subject of cognizance's interventions. So if we consider the Tn and Tn plus 1 instants, what's happening in between, if we ask, one of the models could be Tn is the source, Tn plus 1 is the subject of cognizance, and we have a double slit-like situation here, preparation, evolution, detection, reduction. So basically, if we have a series of electron to slit interference-like situations, if we use a combo of de Broglie, Bohm, Born plus Copenhagen plus interpretations, and actually what we did is, in our recent work, we used not just a free particle Schrodinger equation, we used minus kx as the potential energy, and what we obtained was, so we can have the SOC points, you can see those are shown as the stochastic actualized instants or actualized values. We have evolution model in terms of standard Schrodinger wave equation. We have de Broglie Bohm interpretation coming through Bohmian trajectories, which I'm going to show. We have Born plus interpretation coming through Born rule for an ensemble. And we have Copenhagen interpretation where collapse is assumed as the concomitant actualization of the most probable system screen states and one of the definite cognizance states of the subject of cognizance. So this is what we obtained actually for the stochastic process. Because of the different values of potential, especially the k parameter, what happens is, depending on the k value, the trajectories bend downward or upward, depending on the sign of k, more precisely. And the expectation value of all these distributions follow Ehrenfest theorem. And so basically, what I'm trying to interpret is the most probable state, if we take as the one which is for which subject of cognizance is aware, then those are the values which we observe as actualized values. And the corresponding probability distributions also I'm showing. You can see for your reference, I'm actually showing 0 of the initial position by 0, I mean by a blue circle, so that you can see that in the upper block we have that dot shifted downward, we have a PDF shifted downward, we have dot shifted upward in the second one, we have PDF shifted upward. So the PDFs and SOC's interaction is basically talking about the stochastic appearance of those values. So finally, to summarize, what I'm trying to say in this talk is physics is the all-inclusive reality, anything and everything happening, essentially a physical process, possibly a perspective with a blend of physicalism, but as a metaphysical doctrine, and reductionism strictly as a methodological approach. And again, I'm saying, pardon my philosophical naivete, I am not a philosopher of physics, I'm a physicist. So my knowledge of philosophy is highly limited here. Different interpretations of quantum theory complement rather than compete with each other. This is what I would say. I think in the last talk, one of my colleagues, he said that, okay, nobody really cares about the measurement problem. And indeed it's true. When experimentalists and theoreticians come together and work, probably they have a very mixed interpretations, of reality. I think many words interpretation can also be brought on board by extending the notion of ensemble of similarly prepared systems to include subject of cognizance. This could be an interesting extension, I would feel. A consistent, though superficial picture of the reality of quantum processes, it is not just preparation, evolution, and detection sub-processes, but also the inclusion of SOC. So the components are observed, plus observer, and SOC. And if I just try to classify what I'm trying to say for stochastic processes in terms of epistemology and ontology, I would say epistemology, stochastic outcomes, just like the outcomes of any experiment, are tied up with, according to me, subject of cognizance's interventions. SOC is not there, nothing is stochastic. Ontology, transition from the previous to the next of the seemingly stochastic outcomes could be explained causally by assuming and appropriately modeling the underlying process ontology that includes subject of cognizance. And that's it. Thank you very much.
Thank you for this very interesting talk. And now we have 5 minutes for questions. Are there any comments or anyone wanting to say something? Now you have opportunity for that.
This is the advantage of post-lunch sessions.
Okay, here, Maria-Liisa.
Yeah, thank you. There was so many very interesting things. But then I think the sort of your final conclusion that you want to sort of claim for a sort of monistic view of reality, I think that's totally unnecessary. So why should you reduce social reality to physical reality? There's on such different levels of things. So perhaps you didn't mean that, or did you?
No. Actually, what I mean to say is, it is more. I would say I don't know about monism, but I think I'm trying to follow here more like a physicalism, because suppose if I try to prove by contradiction that social reality, let us keep it aside from physical reality, then I suddenly have a causal link broken. So for example, there is a lightning in the sky, and I'm looking at the sky and I'm getting scared by that lightning, and because of my scared posture, I'm just breaking a glass and it falls down on the ground. So there is a lightning in the sky which can be explained by physics. There is a broken glass falling from, say, a teapot, that can be explained by physics. But I getting scared is not physics. I don't understand how it is not so. So there is a break of causality.
There's one question.
Must SOC be conscious in the sense that, let's say you can have a subject of cognizance which is not conscious, but is able to record measurements, then actually use them, utilize them, a bit like Zurich's machine.
Actually,
it doesn't have to be conscious.
Actually, you're right. So, but what I would like to say is, if we, for example, in an extreme possibility, somebody will say that SOC is just an AI system. So SOC is not a conscious system. Still, it has to be operated by some conscious system, ultimately. You are ignoring that some conscious being is operating that.
Okay, and you can learn more about this on a monograph he has written, coming from Cambridge. It is related to physics and economic sciences, so you can learn.
Yeah, right.
And now we thank you for this presentation.
Thank you very much. Thank you.
And the next speaker will be Maria-Liisa Kakkuri-Knuuttila from Finland. And she has worked with Aristotle's philosophy of science and David Bohm's methodology of quantum mechanics.
Thank you.
So, good afternoon, everybody. So, this will be a presentation in philosophy of science. And okei, kiitos. Ja sitten mä painan, ootas mä sitä.
Tuolla menee eteenpäin ja vasemmalla taaksepäin.
Joo, kiitos. Joo. Okay. And this is meant to be a contribution to the fairly recent neo-Aristotelian approach to philosophy of science. And, well, technique is always a little bit complicated. And my interest in the question of energy as the basis of a unified theory of physics rises because of the Finnish innovation by Tuomo Suntola of such unified theory where energy is sort of the basic concept instead of force. The structure of my presentation, first some methodological remarks, and then the Aristotelian genus-species structure, and then Aristotelian metaphysics of motion and change, and then we come to DU and see how the Aristotelian conception of physics is a very strong element in the dynamic universe theory. Today, we can say there are two approaches to unification. One is based on the notion of force as the sort of starting point for building mathematical equations. And that means that force is a postulated quantity and energy is a derived quantity. In DU, energy is the postulated quantity, force a derived quantity. And it's a good reason to think about the philosophy of science in DU in Aristotelian terms, because it actually has been the aim in creating the theory to combine metaphysics and empirical observations of various physical theories. So perhaps we already got some evidence that DU is a promising candidate for a unified theory of physics in Tarja's presentation. And the point is that it allows explaining observational results of quantum mechanics, cosmology, electromagnetic theory, and also of relativistic phenomena as consequences of conservation of energy by supposing universal time and distance. So my main question here, are there any rational, that is, any philosophical reasons why energy should be a good basis for a unified theory of physics? Clearly, mathematics is not sufficient to solve theoretical conflicts between theory of relativity and quantum mechanics, for instance, so philosophical reflection is needed. There are two main approaches to sort of philosophy of science today, and one is the empiricism, and one is the Aristotelian one. And we have had kind of mixtures of these both two already. So in empiricism, the epistemology is defined as so that scientific observations form the basis of knowledge. And an extreme version is that, for instance, time is what is measured by atom clocks. And this may lead to some problems, as will become clear perhaps later. And in empiricism, there is no place for metaphysics. That actually follows from the strict empiricist postulate. But yet, atomistic ontology follows by the empirist supposition, because we are sort of supposing that the observations are independent of each other. The nomothetic ideal means that the form of scientific knowledge is universal statements or probabilistic statements. And from the first three postulates, it follows that causality is no more than a regularity between concomitant events. So there is no deeper connection between cause and effect. And mathematics is the ideal language of science. Perhaps we had some evidence of this already today. And now there was, Vikram was suggesting some kind of methodology which would fit for all sciences. Now he was excluding then social sciences. So anyway, testing regularities by observations. I have these 5 points, similar points for the Aristotle's view, and now this epistemology. I'm taking this genuine Aristotelian view that common knowledge, which includes observations, but of course at that time there was no concept of scientific observation. So of course that's one area which has to be sort of predefined. But the important thing is that theoretical thinking is also part of this knowledge basis. So it's a wide knowledge base. So it's actually, if you have a problem, then all knowledge which is relevant to that problem should be discussed. So actually it's a very good starting point for a unified theory of physics, because there you have to take all the theories with their observations and interpretations of the observations. And metaphysics is crucial. And it reveals categories of motion and chains, which lead to causality. And the ones we're going to discuss just next is the dynamis, substance, matter, form. And third, the metaphysics of the natural kinds is important. So genus, species, classifications, that is between sciences and within sciences. And instead of mathematics, Aristotle has the syllogistic logic. So genus belongs to species, species belongs to subspecies, so genus belongs to the subspecies. So it's a different axiomatic system. And for methodology, there are various methods for exposing explanatory principles. And one which Aristotle's method is called saving the appearances, which means building synthetical theories. So perhaps in the next conference we shall hear about that. So the neo-Aristotelian approach to physics is a kind of lively area of philosophy today. And for instance, Heisenberg already referred to Aristotle and took up the notion of prime matter, for instance, and which is quite interesting sort of epistemically, because Aristotle has metaphysical sort of arguments for the existence of prime matter, but then it suddenly becomes a physical concept as well. So my main question, now we can specify it, does neo-Aristotelian conception of physics reveal rational or philosophical reasons for energy being a better basis for a unified theory of physics than force? And then, of course, it follows what Aristotelian views need modification. So we begin with the genus-species structure of sciences. First of all, it forms the grounds of division between sciences. And here we see a nice realist sort of methodology. So reality and sciences both divide into sort of natural kinds, genus-species structures. So I took an example from Aristotle. The first principles as causes of motion and change, if they are relevant to all reality, this is metaphysics. If they are relevant to nature, that is physics. If they are relevant to objects close to the stars, that belongs to meteorology. And of course, in contemporary physics, we also have within the science these genus-species structures. In Aristotle, his Nicomachean Ethics is the sort of most complete work, and it is written nicely if you take a closer look at that in the genus-species structure. So Aristotelian metaphysics of motion and change. Next, I'll demonstrate to you how you can teach your students Aristotle's metaphysics of motion and change in 2 minutes. You just need some nice demonstrative device. I have chosen one. I got one of these as presents for my Mother's Day, and then I sort of had to Google how to make them myself. So actually, we have had these both notions here. Perhaps you didn't pay attention to them enough, perhaps not so much as I did, because I have been working for quite a while to sort of understand what these notions are about. So, I guess you all are familiar with these beautiful things. The word for Finnish is lennokki. And so, this is one lennokki. It has the, if you know what they are like, it has the capacity to fly a few meters if somebody flows it in the air. But now, as you can see, this capacity is not exercise. But let's see. Guys. So now the capacity was exercised, and luckily I have another one. So, but what was needed is needed a sort of active agent. Valdi isn't. Oh, wow. This is not a playground, April. So there has to be sort of two complementary sort of things. One is more active and one is the receptive. So I was doing the work, and this was sort of able to sort of receive my work, sort of take it in. And one more thing I want to point out here is that in Greek, there is just this one word, dynamis. But depending on the context, it needs to be translated in different ways. Sometimes it's potentiality, sometimes it's possibility, sometimes it's power. Power is the term which is used by philosophers to discuss the metaphysics of causation. But in the context of physics, I have been told it's not a good translation, because in physics, power has quite a different meaning. But it also means ability, capacity, capability. So I think it shows beautifully that one Greek term can capture so many different sort of contextual meanings, and quite likely they all have some kind of sort of same metaphysical basis. This likes to do some tricks. I think it's trying to imitate you, April, playing a little with us. Okay, thanks. So this is how Aristotle begins his work in physics. And he argues against the Parmenidean view that there is no motion. And he explains that, well, there are two different kinds of motion and change. So this is also a lennokki, as you can see. It has the same substance as the one that's sort of been flying here around. But if I forgot my pen. How terrible. Teachers are very bad at demonstrations. So if I did draw here something, oh yes, it has to be a real demonstration. So if I draw here a heart, let's say, does it change its substance? Does it change its identity as a lennokki? I would say no. I guess you agree. So this is an attribute which doesn't change its identity. So there are changes like that. But then what happens if I... Do we still have a lennokki? No, no, no. But what we have, we still have the paper. We still have the matter. So there are two kinds of changes. One's where the substance changes, one's where the substance remains the same. And this is also relevant to DU. So, johtuuko siitä, että mä painan tuon takaa?
Varmaan pitää painaa tuosta sitä.
Okay. Now, if somebody had matches, we could show that this paper still can change its form. So there's also some form here and matter. So matter and form, they build up in hierarchies. And if there's a hierarchy, there must be some lowest level. And this is what Heisenberg was talking about, this prime matter, which is the lowest level of matter. And it has actually very funny characteristics. It has no form, therefore it's unchangeable, but it's substrate of all reality and change, and does not exist by itself. It's poor potentiality. It has the potentiality to receive forms of different kinds, and it's actual only in combination with some form. And now this is my last Aristotle points. It's also very relevant to DU. The kinds of priority. There's this ontological order of things, and substance for Aristotle is prior to attributes. There has to be a substance before there can be any attributes. And then this is an area I have been working quite a lot. What this epistemic order, that is, we start our research from something what is familiar to us. This is relevant to Paavo's presentation, which he made today. And then we come to the scientific results, which Aristotle calls, it's familiar in nature, it's familiar absolutely, and so on and so on. And then we come back to what we had to start with, and we can see how to correct them. We'll hear more examples of that in connection with BU tomorrow, I believe. So now, how can we say that energy is the basic concept in DU? Actually, mass is the genus proxima in DU and not energy. So that's an important connection there. As for ontological priority, mass is the prime substance, so it has to be some kind of prime matter plus the gravitational potential field. And as Tarja spoke earlier this day, particles are resonators, so kind of mass wave systems. And then material objects, they are combinations of resonators. So we end up with some Aristotelian, very clear, strong Aristotelian elements in DU as a sort of a conception of what physics is about. So mass is a prime substance. It's the genus proxima. It sort of distinguishes physics from other areas of study. It's the most abstract being, and mass, measured in kilograms, is the substance for the expression of energy, which is measured in joules. And that is the first explanatory principle in DU. It explains physical motion and change in terms of the dynamis metaphysics. Mass is an active dynamis. It generates the gravitation potential over the whole rest of space. And it's also a receptive dynamis. It senses the gravitation potential of the mass of the rest of space as gravitation energy. And conservation of energy is expressed as actualization of potentiality. So potential energy is converts to kinetic energy, and this again to potential energy and so on. Thus we can say what we started with, which is sort of prior, energy or force. And now it seems that in DU, energy is ontologically and epistemically prior to force. And we have built some kind of Aristotelian background to understand how this comes. But DU differs from Aristotelian ontology by being a sort of a holistic theory. It's a holistic theory both ontologically and epistemically. So this is a slide that I have borrowed from Tuomo Suntola, and it describes the system of nested energy frames, and it shows, in addition to showing this holism principle, it shows how the ontological priority and epistemic priority go together. So we start with, from up there, is the hypothetical homogeneous space and local group, Milky Way, solar system, Earth, and we here. So, and on the right side, there is the epistemic priority. We move from the simple to more and more complex in a very, very beautiful iterative manner. So up there is the rest energy, M0, Z0, 2, and this M0, Z0, 2 becomes as a factor on the second level. And the second level, the right side, becomes a factor on the third level, and so on and so on. So the formulas become more complicated at each step. And now my conclusions. So we can say that in a lot of respects, DU accords with the Aristotelian conception of physics. It offers first principles to explain physical motion and change, and physics is specified by its genus proxima, which is mass, as a substance of expressing energy, and this functions as an explanatory first principle. And physical motion and change is explained in terms of dynamism, substance and attribute, matter and form, and energy is ontologically and epistemically prior to force. But this doesn't mean that there is no place for modifying the ancient Aristotelian metaphysics, even though there is a grasp of something relevant which seemed to work very nicely with our Lennokki. But we still need to modify the metaphysical notions of dynamism and substance and attributes and matter and form. So one reason for the modification is the holistic approach adopted in DU. So this is my presentation. Thank you.
Yes, thank you, Marja-Liisa. And we still have 5 minutes to discuss.
Thank you. I wonder if you could say a little bit more about why you think, for instance, string theory prioritizes the notion of force, or perhaps what force means in that context. I mean, naively, force is a classical notion. It doesn't show up in quantum theories, and string theory is a quantum theory. So I suspect you mean something slightly different by that, but I'm interested what you do mean.
Yeah, that's a very good question, and I must say that that being a philosopher, I'm not able to give you a satisfactory answer. So I wonder if any of the physicists here would like to respond to your question. That's a very important one. Thank you for posing that. Gabion.
Yes, thank you. Well, perhaps as time has changed, physicists have wanted a notion of causality, which is spelled out in some other way than using this notion of potentiality and actuality. And so 2,000 years after that, they came up with, I don't know, concept of causality in possible world semantics or possible world Salah Lewis, and then with the framework of this. That also is metaphysically quite heavy in a sense. And then finally, we have a notion of causality nowadays, well, finally, where you can measure, you see, well, you have equation and they tell you how much, if there is a change in some values and how much the otherwise value. So don't you think that this kind of progress, I mean, has been important, and why should we stick to the older notion of causality? In the same way as mathematicians didn't stick to the Kantian notion, obviously, of geometry as a form of our intuition, but they had to come up with to overcome that in a way.
Yeah, so you're asking why I'm interested in this dynamis conception.
Why do we have to stick to the Aristotelian notion of causality defined in terms which are somehow obscure, I mean, potentiality and actuality?
Well, now I think you should sort of argue for the claim that they are obscure terms, because they are very widely used in philosophy of science in just discussing causality for quite a long time, and now they have also been adopted in the so-called neo-Aristotelian approach to physics. And at least in two presentations today, Vikram was using this potentiality actuality quite a few times, and I think they are just inevitable in our understanding about what motion and change are. But I'm glad you are working here in Helsinki so we can continue this discussion and have a real good debate, Gabi.
Thank you. And a very short one question we could take if someone has. If not, we thank Maria-Liisa once more and continue. Or is there? Did you see?
No, this is. So thank you very much. Thank you.
And our next speaker is Petri Lievonen, who is a researcher from here, Finland. He collaborates in this Paavost project that organized this conference, and his topic will be visual introduction of Clifford algebras and spherical geometries towards unification proposals by Suntola.
All right, thank you very much. My name is Petri Lievonen. I promised to speak a little bit about Clifford algebras, visual introduction to Clifford algebras, and we will stay there for a while, then go to spherical geometries, especially the three-sphere, and then in the end, we'll go towards the unification proposals by Suntola. So we will start quite clean, and then we'll go more and more towards the research material that is going on right now. So I have first some meta-reflections on philosophy of physics, so nourishing the innovation pool. Ideas are really important. There's path dependence, always. There's network effects are really important. Institutional inertia is, I think, necessary. We want the institutions to stay stable. And division of labor is really important, and we need the specialists, and we need the specialists to collaborate. It's a difficult problem. Freedom of science, rigor and elegance, and curiosity in the large and in detail, and long-term thinking. So that's where those were my starting points. So we start towards Clifford algebras and geometrical algebras by looking at the greatest theorem of the antiquity, the Pythagorean theorem, a squared plus b squared is c squared. So everybody has sometimes tried to add those scalars like vectors, and it doesn't work. You get the cross term there, so you have to avoid that trap. But now, when you are being stricter about possible non-commutative products, this is for physicists, this is like you have done this for decades, but there are now in the audience, there are many people who find it really weird that by making the direction of expression here, how you write and how you read these products, you actually can encode the geometry in the formulas. And this is like the starting point for Clifford algebras, because then you get this cross term here, and now it has to be 0 for this Pythagorean theorem to hold. So you can actually define that this AB must be minus BA, so that this term disappears. So A and B must anti-commute to be orthogonal. And this is something that should be taught in elementary schools, I think. Because it's so easy, and I'm wondering what the greatest minds of antiquity, like Pythagoras himself, even though it's not named, carries the name, but not necessarily the idea, what they would have thought about these things. So to be more strict, you actually have to move these to vectors. So there's a unit vector with length, and you have to disappear the unit vector. So actually, you have to define that the unit vectors square to 1. And this is one of the starting points for Clifford algebra. And now you are in a really nice place where you can actually use like vector algebra plus like some things together, but actually the Pythagorean theorem holds. And now we can use these. And this is a nice introduction, or not. I can't say introduction because Karet Sobczuk has studied these for decades. So he has these new foundations for mathematics, a geometric concept of number, where you extend the numbers with direction. It's a really powerful idea. And also Matrix Gateway to Geometric Algebra, Spacetime and Spinors. It's a really advanced work, and there's I guess many physicists would benefit or would get new ideas from that, because there's these stereographic projections which might give new interpretations to quantum mechanics. But I'm not going to go to the wave formulations, because even Sobczuk, even though he goes to really advanced like Atiyah-Singer index theorems and others, he still calls quantum mechanics like magic of quantum mechanics. There's also Clifford algebras and spinors by Pertti Lounesto and geometric algebra for physicists that I really recommend. So now we can build these Clifford algebras or geometric algebras by starting from some scalars, which are non-directional numbers. We define vectors, directional line elements, so that they square to 1. And then we define these orthogonal, these Clifford relations, anti-commutative relations. And now, according to the previous slide, these are orthogonal. You don't need to see the visuality. And when you start interacting these together, you easily get to pi vectors, or this kind of, this is a shorthand, E1 times E2, and then eventually to trivectors. And now you are in closed algebra, so you can't get out of this. If you multiply these together, they start to collapse on each other. And this is a highly symmetric representation of like three-dimensional space, because there's points, there's vectors, and then there's three planes, and then the directional volume element. There's also these mysterious elements called idempotents, which stay themselves if you multiply them together, and they annihilate each other, and they sum to unity. But now why I got here is because now with these Clifford algebras, you can easily generate generate more dimensions. For example, you can take the extra E0 and you start multiplying them together, so you get really nicely looking view of the four-dimensional space. So there's 3 extra bivectors which are related, for example, in relativity to boosts, and then there are 3 volume elements, and then the hypervolume element or pseudoscalar of the algebra. And these are the generating elements, and in both of these there are subalgebras. For example, here there's quaternions. This is a pseudoscalar. It squares to -1. It commutes with all these, so it commutes with everything. So actually it works as an imaginary element, this algebra. You can exponentiate it. It starts to oscillate between 1 and E12 and such. And there's also these really wonderful idempotents, which are like in between scalars and these hypervolumes. And Sobchuk uses these. But now why I wanted also to show this, because there's another possibility known in Clifford algebra community, where you take actually these 4 elements as your generating elements of the algebra, because these all anticommute, and these are square to -1, and it's usually used. The notation is either the G or the Clifford algebra. And then I guess Basil Haile will talk about these more advanced concepts where you have, for example, 4x4 matrices with complex numbers, and then you get Dirac matrices and something. These are equivalent to polymatrix, polyalgebra. And now I will go this really quickly. If you turn these and get to parallel, you can use scalar mathematics. And now again, if you use non-commutativity, this has to be 2BA. And so AB and BA implies that these must commute so that these vectors are parallel. It's a wonderful structure where there's anti-commutation means orthogonality, and this commutation means parallel. And then you can make these symmetric and antisymmetric products and using exponential function. I also wanted to show, because pedagogical ideas are so important, using exponential function, you can easily group the even terms and then the odd terms, and you can just try what happens if you use unipotent there. You get these hyperbolic geometries, Euclidean geometries with these, I call them imaginary elements. Null potents give this kind of parabolic geometries, and then idempotents, perhaps these, I'm not sure, because you need to interpret these differently. And now this Garrett extends the real number line with null potents A and B, and it actually has this kind of a matrix representation. And now the algebra and matrix representations, they are almost equivalent. You can just calculate with these. It's really amazing that this is like a closure, because now there's these F, E, and EF. They are anticommutative, and you can actually complexify this geometric algebra and get to polymatrices, because this is the first polymatrix. This multiplied by E is the second, and this is the third. And you can even add or continue this by making even larger matrices, so you can extend the Clifford algebras. But now the main thing here is that we should more think about these like really simple algebras and four-dimensional algebras, for example. So as some motivation example, hyperspherical harmonics are really useful. And Avery, for example, has said in his preface, In an extremely brilliant early paper, the Russian physicist V. Fock showed that the Schrödinger equation for hydrogen-like atoms in reciprocal space, which is like momentum space, can be solved by means of a 4-dimensional hyperspherical harmonics. To obtain these solutions, he projected 3-dimensional momentum space onto the surface of a 4-dimensional unit sphere. And this 4-dimensional unit sphere just means that you have a 4-dimensional background space where you have a constrained surface. And my question is that because this is so fundamental, should we take more into account these 4-dimensional background spaces? Of course, these are then generalized to higher and higher dimensions. So is it that somehow the fundamentalness of 4 dimensions is then lost? Then the hyperspheres. So hypersphere is simplest is the circle, or yes, circle, let's say so. And you constrain the radius in a 2-dimensional space, and you get these spherical coordinates. So there's just one coordinate you can go around. And then the sphere, S2, is you have the 3-dimensional background space where you make one constraint. So it's a sphere where you have 2 degrees of freedom, and you can see them from the spherical coordinates. And now the 3-sphere, it's a 4-dimensional background space where there's a constraint of the points lying at the same hyperradius from the origin. And it's a 3-dimensional space. So it's a 3-dimensional space. And this is actually a really, really fundamental, and we should discuss it a bit more. For example, here the lecture notes on general relativity by Sean Carroll. It's old but known. And there's the Robertson-Walker metric. There are different curvatures. And the closed one, we can define that metric, which is the metric of a 3-sphere. In this case, the only possible global structure is actually the 3-sphere. It, of course, needs interpretation. What is meant? Because the 3-sphere is an absolute known object, but how do you interpret the metric there? But it's a known and important thing. Also, the 3-sphere is important in Poincare conjecture, for example, that every 3-dimensional topological manifold which is closed, connected, and has a trivial fundamental group is homeomorphic to the 3-dimensional sphere. And here it's also the 3-sphere. You also always need to go to the mathematics. But it's such a simple and important object that it needs to be studied. So here's a really, really nice property. This is the maximal number of linearly independent, smooth, nowhere zero vector fields on these kind of odd spheres. So the first is 1. So this circle, you can comb the hair once in one direction, and it's okay. For 2 spheres, you can't comb it. So if it's hair, it's the usual example. You can comb it once, like with a great circle, but at some point you hit into singularity where you need to vanish the vector field. You can't comb it. But the 3-dimensional or the 3-sphere is special in a sense that there's 3 maximally independent, smooth, nowhere zero vector fields. And this is a wonderful property. And I got introduced into this years ago in applied mathematics in optimization theory. But now in Suntola studies, I started to think if the universe would be a 3-sphere, what would this theorem look like? So it would actually, this says so that if we imagine that the universe is closed, we stop the time and don't think about speed of lights or anything, just the structure of the space. Then we could start combing the space into one direction, and we would come from the other direction back. And then if we would move a meter and we would comb, we would come back. And we would continue that, we would come from there, actually, and we would comb. And everything, whole universe would be combed into one way. And then the other way, we can start combing another color, for example, to orthogonal direction. And we would go there, and then eventually we would come there back. And again, we could move a little bit and comb, and we would comb the whole universe. like orthogonally in one direction. And now there's two like these kind of hairs together. And now the third dimension also, we could start combing upwards. And we would come down from bottom here, and we would move, and there, and the whole universe would be combed. And this is what it means. It is really wonderful property, because it's such a fundamental thing. Because if you think about the three-dimensional space, then you don't have so many options here. So of course, octonions and these, they use these higher, for example, 7. So then you have then you have much more structure. But that I wanted to communicate, because it's such a powerful picture, maybe even too powerful picture. And I recommend Stellarium, free open source planetarium, to look and watch, think about this thing, because it's so wonderful thing. Okay, but now the second part of my talk. So I will talk about my collaboration with Suuntola, and then some research work that we are doing. So simplicity, virtues and vices. Simplicity brings clarity and non-obscurity. Transparency, you can create thick layers with simplicity. It facilitates knowledge transfer and aggregation of understanding. It's pedagogy. It's reduction of complexity, but also it's sort of a reduction in life works. It's exclusion of alternatives, which is good when there's incorrect things, but it's also really resistant to change then, because it's so simple. It offers shortcuts for experts, for poetic minds, also the ignorant. We all are ignorant in some sense. It encourages enthusiasm, optimism, but it increases odds of accidental correlations. So simple models can lead to fantastical surface detail coincidences, really like, because, for example, power series, if you remove the extra elements, you get really easy correlations. So I recommend, for example, knowing our limits, or Ballantyne's other book, Reason, Bias, and Inquiry. And I want to manage expectations. So there's this known knowns, reflective mind and habitual mind, that we are not known, that we know. And then we expert and literatures try to understand the uncertainty and know where to go. But then there's this unknown unknowns, which is sort of wise to acknowledge, but it also makes you really, really anxious, because you don't know what are you missing. And so I have read the Tuomas books, Dynamic Universe, and the Short History of Science, and I have this is like 300 pages for like 1,000 equations, and I have verified most of them. So I have looked for internal consistency and then the external correspondence, and it's a really, really difficult thing, because they are so difficult vocabulary. But now let's go really, really quickly to things that we have that are there. So usually you have this horizon problem. You are at the center, and you see the cosmic microwave background, for example. Now utilizing these multidimensional objects, you can use the three sphere as this kind of iconic, really mathematical, elegant structure, where actually you think that the universe is expanding in this hyperspheric fashion, and the light travels these kind of logarithmic spirals, because it's exactly the light speed is here defined as the hypersphere velocity, and also the tangential velocity is the same. So it creates these kind of wonderful structures. And now in this three sphere, you can always find the geodesic between 2 points. So you can always reduce it to these kind of pictures. And now even you can make the redshift, because you can think that along the expansion, also the waves for some reason expand in the direct proportion to the rest of the space. So then you get these really beautiful equations, where you have the E, which is like the wonderful function to the theta. So this theta here, it actually is E potency E to the theta is this R observation divided by R emission, and also so you can actually get to the redshift, this kind of like deterministic formula, and you can very easily get the optical distance d, because in the same time frame
that the hypersphere, the radius expands, the same distance is also this tangential distance by definition. So of course, you can check in the literature that it actually you get the same redshift relation than in modern cosmology by that kind of like geometric construction. So then you can generalize it to multidimensional settings. So here's the like the smaller universe that emits some emitter emits light, and it starts to the light follows these kind of beautiful geodesics. And then if the emitter stays at the same place, it's now currently there. But this is like, even if this is somehow unphysical because there's this absolute base, but in mathematical sense, it's a really beautiful structure. And there's these light cones sort of, which are twirling in this logarithmic fashion then. This is also, of course, just a projection. So of course we had to try it and with newest data. So here's the supernova observations. There's the redshift and the magnitude, and this is like a really new data. So they helpfully provide the light curve photometry and the redshifts. So here's the supernova spectral template where there's the spectrum and then the epoch day, and here's the highest when the supernova is highest. Then we model it so that this is the spectral template. So when the redshift increases to 1, so the universe doubles, we assume that the wavelength just doubles. And then also to conserve the energy, we assume that the energy density halves. So then you get this relation to the energy density. And then in addition, you just use the d, the optical distance, in an inverse squared manner, because it's like in a three-dimensional space, because if you are looking at the tangential space. So then this is the actual, the prediction, what kind of energy density you would need. So then you try it with data. So there's a 2000 type 1A supernova, brightest observation selected among all filters. So this is the envelope curve. Let's zoom in. So this is the envelope curve. And these observations need to be below that envelope curve, because I want it to be as simple as possible. So usually the light curves go through really difficult processing. So I just took all the data and I took the maximum flux density that there is, because then if there's there's, for example, not measurement from the top, then you get just too little density. So it actually follows really nicely these different surveys. But there's a really big problem, and Suntola warned me about this, because actually I have needed to help the standard model, because if you plot the standard model, it goes too less. And there's this called, Suntola proposes that there's this K correction that is involved, and that K correction is in the magnitude data where the cosmological model is fitted. But then when you just deterministically convert from the magnitude data to this actual calibrated flux density, then it goes too low. And you can also see it so that now it fits so nicely to the model, but then if you go to the actual magnitude, then it stays too low. And so this is like the actual data in magnitude. So longer or upper is like a dimmer, and you have to like convert the data with this 1/z square correction to get to fit to data that is actually fitted here. So it's a really strange thing, and this is quite common, I guess, in physics, that
that you don't actually, the pipelines are quite difficult and you don't know what is the measurement and what is the processing problem and what is what. And this is really preliminary, but it seems that the DU model fits really, really well. And it has no parameters, or there's like the Hubble constant and these kind of parameters, but it's like fits really well. And this is like almost like too big thing for me, because these are like $1 million projects. so we are looking into it. And you can see the distance measures in cosmology or the K correction. Okay, now really quickly, we have 5 minutes. So Suntola proposes that there's also the dynamics involved. So in Pascal Jordan studied this zero energy balance. So Suntola just takes the equation and thinks that the C is the parameter. So you just solve the R from here. So you get this deterministic equation for the scale factor. And it's then the same scale factor that is in matter-dominated universe in current cosmological models. Because here it's just the proportional factor, but here it's T times 2.3. And then you can, of course, get this C, the speed of light or the speed of this hypersphere expansion. And you can very easily then calculate the angular frequency of the light in this tangential space, and you get the Hubble relation, and it's the same as in standard model. And then you get in these redshift relations, you get this time thing. And now this is just to show that we have tried, or Suntola has derived this Newtonian gravity and S3 inside, so you integrate throughout whole of cosmos in this sense. So I tried to do the same in 3-sphere fashion, and I got the same result than Tuomo. So it's like the basic thing is that Tuomo thinks that when you integrate throughout the whole of space this kind of Newtonian gravitational potential, you actually get the Newtonian gravitational potential towards the hypersphere center, even though it's not there, but it's look like virtually there due to this construction. And this is, of course, this is a varying speed of light, and this modified gravity theory. There's a bounce theory, and this is one way now to conceptualize this. Is this Okun's cube of physical theories, where you have Planck constant, then you have 1 per c is the light speed, and gravitational constant is here. So Dirac proposed that gravitational constant varies. Now Suntola supposes or proposes that the Planck constant has speed of light as a factor, and this changes in cosmological timescales. And it's an interesting research question to think what happens in early universe, for example, in this really hypothetical model, when the speed of light would have been, like enormous. And then for the special relativity, it's a very difficult position, because here in Suntola model, the C changes according to time and place. And then as a solution, sort of, Suntola extends this cube with 4th dimension, which is actually the scale of the universe. And that might give some new ideas, because usually these don't feel the scale, because it's like a Lorentz invariant. You can't feel the universe evolution, but Suntola proposes to add it. All right, but I guess I'll leave it here, because I have lots of material. I guess I'll leave it here, because this is let's see. I have here. Let's see. Here I have this. I'll leave it here, because this is an important thing to discuss. If you go to, for example, Uzan's fundamental constants and their variation, you get the formula for the cesium atomic clock, and also the magnesium atomic clock. And the speed of light is a factor there. And if nothing else has speed of light, as Suntola has proposed, that if you modify that Rydberg constant properly, the speed of light is not there, then it's, at least algebraically, it's like locally invariant. So you always measure the speed of light the same. But this might be because the sea is in so many places, and it's like a common thing. But this is something to think about. And Suntola proposes that the sea varies by gravitational potential, and then the Compton wavelength, which is in this Rydberg constant, it varies by velocity in these energy frames.
Okay, thank you.
Thank you.
Petri.
And it's a great pleasure to introduce Professor Basil Hiley from University College London. Basil would have liked to very much be here, but unfortunately this time he couldn't make it. But we worked out to have this Zoom, and hopefully even you will be able to ask questions afterwards. But without further ado, let's welcome Basil.
Thank you very much, Paavo, and thank you very much for inviting me. And I'm sorry I had to pull out from actually being there. But an operation on my eye forbids me from traveling for the minute. I didn't realize it would take so long to actually settle down. I would like to talk, first of all, let me say I'm very happy with some of the talks that I've been listening to. I would have liked to have interjected, but it's not possible from this end. But I liked Petri's talk in particular, convincing everybody there that what I'm going to talk about is quite trivial mathematics. I will try to make the mathematics I'm going to talk about as intuitive as possible. You don't have to know the details, you just have to know the general patterns of how the details fit in. As you know, I wrote a book, The Undivided Universe, with David Bohm. And when we finished it, unfortunately, before we finished it even, David passed on. And so I left it exactly as it was. But I was never happy about the relativistic attempt that we'd made in the book. And during the COVID lockdown, one of the advantages, the only advantage, was that I was able to do a lot of reading. And three particular one book, two papers that I read, changed my perspective on what we'd written in The Undivided Universe. One paper was by one book rather was by Rudolf Haag, which was called, what is it called now? Local Quantum Physics, Fields, Particles and Algebras. The other was a remarkable paper by Bryce DeWitt, which was published in exactly the same year as David Bohm's Hidden Variable paper, 1952, and I had never heard it referenced anywhere in the literature. And I want to put that right. And then I also was in Paris last year, and I met Michael Berry, and he introduced me to a paper which was very important in the story I'm going to tell. Now, just let me remind you that when I started out on my academic career, I had a great privilege to sit in and listen to seminars in which David Bohm and Roger Penrose had many discussions, and particularly the question of how to quantize gravity. At the time, Roger was very much developing his twistor program, and the twistors are semi-spinners of the conformal Clifford algebra. But this discussion actually raised my interest. What are these Clifford algebras, and why did someone who invented this algebra before quantum mechanics came along, how could he invent an algebra which many of the features that we see in quantum mechanics appearing there, particularly when we look at the Schrödinger equation, Pauli equation, Dirac equations, and so on. Now, unfortunately, Clifford died when he was very young, and he was actually at University College London, and I had the advantage of being at Birkbeck, just across the road from University College, and I used to go and sit in their library dungeons and actually read some of his original papers, and they were quite fascinating, actually, and they enabled me to see exactly how Penrose's twisters fitted into the work he did. Now, I'm very glad that Petri has given a very nice introduction to Clifford algebras. I want to take this a little bit further. Now, as I said before, the undivided universe, which I penned with David Bohm just before he passed on, we introduced the idea of a quantum potential. Now, we were accused by Heisenberg of actually importing an idea from outside of quantum mechanics. Can I assure you that that is not correct? The quantum potential appears immediately from the Schrödinger equation when you polar decompose the wave function. And as I said, in the undivided universe, we made rather a poor attempt to bring in relativity. What I learnt at the Paris trip was de Broglie had made an early attempt to include the Dirac equation in 1960, and again, it didn't work. And it was when I was in Austin, Texas, that I met David Hestenes for the first time, a great expert on geometric algebras, and he suggested that a successful attempt to extend the quantum potential to the Dirac equation could be made through geometric algebras. Inspired by that, I joined Robert Callaghan, and we obtained expressions for the quantum potential for the Dirac equation. Unfortunately, David Bohm had already passed on, and he had always found it difficult to understand how we would put the Dirac in there, and I wish he'd been around to see what we had actually done. Now I want to go to the DeWitt paper, and this, I say, if you look at it, the reference is 1952, PhysRev 85, and the Bohm hidden variable paper, I haven't got it here, was PhysRev 85, 1952, and it was an earlier pages, it's in the fourth issue, in the second issue, whereas DeWitt had this in the fourth issue, and he had a term in there, and he showed that if the principle of general covariance was to hold, the quantum Hamiltonian must include some extra term, and it turned out that this extra term was related to the scalar curvature in differential geometry terms. Now, how on earth, what is this connection? Here is this strange quantum potential, which nobody wants to talk about, although that was in the days when we first invented it, nobody, or introduced it, nobody wanted to talk about it. And then we find that, in fact, in the 60s, 57, no, in 57, DeWitt had already shown that it was the curvature. And then Berry introduced me to one of his papers in which he looks at the curvature of optical streamlines and looked at the Gaussian curvature in particular, and he found that the curvature contained this extra term, which was just the quantum potential. AR here is just the refractive index. So the curvature is the curvature at a point, which is the rate of change of the tangent vector along the streamlines. So here we've got something which is quantum mechanical and something which you could almost call classical, because these were classical optical streamlines using the Helmholtz equation. And then I found, with the help of Glenn Dennis, that we could go to a picture of quantum mechanics between the Schrödinger picture and the Heisenberg picture. And it's something that Dirac developed in his book, classic book, textbook on quantum mechanics. And what he showed was that if you go to the situation where you make the phase transformation and work with a real wave function, you find there that the amplitude of the wave function turns out to be, again, related to the curvature, exactly the relationship that DeWitt had got. And I want to talk a little bit about this. And I want to, in the present context, we were talking with Roger about quantizing gravity. And Penrose is now saying, no, what we should be doing is looking at a gravitization of quantum mechanics. Ugly word, gravitization. In other words, is there any geometrical aspects of quantum mechanics that we should be talking about? So I'm not going to talk about Hilbert space in this lecture at all. Okay, I thought you'd like to know about this DeWitt, so I've got this particular PhysRev picture here, and the introduction here is saying there is an isomorphism of the group of point transformations in classical mechanics and a certain subgroup of all unitary transformations in quantum mechanics. And it turns out that this group is the metaplectic group. And I thank Maurice de Gosson, a mathematician from Vienna, who has pointed this out, slowly taken me through to understand symplectic geometry, which is very important, and we seem to neglect it in the physics. And he says there is no ambiguity in ordering of non-commuting quantum operators. The method of constructing quantum analog is covariant under general coordinate transformations. And then what he goes, it's quite a long paper, and he actually shows that you really should have this extra term in here, and he actually called it the quantum potential energy. And here is lifted straight out of his paper. The quantity 8 bar squared Q may be regarded as a kind of quantum mechanical potential, which goes to 0 as H bar goes to 0. It is a quantity which, and listen to this, must be added to the covariant classical Hamiltonian in order to produce the covariant derivative. And then later on, he showed it. But what we also found when we were looking around for something was that this relationship here was discussed, and I can't quote definitely, but any one of these three, two of these three were discussing it. Feynman, Schwinger, and Wheeler's name was mentioned by Schulman, and they said, could we measure it? And they decided at that stage it was too small to measure. And so the whole thing disappears from the discussion. Subsequent discussion of the causal interpretation of the Bohm's theory of de Broglie-Bohm theory. Okay. Now I want to go back to a paper by Dyson in 1962 called The Threefold Way in a Journal of Mathematical Physics. And he says that what we should be aware of is that there are three associative division algebras over the reals. There are R, C, and H, and my story is going to be talking about these three algebras. H are the quaternions, which Petri has already talked about. Now we know R is in classical physics. We see C coming in quantum physics, and in Penrose's terms, the C for quantum mechanics is magic, and the H is rubbish. Now, I'm sort of paraphrasing him. I was in his flat when he actually told me that he thought this was not worth bothering about. Whereas what Dyson is claiming is that H quaternions are the magic and the C is rubbish. So let's have a look. What is the argument and what's going on between this H and C? And in this case, one thing I've got to emphasize, I'm not sure whether I've emphasized it, and that is that we're looking at the Clifford algebras over the reals. Now, you might say, well, surely we need a -1, something squared to -1. Well, yes, that's our ordinary imaginary number, I. But as Petri pointed out, in your Clifford algebra, the generators all square. They did originally in the original work of Clifford. They all squared to -1. So how do these Clifford algebras arise? Well, let's remember what Dirac did. Dirac said, oh, look, E squared minus B squared minus MC squared. I don't like square root of the energy because that's going to be plus or minus. So I want to linearize it so that the energy comes out to be always positive. And then he got the Clifford generators of the Clifford group, and he called them alpha matrices. They eventually become gamma matrices when we learn how to deal with them properly. And the Clifford algebras then quite generally have a series of generators which square to +1, series of generators that square to -1, and Petri showed there were ones that square to 0. I'm not going to talk about that here. That generalizes the idea. I want to talk about just the P and Q, the metric, the sign of the metric tensor, because that's where general relativity comes in. And what we normally do is we usually keep this fixed and never worry about what happens if we have a theory which actually the P's and Q's change. Right. So that's the task that I want to try to get across to you. Now, the rather remarkable thing about Clifford was that his algebras were generated because he wanted to describe the very small. Normally, we're told that Clifford gave us the clue of the curved space-time, the curvature of the universe. But no, he was arguing that the axioms of the Euclidean geometry may not be true in the very small, and if they're not true in the very small, how do I find a mathematics which will describe a non-Euclidean geometry? Okay, now to do that, Clifford invented a process-based algebra for classical physics. That is, you look at all the mathematics, even the numbers, as not as symbols, abstract symbols, but as processes. So if you want to multiply 2 by 3, you don't say it's number 2 multiplied by number 3 to get 6. You say you double 3 or you treble 2. And it's that idea of activity that he was basing the whole thing on. Now, what I found absolutely extraordinary was all the structures that are used in quantum mechanics actually came up in Clifford algebras. And to bring that out visually, I have taken the idea of Vaughan Jones, who actually had a tower of von Neumann algebras, which is, if you were real mathematicians, that's what you would be talking about. But I want to talk about Clifford algebras because it's a lot easier to see what's going on. And it's a lot more fun, as Petri has already pointed out. Well, if you turn the algebras starting with a point, just 0, 1, 0, 2, 3, 0, 3, 1, 3, 4, 1, 2, 4, you generate these metrics that actually we use in quantum physics. The Schrödinger equation is essentially here. We've just got the complex number. The Bohm theory is just here. The Pauli theory is there. That's the Dirac algebra. That's the de Sitter algebra. And that's the conformal algebra. And here are Penrose's twistors, which are a bit like a pair of Weyl spinners. So how does this come about? Oh, and now we generate this tower in a very simple way. We just simply start with one element, and then we tensor product it with the C11, and we take 2 steps up. It's always 2 steps up and 1 step back in this game. And so now, if we now look at the Clifford algebras in a different way, I'm now turning the tower the right way up. So I've got my real number sitting on the top here. I've got my complex number sitting here, and I've got this creature sitting here, which we won't worry about. Then I've got my quaternion sitting here, and I've got my R2. R2 means the matrices that represent that Clifford algebra are 2 by 2 real. Then we go up. This is the 2 by 2 with the complex numbers. This is 2 by 2 with the quaternions, and so on and so forth. Now, the interesting thing is that the tower finishes at 8. And that's because there's a deep theorem called the Bott periodicity theorem, which says that we get to 8 dimensions, and then 8 dimensions and above, everything repeats itself and repeats itself and repeats itself. So what I've done in my tower is I started from this matrix representing the complex number by a real matrix, because I want to do everything in terms of the reals so that we can see exactly what's going on with the complex number. Okay, now then, we've had the word wholeness, and I think Suntala's theory is depending very much on this notion of wholeness. And a very nice talk, by the way, from about Aristotle's work, who I was looking at when I first started out, by the way, and inspired my causality ideas were inspired by reading Aristotle. Now, suppose we want to generate the whole geometry. We're not generating particles, our whole geometry is moving. So let's start with a very simple geometry, the straight line. It's the simplest geometry we can have. And the order of succession means that the line moves, and any point on the line as it's moving along here is actually projected up here. So this is the proper time that we measure for the particle going between these 2 points. And here is how the Clifford algebra fits in. Here's our C01. And in this case, I've chosen minus ds squared because it makes life a little bit easier. Now then, let me use my formulae, which was tensor product, then 0, 1 with 1, 1. And I immediately get a metric, which is a 1, 2, that's 1 time, 2 space dimensions, Minkowski space-time. And what happens when we linearize this is that we find that we get x plus iy, which is a rotation in the anti-clockwise direction, and x minus iy is a rotation in the clockwise direction. And so we represent the element of the Clifford algebra as a 2 by 2 matrix, and that matrix can now be read as the time is going up here, and we have either a left-handed or a right-handed. I shouldn't have drawn those rays there at the moment, but you'll see why I did. Now, if we go and use the generator again, starting with the plane and generalizing by tensor producting, we find now we get 2 variables going up the plane, t plus z, t minus z, and we've got our usual X and Y. So here's the plane where we're living in, but we've now extended the dimensions to include Z and T in one go, because this is the way the formula does it. So if we take X squared, T squared minus Z squared, and write it as T plus Z, T minus Z, these are the Dirac light cone coordinates, and here is our rotations. So what we've done, in fact, is now constructed our vector, which is what Penrose calls its incidence relation, and we have now put into our Clifford algebra the Cartesian coordinates. But what this object is describing is in fact a light cone. The top half describes the forward light cone, the bottom half describes the past light cone. And it's the light cone coordinates that use the Quaternion algebra, and we can if we introduce an I, smuggle an I in here, we can represent them by Pauli matrices. Okay, one more step, and this stops the story, and the reason why it stops the story is because of the Bott periodicity. But now we can go from the Minkowski space into the conformal space, and it's in the conformal space that Penrose does all his work with the twisters. And what we have here is an extra parameter lambda, which we don't use normally in the Cartesian coordinate approach. Now, what is this? What is the new thing we've got with this picture? Because we've got an extra parameter in here, so we've got more structure. And what we find is that the Dirac spinors have got two Pauli spinors in them, whereas the twisters have got two Pauli spinors, but the opposite type. We pull together psi L and psi R and put them in one twister, and we've got the psi 2 and the R1 in the other twister. And what they're doing, and here is Penrose's relations between the twisters, he's now brought in X. He's brought in a way of finding the angular momentum of this light ray about this coordinate. So we've got here a tenfold parameter group, and this is the structure of it. And you now relate that the whole thing has to be coherent, so that as this light cone moves up there, it must match this light cone down here. And you see that is why here is the L1, R1, R2, L2. And when you get up to here to compare the two, you've got the L2, R2. You've got to make sure these match each other, and they match each other because of the structure of the twisters. Okay. Now, that's probably a bit much that you've got hold of. Let me try and do it again in a slightly different way. The quaternions. I want to see exactly how the quaternions fit in here. Here is the metric that we use, and here is the anti-commutation relation that Petri told us to expect, so that each element's anti-commute. Now then, what I want to show you is that you can look at the quaternions, and this is why I think the quaternions are more magical than the classical complex numbers, I'm sorry. And that is that the quaternions can be written as a four-dimensional object, real plus real 3, and this is your space-time, and this is your space, and this is your time in non-relativistic physics. But the quaternion can be split into two pairs of complex numbers, and we'll see what they mean. Here is one complex number, and here's the other complex number. Right, now then, but we can also choose a minus sign or a plus sign instead of a minus sign here. And then I get to my relativity, because when I put the C number on there, you'll see I get a complex, but here I've got a rotation space again. So I'm looking at this all in terms of R2. So the difference between the H and the R2 comes in just the tangent, and we'll see it's a tangent space in a minute. And this, so it's the split quaternions that gives us the minimal relativity, and I call it a mini relativity, which is two-dimensional space-time, three-dimensional, sorry, that should be a three-dimensional, shouldn't it? I've got two generators with three elements. So it's a three-dimensional space-time. And I get the chirality operators come in here and so on, for those who are interested. Now, what has this got to do with the physics and because this is all pretty cold mathematics, maybe. And to get it into perspective, I have to reproduce a couple of diagrams that a mathematician friend of mine, Ernst Bintz, drew on some hotel note paper while we were waiting for probably Paavo somewhere or other, and he drew on the note paper exactly what I should have been thinking about when I was doing my Clifford algebras. Think of this as a light source. So we've got the light rays, the light reaches the sphere. This is called the celestial sphere. So you let it go for a bit of time and the light rays reach this sphere. Now then, let's take one particular ray from that and put it perpendicular to the F, this tangent plane to the light sphere. So this is going to be where the electric and the magnetic field oscillate in Maxwell's equations for the light ray. Okay, remember it's right angles to the direction of travel. And so what we have in here is the light cone is coming out with this circle being the projection of the light, of a cone of light rays coming from the origin. Now this C is just looking at the perpendicular plane to this plane here, and this is the plane which has two vectors which we're going to play with. Okay, so what we want to see this intuitively is just a disk with a vector. So it's a three-vector object. And we're going to see that this is related to the moving frame. So if we want to discuss the dynamics of some energy moving, we've got a moving frame which we've built out of this activity. And here is Cartan's moving frame. And we're talking now not necessarily about particles, we're talking about energy flow lines. So this, like the dynamic universe, is actually taking energy as more basic than the force. But this is how, if you want to do it rigorously in the mathematics, this is the steps you have to make. Right. Now, Petri also mentioned stereographic projection. Well, this is one of the first papers I ever got published showing the stereographic projection in terms of a very simple model, which is the model. You see, I've got it here. Here's my spinning disk, if you like. Now, the spinning disk is embedded in that light sphere. And what I do is I take a projection from the North Pole through the point on the surface of the sphere to get Qn. So every rotation group, which requires 3 dimensions, can also be described in 2 dimensions, because this, as this point P moves around the sphere, so Q moves around the, oh, sorry, getting too excited. moves around the plane. And this is where, this was the Penrose vector that I talked about on the previous slides. And it's just a geometrical representation of this structure, of how we relate the three-dimensional structure to a two-dimensional rotation, and it's the quaternions. So this stereographic projection gives me the quaternions straight away. Now then, that we can get the V3, and the V3 is just, and I'm bringing in quantum notation here because you'll see that all I'm talking about are combinations of wave functions. I've got my vector is actually a combination of these, they're Pauli spinners actually. And I can just multiply them out. This is all standard mathematics. And I eventually end up with a vector, the X component, the Y component, the Z component. And remember, we have R plus R3. And this is just the Stokes vector. This is just classical physics. And question then is, what about the V1 and the V2? Well, I can then form a different matrix, which is formed in this way, which is, this is a dual that it makes it a little bit common. I won't go into the details of it here, but we get another, only in this case, we get another vector. This vector is complex, which if we write as V1 plus IV2, that is just the V1 and the V2 on that other diagram. And then we find that we can write the spinors as RE to the IS, RE to the IS. So I'm doing a polar decomposition, which is why I mentioned polar decomposition before. So what I'm doing actually is I've constructed Penrose is null flag, is spinner described as a null flag. And I just thought you don't have to know about this, but it's just rather interesting that this picture that I'm getting here is related to the flag picture, but Penrose has only got half the structure in it. The way I'm doing it, the way Binz told me to do it, is that you get an extra bit of structure in it. Okay. Now, what's this to do with quantum mechanics? And here we come to something which, again, Petri mentioned a few of the terms. But what one finds, and this is what one finds, is that all the information that we encode in the wave function is already in an element of the left ideal of the Clifford algebra. So you don't need a Hilbert space in order to do quantum mechanics if you come through the Clifford algebra approach. And I should just point out to the mathematicians, if anybody's listening, the Clifford algebras are of the type 2 von Neumann algebras. That's just for the people who would want to try and trip me up. Now, how do we do this? Well, we already, and David Bohm and I already published a paper showing exactly how this worked way back in 1983. Nobody took any notice of it. For example, the general wave function, the relativistic wave function, can be written in terms of a product of the idempotent times a function psi L, which is what I've been talking about. The psi L then can be written in terms of geometrical equivalence, because this is the scalar, this is the vector, this is the bivector, this is the trivector, and so on and so forth. So what we've done is we put geometry into the quantum formalism itself. Now let me show you in detail, because you probably don't believe a word I'm saying. The Schrödinger uses the quaternion Clifford. I had it. There's a disagreement. I've just realized with one of the earlier slides. Forget that. It's always tricky this to start it all off. And what we really should be doing is a simple Bohm model which uses the split quaternion and chooses 0, 1 as the basic. Then psi L equals this. And you've got your two, these are real numbers, these G's are real numbers, and I is the generator of the group, and I don't, like I shouldn't, I was being told not to put that equal to. Put an arrow there. Replacing E1 by I, you can't do it accurately because that's a vector and that's a pseudoscalar. Oh, sorry, that's a scalar. So they don't match geometrically. So that G0 is the sum, wave function, complex conjugate plus wave function, and G1 turns out to be I times wave function star minus wave function. Now, if we do the Pauli-Clifford, it comes from the Clifford algebra C3 in that tower, and here is the wave function, and here is the way you identify the wave function. You do the same for the Clifford, and you then see that instead of writing them as matrices, you can write them as elements of the Clifford algebra. Well, we're talking about the same thing. Okay, and if you go through the algebraic approach, you find that you get two equations of motion. One is the conservation of mass density, and the other is the conservation of energy. And these two together are equivalent to not only the Schrödinger equation, but they're equivalent to the Dirac, Pauli, and Schrödinger equations. And if you analyze them in the sense that DeWitt was suggesting, you actually find that you get a quantum potential for each algebra. And therefore, this quantum potential energy is something which is not just a fluke, it's actually an important integral part of the whole structure. So there's a new quality of energy that's involved in all of this. Now, does this give us any new insights? Well, I've been very lucky to find Peter van Rieth at University College, and he knows how to use computers. I'm afraid I'm an old gaffer who actually didn't grow up on computers, because when I started using computers, they actually took a whole building across the road from Birkbeck College. Yes, a whole building, whereas now we can do these things with our telephones. Incredible. Sorry, but that's the change that I have seen, and I have not kept up with it, unfortunately, because the youngsters seem to find this much easier than us old fuddy-duddies. So what can we see? What new features can we see out of this algebraic approach? Because I'm now using the Pauli-Clifford algebra to do these calculations. Sorry, I say I'm using, I really mean Peter is using it. And I want to look at a particular setup, which I think brings out some very interesting features. And that is a double Stern-Gerlach magnet. So these are infinitesimally thin Stern-Gerlach magnets, one there with its magnetic field making spins coming in the X direction, go into the Z direction, into the Z, yeah, and the minus Z direction. So it's a usual Stern-Gerlach where you separate off the spin up and spin down. And then we've got a second magnet here with its spin, with its magnetic field in the opposite direction. So that what comes out of will be spin down, hopefully. But look what you do. And this is just doing the differential equations that give us the Bohm trajectory. It's exactly the same. We're looking at the energy flow lines. And the energy flow lines now are not just the ordinary bending here. Notice there's nothing. There's no physical fields between this Stern-Gerlach magnet and this Stern-Gerlach magnet. Remember, we're theoreticians, so the magnetic field is confined exactly theoretically to that. But notice that this, and again, we don't have spins jumping into eigenstates. They slowly turn into eigenstates. But look at the other way. They're flowing in, they're pointing in the wrong direction. And that's what Marlin Scully said to me. No, these are surreal trajectories because the spins must come out. They must go straight through. See, because this is pointing up, this is pointing up. So the only way they can do is they go, no, they don't. They actually undergo this turning process, which comes out directly from the quantum potential calculations. So this is just using the mathematics without adding anything new to the Dirac equation or the Pauli. This is the Pauli equation. A Dirac equation can be done this way, and I'm sure there are people beavering away at it at the moment. But I don't think you'll learn that much more from it. So what is in between here? The quantum potential. And here is one quantum potential for the ordinary one Stern-Gerlach magnet. And this is for two Stern-Gerlach magnets. And they're very difficult to interpret, but it's interesting to have a look and see what. And then I got Peter to put it all on one slide. And so here is the quantum potential. So the reason why this is bending here is because there is this potential. And this is the energy, this is the reason. If you look at in terms of energies, you find that the energies actually give rise to a force. And these are and sometimes they were called the Coriolis forces, essentially, and they were called pseudo forces. Now, can we measure these? And this is what we were trying to do in the laboratory before lockdown occurred. And unfortunately, we were just getting into the position where we've actually got two-slit experiment, two-slit results for argon and for helium. We've just got the two slits for helium, and we may also have it for argon. I'm sorry, my memory's just gone blank for a minute. And therefore, what we were now trying to do is to say, can we actually do something on our machines to see if we could see this type of behavior coming out? Okay, so what happened was that Weidmann and Aronoff and Albert actually published a paper talking about weak values. And I had a look at what they were doing, and to my amazement, their weak values actually turned out to be my momentum plus a complex momentum. And I was wondering where this, we called it the osmotic momentum, how it was coming in to the picture here. The osmotic momentum was introduced by Nelson in his attempt to get a stochastic a derivation of the Schrödinger equation. He found he had to introduce an imaginary momentum. And Mike Berry has this momentum. He actually has a very nice paper talking about 5 momenta. But I don't think he's mentioned this momenta. Okay, so then what we've got here is, if we look at this V, of course, is just the grad S over M from the Bohm theory. I'm now going to the Bohm theory. And with VI is this thing here. And this is the osmotic momentum. It's to do with the amplitude. And if we look at the energy, kinetic energy, we find that here we've got the kinetic energy, here we've got this Q, and then we've got these 2 extra terms here. which can be accounted for. But notice there's no H bar in front of this. Forget those terms for the minute. Think of the DeWitt paper, and there was no H bar in there. But if we use the imaginary, this weak value, then we actually get an explanation of where the quantum potential comes from. So the amplitude is playing a very important role. And remember, the amplitude turned out, the quantum potential turned out to be related to the scalar curvature in the geometrical aspect. And so here,
got about, let's say, 9 minutes.
yeah, no, I'm just finishing. This is the last slide. Is that okay?
Yeah.
Yeah, and here we then were trying to, as I said, get back to the story of the experiment before COVID shut us down. We had designed and was carrying out an experiment in which we hoped we could measure some of these, or we could measure some of this behavior in the spin system. And unfortunately, instead of being able to triumphantly say we've succeeded, we had to spend our money because research students have to be paid even though they're not doing what they should be doing because the laboratory is locked up. We ran out of money, and we're trying to get some new money to actually complete this experiment and to show that there is extra effects coming from this particular way of looking at quantum theory. Thank you. Okay, Paavo?
Yeah, thank you. And we have some time for questions.
Yeah.
Put this mic on.
I can't hear the audience. I see you've got them switched off, have you?
But we are using a microphone, so let's see if there is.
Okay.
I'll give this to this. There we go. So let's see. Anybody?
I'm sorry, this is very different.
You wouldn't be surprised if I told you that I didn't understand every single equation. Let's have Utsi over there.
Sorry, who's talking?
Utsi Albrecht. You remember Utsi?
Yeah.
You know him.
Hi, Basil. Great talk. And
oh, yeah, right, yeah.
And I really enjoyed the way that you related Q to the curvature, to the scalar curvature, which I've never seen before. My question is not one of principle. I noticed that you were representing the I. The square root minus 1 is a 2x2 matrix with 1 minus 1 minus 1 1.
Yep.
But there are some papers that show that there are some things in quantum mechanics where you cannot make this move, where you can replace the complex numbers with real numbers.
Well, I would like to see that because, to be quite honest with you, it's only in the last 4 years that I've rethought the whole of the Bohm. You know, what I was doing with David Bohm.
Okay. The paper is about 2 years old. I can send it to you.
Yeah, okay, that's good. No, I'm saying I'm still hunting because there's so much literature out there now.
Okay. And it may not have anything to do with what you're saying. It's just that in some cases.
Well, this particular matrix has a very important role to play in symplectic geometry. And it's the key. And I have some papers which I didn't understand, which Ernst very kindly put my name on, in which now I understand them. They are very, very, very good papers. And they bring in the symplectic structure in a very interesting way, that we're looking really at the intersection between the unitary groups, the orthogonal groups and the symplectic group. And the overlap between those two are a unitary group. And we're exploiting that particular structure, the intersection between the symplectic and the orthogonal.
Okay, thanks again.
How far you can go with that, I don't know.
Yeah. Let me ask one question, because you had you had this one slide when you had different quantum potentials for the different algebras and
Yeah.
equations. So are those quantum potentials physically different? Do they operate in different ways, or do they depend on different things? And how would you describe that?
Well, they do different things, Paavo. I think the diagram is, pictures tell 1,000, stand for 1,000 words, and I'm no good at words. What we have here are the bone trajectories a la Philippides and Dewdney. Yep.
Yep.
So that would be the actual, that would be, where are we? That would be this quantum potential, okay? So now if we look at the Pauli, because that's what we're doing the calculations, we now have, what doesn't look as if this becomes this in the limit. It does. I can assure you, because I wouldn't be putting it up here unless I actually showed that this degenerates into the Schrödinger, and this degenerates into the Pauli, into the Schrödinger. So that's where this term comes from. But notice we've got a term here which is due to the spin. And there's an extra parameter in there. It's not an easy task to do this, Paavo.
Right.
But that's the extra term which is due to a spin turning. I tell you who had a brilliant, easier one to look at is Chris Dewdney and Vigier and Kyprianides in Nature. I think I've got it somewhere in my slides, the reference to it. But they show how that gives rise to a coupler, a twisting couple. And that twisting couple is what we've got calculated here. So we take the spin vector, and then it is coupled in the Clifford algebra, and it turns it into up. So Schrödinger was right. There are no quantum jumps in this way of looking at things. Okay, so in between here, you've got the quantum potential, which is that one that we had, where was it? This one here. Okay, so we're using that to actually calculate these trajectories here. And if we are right, then we will see something very different. And we've done all the calculations, and I think this is a few millimeters for the strength of the field that we're using in this experiment here. Okay, because can I go through? It'll take me a bit of time to go through that. I'm not the experimentalist. I just wanted to show you guys that there is an experimental consequence of what I've been talking about.
Okay, we have many concurrent talks to come. So Basil, we thank you very much and look forward to seeing you in the next Physics and Reality Conference here in person. Will be.
Okay, I hope
Excellent.
so. I hope my eye is actually my. Oh, forget it. I hope I'm better then.
Yeah, absolutely. Excellent. Thank you so much, Basil. Thanks.
Okay.
Our first talk is from Michael Silberstein and Mark Stuckey, although Mark will be here. Yeah, over to you.
Thank you. Thanks to the organizers for having me. We'll be briefly introducing how we have unified special relativity and quantum mechanics in principal fashion by adynamical global constraints. We have some published papers here with these co-authors, and we have a book coming out later this month with Oxford, where it's everything I'm going to present here is presented in detail. Please forgive me if I misspeak, mispronounce some words. I'm very jet-lagged. I always have trouble coming east. So let me get started. Maxwell unified the disparate concepts of the electric and magnetic fields with the theory of electromagnetism, And then Einstein unified the disparate theories of mechanics and electromagnetism with the kinematics of special relativity. And what I'm going to show you is how we can unify the disparate kinematics of quantum mechanics and special relativity with the relativity principle. All right, so let's go back. How did Einstein do his unification? In his own words, by and by, I despaired of the possibility of discovering the true laws by means of constructive efforts based on known facts. He turned to a principle account. We called principle explanation, according to which you have a fundamental principle justifying an empirically discovered fact that you use to derive the kinematics which constrain the dynamics. And so in this case, of course, we have the relativity principle justifying the empirically discovered fact. Light postulate, everybody measures the same value for the speed of light. That gives you Lorentz transformations, which constrain your dynamics. And today, we don't have any problem with that principle account of special relativity. We don't look for the ether theories anymore. We don't care. We're quite happy with this principle account. Here's from an intro physics textbook by Randall Knight, for example. This is quite the norm. So Ravelli said, you know what? We have a similar situation with quantum mechanics, right? We have a formalism, and we know how to use it, but we really don't understand it. Maybe instead of trying to interpret it, we should try to derive it like Einstein derived the Lorentz transformations from some sort of principles. And he suggested that we use information theoretic principles. And in 2001, Lucian Hardy was the first to successfully meet his challenge with this paper, Quantum Theory from Phi's Reasonable Axioms. And since that time, there have been many of these so-called axiomatic reconstructions of quantum mechanics based on information theoretic principles. Here's just a few in one of our papers that we cited. I'm going to talk about those that are derived from this empirically discovered fact, information invariance and continuity, from Bruckner and Zeilinger. The total information of one bit is invariant under a continuous change between different complete sets of mutually complementary measurements. Now, that doesn't really strike you as clear, unless you're in your quantum information theory, that doesn't probably strike you as clear as the light postulate, right? So let's move this into space-time and talk about an example. This is an example that they used in their paper. Talk about spin a half. So you have spin in the z hat direction, you get two results, up or down. You pick off the up results and send it to a b hat measurement, and you get up or down with respect to b hat, right? And that's what they're saying. It's that simple. You're talking about this b hat and its complementary measurements. Every frame, you always get two results, up and down. Same with the z hat frame. So it's invariant with respect to these rotations. All right, so Weinberg points out, hey, when you measure the spin of an electron, you're measuring Planck's constant h, right? So what can we put together here? The principle of information invariance and continuity entails the observer independence of Planck's constant h with respect to spatial rotations. Just like we have the observer independence of the speed of light c, right? But you can justify that with the relativity principle. This is our only contribution, except the narrative itself here. All the results I'm presenting are other people's results. So here's our great contribution. I'm going to justify this with the relativity principle. And there you go. I have the relativity principle justifying the empirically discovered fact, whence the Hilbert space kinematics of quantum mechanics. And I have the very same relativity principle justifying the empirically discovered fact, observer independence of speed of light c, whence the kinematics of Lorentz transformations for special relativity. Unification done. All right, let's look at some consequences. The classic constructive model for spin, you have your dipoles coming in, your Stern-Gerlach magnets being deflected in all possible directions. So we said that previous example, right? We have the spin up, angular momentum is up along z hat, and we measure it b hat, and we expect to get a projection of our spin and angular momentum in that direction, cosine theta, right? In units of h bar over 2. We expect to get cosine theta, but you can't get cosine theta. You can't get fractional values of h. You get +1 or -1. But +1 or -1 can average to cosine theta. That, with normalization, in fact, gives you your spin a half qubit probabilities. So you have the relativity principle justifying information invariance and continuity, which we call for short NPRF plus h, no preferred reference frame, plus Planck's constant. And you get from that for spin this average-only projection. So what does that mean? What's the consequence of that for your Bell states, or your entangled states for that? Well, you have your Alice and Bob making their measurements at a hat and b hat, just separated by theta. Your correlation functions for your singlet state would be minus cosine theta. And then for any of your triplet states in their symmetry plane, cosine theta. So now let's try to understand where does that come from, plus the joint probabilities. Let's see if we can derive those like we did the probabilities for our qubit, right? Spin a half. So Alice says, look, Bob, I know if you had measured it in the same direction as me, when I got +1, you get +1. I get -1, you get -1. But you measured off at this angle here, so you should be getting the projection of that spin angular momentum, right? And this to conserve, right, to conserve spin angular momentum, you should be getting the projection down here of plus or minus cosine theta. Of course, Bob says, no, I always get ±1, just like you do, right? All right, so she says, well, what if you average your results? If your results average to that, you immediately get your correlation function, and you have these two average-only conservation criteria, plus normalization here, and that gets your joint probabilities for your Bell states, right? Now, that was all from Alice's perspective. Of course, Bob can say, the hell, you're the one that should be getting plus or minus cosine theta, and of course, everything can be turned around and get the same joint probabilities. So what kind of explanation, what kind of a view of reality are we talking about here, right? We didn't mention, there's no mention here of causal mechanisms behind this average-only conservation for your entanglement. Well, you have these world tubes here for Alice and Bob's measurement devices, the world tube for the source, some Bell state. You have the settings, Alice setting randomly and independently of Bob's settings here, and then for each of the emission events, at least with respect to the Bell state, right? With quantum mechanics being as complete as possible, given NPRF plus H, there's no other thing you can tell about this story. This is the end of it right here. And all this is determined by these world tubes and their Minkowski spacetime. That's from your adynamical causal constraint, NPRF plus C, right? And now the Bell states, which come from the NPRF plus H causal adynamical constraint, then gives you your distribution of quantum outcomes in that spacetime context, right? All right, so the term that's been used for this, we started using it in 2008, and a bunch of people have picked on it since. All at once explanation. Evans, Liu, Price, and Wharton for retrocausality, Esfield and Gisson for Bell-Flash ontology, Hans, Hosenfelder, and Palmer have used it for superdeterminism, Adlam and Ravelli for relational quantum mechanics. So there are many other researchers, many other approaches to explaining Bell state entanglement in general, that invoke this kind of all-at-once kind of explanation. All right, so we had the relativity principle, justifying the empirically independence of observer independence of H, giving you your Hilbert space kinematics of quantum mechanics. As Stern and Gerlach rotated their magnets, they saw no change in deflection pattern of atoms. It also justifies the observer independence of the speed of light c, which gives you your Minkowski space kinematics for special relativity. As Michelson and Morley rotated their interferometer, they saw no change in the interference pattern of light. All right, so whose meter sticks are really shorter? So you have here these three events. You have three girls moving at 0.6 c relative to these two boys' frames. The girls and the boys agree on the facts contained in these events here. The time differences are exaggerated to make it interesting. The boys take the three events and partition them according to their surfaces of simultaneity in which they're the same age. And they can quite clearly discern that the girls' meter sticks are shorter, right? It's obvious from their measurements. The girls, on the other hand, can partition these events according to their surfaces of simultaneity in which they're the same age. And then their measurements show quite clearly that the boys' meter sticks are in fact shorter. So, whose meter sticks are shorter? What is the causal mechanism that's missing from special relativity to account for this length contraction? What do we say today? It's the wrong question. This is not a dynamical effect. This is a kinematical consequence, a kinematical fact that obtains because of NPRF plus C. It's not dynamical. There's no dynamical story that underwrites this. Most people aren't looking for it, although there are still some people doing the ether theories. But most people would say nobody's meter sticks are literally shortening. Likewise, let's go to our average-only conservation, according to which Alice takes this data. Again, Alice and Bob agree on the facts, what they got on each trial experiment. Alice partitions it according to her +1 and -1 outcomes and says, Bob, look, you have to average your results for conservation of the spin angular momentum. And Bob said, the hell? He organizes the same data according to his equivalence relation, his +1 and -1 results, and shows clearly it's Alice who needs to be averaging her data. Yeah, this is the last slide. I'm in good shape, huh? So Bob says clearly, Alice, it's you that has to average your data to satisfy conservation of spin angular momentum. So what is the missing causal mechanism here from quantum mechanics to account for this average-only conservation? We're saying exactly the same answer we had for special relativity. There isn't any. This is not a dynamical effect. This is a kinematical fact that follows from an adynamical global constraint, MPR of F plus H. And you can see here we haven't invoked it. We don't need to invoke violations of locality. No causal mechanism to talk about. We have Alice and Bob choosing randomly and independently their settings, one in the same Bell state, which is totally complete. Therefore, no violation of statistical independence. You don't need retrocausality. You don't need superdeterminism. You don't need Bohmian superluminal causal mechanisms. None of that. Questions?
So we have about 4 minutes, so we might be able to get a couple of questions in here. Any questions, please?
David.
David.
My talk is the antithesis of your talk, right? The opposite, exact opposite. Yes.
So I'm just channeling Harvey Brown here, and it's a minor point in the talk, but if you want to say, look, there's pure kinematics, there's not even reference frame-dependent dynamics involved in length contraction, what do you think the right story from that framework is to tell about Bell's stretched string?
I'm sorry.
I'm thinking of Bell's stretched string. You know, I have two rockets co-accelerating my reference frame at the same acceleration. There's a string between them. The string contracts and in due course snaps. So I'm just interested how you think about that. If you, it's not a gotcha question, but from the very kinematic take on it you want to take, how do you think about it?
Yeah. Again, everything that your Lorentz transformations deal with purely kinematic. Do you agree?
No, not necessarily. No.
Yeah.
I think it's like
Lorentz transformations, right? To go from X and Y and Z and T to another frame. To events in space-time to transform them into another event. Now you take those transformations and you demand that any dynamics on the space-time be Lorentz invariant or Lorentz covariant, right, in terms of its form structure. So anything you're talking about there with breaking strings or whatever, that would have to be according to your some sort of dynamics, right? The string is forces.
Sure, but it's not so clear you don't want to say the same thing about the rod. After all, if I start accelerating with a rod, the physics had better shrink the rod. Now there'll be a different description and a different reference frame, but it'd better be the case that the moving physics contracts the fields appropriately, so a rigid rod actually manages the dynamics as the accelerating person accelerates with it. So I'm not completely convinced that the right way to say that is it's just kinematic. I mean, I agree with you. Of course, it's all simply relative. There's a good story in each place.
Yeah, these are just empirical and mathematical facts. I have not introduced any new physics nor anything.
No, it's just interpretation.
Except to justify everything that they've already shown to be the case. All I'm doing is, hey, you can justify that with the relativity principle. You realize that, right? So.
Possibly time for one more very swift question, if there are any more. Okay, if not, let's thank our speaker again. Okay, so our next speaker is Ovidio Cristinel Stoica.
Thank you. Thank you very much to the organizers for allowing me to present the talk. I hope I can use this well. I don't know.
It's that one.
That one.
Yeah. Next. Yeah.
All right. So I'm by physicalism, I mean the position or the thesis that only the structure and dynamics of the stuff matter, and not the stuff itself. So the stuff, call it substance or whatever. So, for example, if there are two worlds that have the same laws of physics, like the same equations of motions and the same ways to the same structures, they should be completely identical from the physicalist point of view. Like, for example, one of them has sentient beings, the other one should have sentient beings, because there is no physically observable difference, because when we measure something, we just find relations. Like, for example, I use this as a stick to measure a length. I find relations. Whatever I do, I cannot go beyond the relations, beyond structure, and beyond how this structure changes in time. So if it happens somehow for whatever reason, I don't know if this is the laser, but it doesn't matter. The colored picture and the black and white picture represent two possible worlds with the exact same structure, which evolves in time in the exact same way. But can it be one of them contains sentient beings, and the other ones contains identical structures like the sentient beings in the first one, and they evolve in time the same. But can it be that one is sentient and the other one is not? According to physicalists, as I define it here, it cannot be, because there is no difference in the structure or in the dynamics. But some people think that there should be, and they say that at least it makes sense to ask the question of philosophical zombies. So philosophical zombie is, in this case, a structure in the black and white world, which is identical and behaves the same, like one with brain, and so it has its own brain. The other one in the colored world experiences the world, and the one from here, it doesn't. So some would say this is not even possible to think about in a logically consistent way, because you have to show me something to measure in the lab, and all I can measure is the structure. Now, okay. Now consider like, the Laplace demon, but in quantum settings. What I say now, that is not limited to quantum, but I have to explain using some ground, something to think about, but it works in any dynamical theory, which involves structure. So in a quantum world, we have a wave function on the configuration space. The configuration space is, for example, for M particle is n copies of x, y, and z. So by looking at the patterns of the wave function, an omniscient being, similar to Laplace's demon, should be able to say this structure is endowed with consciousness, the other structure isn't, just by looking at the pattern. So, for example, if you to see the pattern that when you bring it back in the 3D space by taking reduced density metrics of the wave function, you get orbitals arranged in atoms that are arranged in the shape of the brain and so on, then you'll get a brain that gives a talk like this, that omniscient being would be able to read in the wave pattern that brain and say, this is a conscious person. But the same structure that would appear to the sentient being as a pattern of as a structure of a brain giving a talk and so on, can be found on the configuration space of momenta. So if the same omniscient physicalist demon would look not in the configuration space of position, but in the configuration space of momenta, can find a wave function which has the same structure like a brain. The difference would be that the dynamics, I mean the Schrödinger equation, will involve differently the positions in the momenta, or the wave function will evolve in time in a different way, like maybe the brain would melt or will explode or something. Now, there are other bases besides the position. You can take any unitary operator of the Hilbert space and can apply a transformation of the position basis and obtain another basis. And the pattern that appears in the position basis as a brain that thinks and gives a talk would be transforming completely different patterns depending on the transformation that we apply. Not only, so you get not only the momentum representation, but you can get all sorts of representations. However, if the unitary transformation that I use, which I denoted by S, is commutes with the Hamiltonian operator, it will evolve with the same laws. So this is not the case in general for the Fourier transform that gives you the momentum from the position. But there are infinitely many unitary transformations. I would say even in a two-dimensional Hilbert space, you have infinitely many unitary transformations that commute to the Hamiltonian. But in a huge Hilbert space that we need to describe our world, there are infinitely many, I cannot say how many infinites there are. Big. Anyway, the question is, how is it possible for the omniscient physicalist demon to look at the different possible bases of the Hilbert space and read the patterns that will give you what we see in our world, if there is a brain that is part of a body that gives a talk and so on. How will that being be able to find out if it's not given the basis? So if that being doesn't know which is the position basis and chooses a random one of the bases, it will find different patterns of the wave function doing different things. Now, the thing is that the positions cannot be read just by looking at the operators, because these operators that I obtain, so let me go here because I don't know. So these operators are just like the position operators. You cannot distinguish them by their mathematical properties and if S commutes with the Hamiltonian, because they will be in the exact same relation as so the Hamiltonian will depend on them in the exact same way in which it depends on the positions. So they will, on this configuration space, the wave function will evolve according to the same Schrodinger equation. Suppose that the demon says, the physicalist demon says, yeah, but I choose one of them and they are real position basis and the other one are not. But how do you define position basis? We will see that you cannot choose because they cannot differ by their structure. Suppose that the omniscient demon will say, yeah, but maybe positions are fundamentally, like ontologically, more real than other operators. But if the positions are real, the partial derivatives, and actually the gradient with respect to the position will be real, and any function of those would be real. Like, for example, you construct all operators, all physical properties, just as functions of positions and momenta. And you cannot say that one of them is more real than the other. It would be like saying the center of mass of this desktop was this. Anyway, of this thing, and the center of mass of this thing are more real than the center of mass of them together. It cannot be, so you cannot get something less real from something real. So then, if you do this, you break the rule of physicalism, because you say there is something about the stuff that makes them, which makes some observables more real than the others. So it has to be perfect symmetry. Thank you. Now, what breaks this symmetry? Because obviously, we don't live in a world in which the laws of physics appear to us as being invariant to the full unitary transformation, even if they preserve the Hamiltonian. We live in a world in which we have the Euclidean symmetry of the three-dimensional space. Or maybe if we have spaceships good enough, we can experience four-dimensional transformations like the Lorentz. But we cannot go beyond this. Oh, there are also gauge symmetries. Okay. So then if nothing breaks this symmetry, it should be that the case that there is an explanation for why we observe this symmetry as being broken. So I will now use a term that I want to convey something, observer-like structure. So if I'm an observer and the wave function looks in a particular way and moves in a particular way in a position configuration space, and if in another configuration space obtained by transformation, by unitary transformation, we find an identical wave function, the same pattern moving in time in the same way, I will call that both that and me, observer-like structure. I only know about me that I am sentient. I don't know about that one. So I don't want to speculate is not or is sentient. But let's call both of them equally observer-like structures. So each of us is an observer-like structure, which happens to be sentient, I presume. But the same pattern in a different basis will also be an observer-like structure. So how is it? So I have a question now. Is it true that if in a different basis, I forgot something. So if in this basis that we obtain by the transformation, you have a pattern that makes an experiment and says, I found the position of an object, it refers to their own basis when they say position. So they will, if they consider position basis as more fundamental, they will say, in my basis of the Hilbert space, what I call positions, is more fundamental. Something wrong happens, I got. All right, so if physicalism is true, this principle of relativity of structures should be true. In any basis you look, people who, I mean observer-like people who do structures, who do people-like structures, who do experiments, they will say, this is the real position basis. And the other guys are wrong, they don't even exist. Thank you. So then it appeared that from the structure alone, you'll have sentient beings in all bases. They will be different. You cannot say that if one of the bases is occupied, the other cannot be sentient, so to speak. Now, if they are not equally sentient, and one of the bases is more special, then there should be a way to prove it. But how can you prove it? Because there is this, all you can find is the same structure and the same patterns. So there is a way to prove it, and this way is based on the following observation. If there is a way to find that I can be one of these observer-like structures and I cannot be another observer-like structure on a different basis, then I proved it. And to do this, I'm sorry, there is a lot of math involved. I try to say it briefly. Whenever some observer-like structure is here and says, this is a table which has a list of physical properties with particular values. The same vector in the Hilbert space will appear in a different basis as a wave function which thinks the same about being near a table with this list of physical properties, but those physical properties can have any value. So if we would apply because they all exist at once, all the bases exist at once. You cannot say if a basis exists, the other one exists less. So if they all exist at once, I should get somehow something from this, like a probability. And the probability that you get is that if I identify with any of these observer-like structures, there would be no correlation between what I think about the objects around me and their properties and what those properties actually are. Thanks.
Okay, thank you. And I'm afraid we don't have time for questions this time, but our next speaker is Jörn Klövfeld-Mjelde.
Hi. Let's see if I can understand this. Yes, I can. Brilliant. So I want to talk a bit about something which I have been trying to wrap my head around for a while, namely the issue of hypersurface dependence of state assignments in relativistic collapse theories. So I'm going to say a bit about what it is, why this might be considered puzzling, how this puzzle one way in which this puzzle might be resolved, and finally, I'm going to present what I take to be a somewhat new puzzle, namely the case of space-like entanglement swapping, which I will argue raises some new issues that proponents of these theories need to contend with. So, so that we're clear on what I'm talking about, here we have two different hypersurfaces, one nowhere in the path of the other, and they share a common subregion A. And to each of these hypersurfaces, we can associate a global quantum state. from which we can derive a reduced density operator associated with the subregion A. Now, if we introduce a collapse occurring between these two hypersurfaces, then the reduced density operators as evaluated on the two different hypersurfaces will generally differ. I've had to illustrate this with the entangled EPR state. On the hypersurface sigma, the associated reduced density operator corresponds to a mixed state corresponding to no determined spin property, while on the hypersurface sigma prime, it approximates an eigenstate of spin corresponding to an approximately determinate property of spin up. And Wayne Myhrvold has coined the term the relativity of entanglement to characterize this feature. In this particular case, the relativity of entanglement can be thought of as a consequence of the fact that the notion of an extended system is ill-defined in a relativistic theory. So the system, as the system is considered as the joint region A and B1, is in an entangled state, whereas the system, as considered in the joint region A and B2, is separable. But later we will see that in the case of space-like entanglement swapping, we have a form of relativity of entanglement which cannot be merely attributed to the fact that the notion of an extended system is ill-defined. So this is something which has invited incredulity, as illustrated with a quote by Tim Maudlin, emphasizing the radicality of the sort of holism implied by hypersurface dependence. And one way, there are several ways to go on about trying to resolve it, but here I'm going to focus on a suggestion by, again, Myhrvold, who proposes that we should distinguish between what he terms the intrinsic and the extrinsic state of the system, and further arguing that the intrinsic state should be identified with the past light cone state. Then we do avoid any issues about assigning different intrinsic states and intrinsic properties to the very same region, though of course the extrinsic states will differ. I've heard take this distinction to be connected with another distinction we find in Myhrvold's work, namely the distinction between a local and a global notion of becoming. So the intrinsic state, the past light cone state, is sufficient to account for becoming in a local sense, i.e. the results of local measurements performed on the individual subsystem. This is what I've tried to illustrate with the left-hand figure. But if we are to account for becoming in a global sense, including then becoming of bell-type correlations, we need to use the global state, which almost by necessity needs to be defined on a given hypersurface. And it might not be all that unexpected that in order to account for non-local facts like correlations between spatially separated systems inherently are, we do require some sort of a global account. But I would argue that if this approach is to avoid a charge of instrumentalism, we are still owed some kind of an explanation of why these Bell correlations arise, i.e. some objective feature of reality that might explain that. And in the EPRB experiment, one such feature is naturally forthcoming, namely the fact that the pre-collapse state of the joint system is entangled. And since this entanglement is due to a preparation process occurring in the common past light cone of A and B here, it is the intrinsic state on this account which is so entangled. So while we cannot give a local account of the correlations in terms of the intrinsic states of the individual subsystems, the account is still in some sense pseudo-local, in that the correlations may be explained by the fact that the intrinsic state of the composite system is entangled. But that leads us to the case of entanglement swapping. So to briefly go through the protocol, here we have two different EPR sources, each sending out an EPR pair. One from each pair is sent to Alice and Bob respectively, whereas the two other ones are sent to Vicky. And Vicky can perform a Bell state measurement, which swaps the entanglement from the pairs 1, 2 and the pair 3, 4 to the pair 2, 3 and the pair 1, 4. And in the case of early entanglement swapping, we have that Vicky's measurement occurs in the absolute past of Alice and Bob's measurements, and hence the Bell's correlations may be explained by the fact that the intrinsic state of the joint system entering Alice and Bob's measurement devices is entangled. In the case of delayed choice entanglement swapping, then Vicky's measurement occurs in the absolute future of Alice and Bob's measurements. And hence the intrinsic state of the joint region A and B is not entangled. And so how to explain the correlation seen in that case? Well, it has been argued that the correlation should then be interpreted as a selection effect. And Pies and Wharton have recently also argued that this sort of a selection effect might be attributed to collider bias. So as the intrinsic state of the region V depends on the measurement outcomes, or the outcomes of Alice and Bob's measurements, then Vicky's outcomes might be treated as what in the causal modeling literature is known as a collider, i.e. a joint effect of two or more distinct causes. And it's well known that conditioning on such a collider can introduce correlations between the causes despite them actually being independent. So here we have two different ways of explaining the correlations, Bell type correlations, and I should mention when we condition on the results of Vicky's measurement, the outcomes of Vicky's measurement. But what then of the case of space-like entanglement swapping? Well, here we have what Bhattacharya-Galluppi and Hermans has termed the relativity of pre- and post-selection, at least when we consider the extrinsic states. So the extrinsic state assigned to the region A and B when evaluated on the hypersurface sigma double prime is entangled, whereas the extrinsic state when evaluated on the hypersurface sigma is separable. And here's what I mentioned earlier, similarly a case where this relativity of entanglement doesn't go away by just specifying the space-time regions of interest, and so it cannot merely be attributed to the fact that the notion of an extended system is ill-defined. And similarly, the extrinsic state of region V is, will depend on the outcomes of Alice and Bob's measurements when evaluated on the hypersurface sigma prime, but not when evaluated on the hypersurface sigma. Meaning that the correlations may either be explained to arise due to entanglement or due to collider bias, depending on the foliation of space-time. But what should be noted here is that in this case, the intrinsic states of the various regions of the joint region A and B is not entangled, and the past light-cone state and the intrinsic state of the region B does not depend on the outcomes of Alice and Bob's measurements. So unlike in the EPRB experiment that we considered earlier, there is no pseudo-local account of the Bell correlations. The only thing we have is a fully global account where these correlations might be attributed either to entanglement or to collider bias, depending on the particular foliation. And what this suggests to me is that maybe entanglement does not play this explanatory role for accounting for the Bell correlations after all, but what we have is just a complete correlational structure which might be predicted from the quantum state on any arbitrary foliation. And this might both have implication for the role that we assign to the quantum states and to the idea of becoming in quantum theory, at least when we consider the relativistic model. And so in summary, on the collapse theories, different state descriptions might be assigned to the very same system depending on the hypersurface. This has motivated at least Myhrvold to introduce a distinction between intrinsic and extrinsic states of a system corresponding to, which I argue might be correspond to the local and global notion of becoming. This is something which still allows a sort of pseudo-local account of the Bell correlations displayed in the PRBA experiments in terms of the intrinsic state of the joint system being entangled, but such a pseudo-local account is not available to account for the Bell correlations displaced in space-like entanglement swapping experiments. What we have here is just a fully global account of the complete correlational structure. And thank you for your attention.
Okay, questions?
Hey, can we add you on our all-at-once explanation now? Your global account only? That's I shouldn't need that, but I don't know.
I've the more I look into the various kinds of interpreting quantum mechanics, I am myself moved towards the all-at-once type of picture. I can see that them coming from very different angles, both the hidden variables approaches of Price and Wharton leading towards that. I can also see remnants of that in the sort of flash ontology GVR approach, that if what you have is, and this is something which I maybe hint a bit at, is that this maybe if what you have is just a correlational structure, maybe then the quantum state doesn't really play much of a role in the notion of becoming, but it's useful when we want to predict forward. The question then is, where do we then also need the stochasticity of these accounts? Or is that an artifact of us evolving the state forward in time? I think at least that these different lines lead towards more of an all-at-once picture.
Time for one more quick question, if there are any more questions in the room. Okay, well, thanks very much. And our next speaker is Enrico Maresca.
Yeah, I will talk. Yeah. I will scream, I think you can hear. Yeah.
Because of the streaming.
Okay. Okay, so I'll try to summarize basically a 30 pages paper in 10 minutes. I'm going to talk about non-commutative geometry in space-time. Now, non-commutative geometries are a very interesting area of research which developed mainly in the last couple of decades. The very basic idea of non-commutativity is that when you compose your objects, you need to be careful with the order you use. Non-commutative geometries have very interesting applications to quantum gravity. And the shared conjecture among all the different approaches is that the fundamental structure of space-time should be non-commutative in the end at the appropriate regime. Now, what I want to suggest in the paper and to argue for is that despite what several accounts and several reconstructions have suggested, actually the development of non-commutativity and non-commutative geometry as applied to space-time in particular, is not an homogeneous development, but it is actually the result of a discontinuous interest in the topic, far from uniform development, and the way I will try to explain it, and I try to explain it in the paper, is through what I call the interlaced convergence, but more at the end. So I will proceed by highlighting 3 different phases in this development very quickly. A first phase is called divergence, localization, and the new approaches from the early 90s up to today. And then I will conclude with this interlaced convergence idea. So originally, the problem of non-commutative geometries actually started in QFT in order to treat the divergence problem in QFT. We had different attempts at solving the divergence problem. One of them was Heisenberg's lattice proposal, but it actually ended up having lots of problems, for example, breaking several conservation principles and breaking Lorentz invariance. Now, Hartel and Schneider in 1947 suggests the first actual model of non-commutative space-time. And the idea is, well, let's solve the divergence problem. We want to retain Lorentz invariance to maintain it, but we can reject space-time continuity. And so how do we do that? we use an analogy with the construction of quantum phase space. And so let's take the coordinates, spacetime coordinates, promote them to emission operators, modify the algebra in order to make it non-commutative, and then the spectra of these Hermitian coordinate operators will encode a fundamental length, basically. And then Born reciprocity is used, for example, to build Maxwell equations in this new setup. Now, the problems with Snyder's proposal were both specific, meaning we have unbounded coordinate operators, position operators specifically, and unbounded spectrum for the energy, and general problems. We are not saying what this fundamental scale amounts to physically, and we haven't fixed its value. So Snyder's approach it didn't have much resonance immediately after its publication, but still the second phase actually tried to solve the general problems which were raised by his paper, by his work. And so the second phase actually, which comes around the 50s to the 80s, there is the exception of Doppler's paper, but I will talk about it if you ask it. The general idea is, well, let's reframe the entire problem. Let's talk about localization and localizability of our physical systems in space-time. We have an underlying operationalist assumption. We want to understand whether there are bounds to our ability to localize systems within regions of arbitrary small size. And so what we do, we take GR, we extend it to the new domains, to high energetic domains in particular, and then what we end up with is having incompatibilities with quantum effects. There are several kinds of arguments, breakdown arguments, black hole production arguments. The interesting fact is that in order to fix the scale, which is the Planck length here, we use other results, independent results coming from Wheeler's geon theory and string theory in particular. What does it amount to? Well, we have a failure of operationalism at the end of this phase. It has to be restricted to some regime, or it has to be eliminated entirely. But the interesting thing is that these arguments actually they do not use non-commutativity. They do not refer to non-commutative spacetime, and yet they are one motivation for the rebirth of these approaches in the early 90s, because, well, non-commutativity gives us a natural way to reintroduce a fundamental scale into our picture. For example, if you take Snyder's algebra of coordinate operators, then you can show that it doesn't have pure states. So this means that you won't have sharp localization in that model. In the paper, one of the sections argues that, okay, that's great, but this still cannot explain the re-emergence of these approaches in the early 90s. Why? Because we still have the specific problems raised by Snyder's paper. They're still open. And so what the missing ingredient is the development of new mathematics. Starting from the 40s, especially in the 80s, mainly in the areas of algebraic geometry, quantization, and here I refer especially to deformation quantization and quantum group theory. Now here you have several results. I won't discuss them in depth. The star product is a non-commutative product which allows us to explain what we are doing, the so-called quantization procedure, in terms of deformation and contraction of the algebras involved. Quantization solves the unboundedness problem. And then quantum groups are very funny structures which basically show a case of self-duality, meaning that we have lots of quantum groups. Each quantum group is taken to represent a set of quantum symmetries, and these quantum symmetries will correspond to different non-commutative spacetime models. So we don't have just one model, such as Snyder's one, but here we have an undetermination of what kind of model we actually are talking about, and each model can be shown to be inequivalent with the others. And modern approaches indeed start with the localization problems, start with the new mathematics. They are very different from one from the other. They share some conjectures. I will focus on the spectral triples approach of Alan Kohn and collaborators, and on the quantum groups approach, just to give you just to sketch a bit of a landscape. So the spectral triples approach actually started as an attempt to extend the standard model in order to include semi-classical gravity. by using an uncommutative underlying structure. The idea is we have this basic object, which is an entire algebraic object. We have an algebra of fields, a Hilbert space, and a Dirac operator, which induces a quantum metric, which should codify this idea of non-commutativity of space-time. And the way we use it, we can build a spectral action and then use techniques of algebraic quantum field theory in order to build the entire system. And they actually derive a standard model, but it has a couple of problems with some of the couplings. And the main strategy, and that's probably, I mean, in my opinion, that's the most interesting thing, is that they use this correspondence between algebraic description and geometric description of what is happening, meaning that we have our differentiable manifold, we translate it into an entirely algebraic language via what is called Gelfand duality. Then we modify the algebra, turning it into a non-commutative one, and this will describe new geometric structures which do not necessarily fit into the definition of a differentiable manifold. That's one approach. The other one, the quantum groups approach, instead focuses more on the definition of a non-commutative space-time structure. Because non-commutative space-time structures, as I said before, by self-duality correspond to new possible quantum symmetries. And then they study the way that fields behave with respect to this modification of the underlying geometry. And the interesting fact is that while Snyder, on the one hand, tried everything in order to maintain Lorentz invariance, now Lorentz invariance is explicitly violated at the fundamental scale, and instead it is basically taken just as a guiding principle, meaning that, and what I mean by this is, we are just interested in recovering Lorentz invariance at the emergent level, so at lower energies in the so-called commutative limit. We're not interested in having Lorentz invariance at the fundamental scale. Actually, we probably won't have that. We have some very more complicated structure which manages to avoid the breaking of the symmetries, which was one of the main problems in the original approach. And so how we do this, self-duality and the connection of parameters, meaning that we can identify the deformation of the algebra with the non-commutative parameter of the algebra and the fundamental scale we are studying the system at. And so skip that for now. In the end, what's the picture? And then I'll finish. We have different leading questions. Divergence problem in the beginning, then a localization problem, abandoning non-commutativity, a specific reference to non-commutativity, and finally focus on quantum space-time and on particle physics. Cross-contamination of different methods and different results. Here you have some examples, Born reciprocity, which comes back in the quantum groups approach. The algebraic construction, once again, quantum groups approach, how you construct the differential calculus in this non-commutative structure. The analogy with quantum mechanics, which is actually pervasive in the way you use quantization in order to build an appropriate algebra to work on. These approaches also emphasize the scale dependence of the structure, of the space-time structure. In particular, usually most of the approaches take non-commutative geometry to describe an effective theory, and in particular, they focus on the relationship between space-time and fields, so how fields behave once we modify the underlying space-time structure, and the role of symmetries, as we saw that, Lorentz invariance versus the use of effective Lorentz invariance. And so in the end, what does this weird expression interlaced convergence means? If you have a substitute, please let me know. I'll be happy to change it. The idea is that we have a complex fabric of independent results, both in physics and mathematics, so different methods, conjectures, goals, strategies, which developed most independently from one another. We have some driving problems, the two listed here, the three leading questions here, which bring these ingredients together at different stages in groups. Early attempts are recovered and modified in order to meet new understandings and research questions, and there is a general convergence based on a common thread, which is that of non-commutativity. Thank you. If you want to see the mathematical model, here we go.
Okay, we have 3 minutes. Any questions?
When you say derive the standard model, what do you mean exactly? Do you mean construct?
So what Alain Kohn tries to do is that he starts with his spectral triples approach, and he wants to build the Lagrangian of the standard model with an additional term for the gravity, basically.
So he's constructing. You don't mean he gets out the SU3?
No.
Okay, good.
Still have a couple of minutes. Any further questions? Yeah, go ahead.
Well, different then in that case, since there's no one else. This is just curiosity. I mean, so the new approach is 1990s to today, but the references you're listing are all kind of late 90s or very early 2000s. Which of these things are still kind of going, and which? This is in your list of.
The modern approaches, you mean?
Yeah.
You
gave that nice list of modern approaches.
Yeah,
The actual
yeah.
references are all kind of 20 years back. It's interesting where we are now.
Yeah, so the spectral triples approach is still pursued, mainly in the area of cosmology. There is a recent book by Matilde Marcoli on the topic. The quantum groups approach is probably the most studied because it actually relates to the non-commutative approach to string theory, meaning in string theory, under certain conditions, you can actually derive a non-commutative geometrical structure at an appropriate scale. And indeed, the very idea of quantum groups and a certain interpretation of quantum groups was originally suggested in that same paper for the non-commutative approach to string theory, Seiberg and Witt in 1999. DSR, doubly special relativity, was actually studied in the beginning, in the beginning of the 2000s. It has a couple of interesting applications in the area of QG phenomenology, but surely it's not the ultimate theory we want in these approaches because it's a non-quantum approach, basically. Yeah, but it is very interesting in how it develops certain quantum symmetries. For example, the so-called Kappa-Poincare group, which would correspond by self-duality with the Kappa-Minkowski non-commutative space-time structure.
Okay, great. Thanks very much. And our next talk will be from Ada Kopralula and Özgür Aydin. Tonight.
Yeah.
And again, we have a joint paper, but just one representative here to give it for us.
Hello, everyone. Today I'm going to talk about David Bohm's metaphysics. I called it metaphysics because I think in his later works he really tried to combine our experience with physical reality. And since this conference about physics and reality, I wanted to tell you how could David Bohm's metaphysics could explain reality as we perceive. I got inspired from his book Wholeness and the Implicate Order, in which there is his aspects of the ontological interpretation. The ontological interpretation is an extension of the hidden variables theory, and in the hidden variables theory, as you know, every particle has a definite state in every time, and these variables are hidden from us, but it gets revealed through experiments. So the idea of wholeness is that it really opposes to the classical reductionist point of view in physics, and it says that the universe should be understood as a fundamental whole. Systems are always connected, they are never isolated from the environment. And opposing to the mechanistic point of view in physics, he talks about active information. This is not like regular information, the Shannon information as we know, because the Shannon information is about us, is about what we know about the system, but this information acts on the particle, it moves it in such a way because it puts form into its action. So information is really information. The hollow movement means that the universe resembles a hologram because every part of the hologram contains the information about the whole structure. And like every part of the universe implies in every other part of the universe. So this is the implicate and explicit order. The explicit order is what we perceive. And there's also the quantum potential that highly talked about. So when a quantum system interacts with the quantum potential, it gains all the information about the environment. And also there is the subquantum level, as we talked about, where the hidden variables might be. So in the book, he says energies such as light, sound are continually unfolding information of the entire universe into each region of space. And more deeply, all the matter in our bodies from the very first unfolds the universe in some way. So this unfoldment and unfoldment means that, like he gives an example of a particle that contains life in it. So life is unfolded into matter, and it gets unfolded in the case of biological organisms. So if this wholeness is real, why are our perception is not like that? So what is the nature of fragmentary thought? Because in the book he talks about this, and he says that man's action guided by illusory perception, which is shaped by fragmentary thoughts. So he thinks that our perception is an illusion. But what is the reason for this illusion? Like, who is tricking us? And why cannot we perceive reality as it is? Why isn't there wholeness? So one of the answers that came to our minds was The Case Against Reality book by Donald Hoffman, in which he explains that things like survival mechanisms are more important when we are talking about perception, because we're not perceiving truth, we are perceiving what aids us to survive. So his theorem is fitness before truth theorem. But we think that in a Bohmian framework, there should be an explanation of this also, because even emergent structures such as evolutionary biology is implied in physics somehow. So what could be the physical reasons of why we're not seeing reality is what we're trying to achieve. So we thought about a isolated system, quantum system, and the collapse. So we say that the wave function contains all the information about the possible states of a quantum system, and the measurement actually means that the system gained information about itself, because remember, in Bohm, there is a definite state for all the particles, and through interactions with the environment, this hidden variable reveals itself. So there is no actually collapse. There is only gained self-information of the system. It learns its state. And the self-information is objective in the sense that its hidden states in the quantum level were revealed, but it's also subjective because it's about the particle. But the total information is always constant. It's diffusing between levels. Some is gained in one level and some is lost in one level, but there's only a redistribution. So there's always an exchange between active and passive information. So if we extend this view in a complex system, which there is an interaction with the classical environment, we say that the system, the temporal evolution of the new system after the entanglement will be in accordance with the dynamical evolution of normal classical systems. So there will be an increase in entropy because the temporal evolution of a classical system includes the second law in it. So if we take the arrow of time as an axiom, then the dynamics of which states are going to be entangled with the classical system would be defined in some way. So some interactions are more favorable than others because the interactions that increase entropy in a classical sense is always more favorable than ones that decrease them. So there should be an explanation in the subquantum level or the quantum level that defines this hierarchy. Like, why is the states that increase entropy more favorable and the ones that decreases are not? And also, even though there is this kind of relationship, some states are more stable than others. So there's a constant exchange between active and passive information. But some of the states are not stable in time, they dissolve. So what is the nature of this hierarchy at the subquantum level is what we don't know at this state. So why does matter in our context of reality, perceiving reality? So if we take the brain as a quantum system, not like a quantum system, but a system that exhibits quantum system, then this active-passive information dynamic could play a role in our perception. And we really think this would be the case because the quantum system, quantum effects really has a role of distinguishing us from the things that don't have consciousness. So if the brain exhibits some quantum effects, this could be the reason of this perception. So there was a study recently discovered that microtubules actually exhibits quantum mechanical effects. There were some evidence, and Penrose is known for his consciousness theory about microtubules and the fact that they're in the brain and they exhibit quantum effects accounts for consciousness. So if we take brain as a quantum system, then we can apply what we just told into ourselves. So if we're going to talk about the limits of knowledge, we can give the general framework as this. So we saw in the wave function collapse that the physical meaning of information are the states of the system. And the system gains self-information through interactions with the environment. And this passive-active information dynamics enable hidden states to be revealed. And the reason why are not all parts of reality, like why we are not perceiving wholeness, could be due to two limits. One of them is the fact that we gain information through interactions. So we're extending the collapse theory into ourselves. We are a system, cannot interact with all systems, and we're making the epistemic claim that the knowledge comes from interactions, basically. So this is the subjective limit that we have, that all systems have, in not achieving all the information about the universe. And even with interaction, some states would always be more favorable than others. And this is the objective limit that was put by the entropy statement that we made earlier. So there is a mechanism that enables some states to be more stable and some states to be perceivable in the classical realm, but not others. So we don't know the exact mechanism beyond this hierarchy, but we really think that it could be something in the subquantum level, this interactions and this hierarchy. Through experience and experiments, we can really get closer to perceiving the underlying wholeness. And this is my idea of a whole universe. Thank you.
Okay, we have 4 minutes for questions. Let's start with Uzi over here.
I'm curious, trying to use maybe variational principles like we do in classical mechanics to identify the trajectory. So you use variational principles, let's say, in classical mechanics to discover the trajectory. So maybe if you could use a variational principle in entropy, maximizing entropy, would that give you and then you'd have to somehow quantize it. But I'm just curious if you did anything in that direction.
Actually, we thought about the difference when we thought about the differences between classical level and the quantum level. We first thought about these paths and why are some paths are more favorable than others. So we didn't look into this with relation with entropy, but we will definitely check it.
Any further questions? We still have a couple of minutes.
Hi, this might be a general question out of lack of knowledge, but if you think on neuronal level about the information processing, and that happens on certain time scale, and then you have quantum processes on a much faster time scale below the kind of surface of these huge neurons, then I find it difficult to see how the quantum processes could be meaningful in terms of neural processing, other than, for example, in terms of their statistical properties, for example. So can you, or maybe someone else can help me understand the kind of the relevance of the quantum level in terms of consciousness, which happens on neural processing. Thank you.
I don't know what the neural process is like, but I know that there are like integrated information theories of consciousness. Like a lot of neuroscientists, I believe, are working on this topic. But in David Bohm, actually, the thing you said about temporality is an issue, because the information that we talked about in Bohm is really non-local. It has nothing to do with temporality. And we say that temporality emerges when a system interacts with the classical system due to what we told about entropy and the arrow of time. So I think in this point of view, in the brain point of view, it might be the case that it emerges out of the quantum processes, but the whole structure as a brain, as a classical system, is also important.
Can I say 10 seconds?
10 seconds.
Haverock and Penrose have this idea that you have these very fast processes in the microtubules, but then you will get these beat frequencies, which might then come up to the EEG. That's just like speculation, but just to say people have thought about it. But that's my 10 seconds.
Okay, thanks very much. And our next speaker is Jose Alejandro Fernandez Cuesta.
Okay, so nice. Well, thank you to the organizers and everyone here. I'm not a physicist. I'm not neither a philosopher of physics. I'm doing my PhD on logic and philosophy of logic. But I'm working in a team. I'm the philosophy of logic guy. Michele Piazzai and Umberto Rivieccio are the, respectively, the quantum cognition guy and the algebraist guy. So if I said a lot of stupid things from the physical perspective, just interrupt me. I'm going to focus on the fairy tale of a main argument with thing that maybe makes sense from the philosophy of physics and the philosophy of logic perspectives. So I made a little introduction to the quantum logics and a really brief introduction to what are the strict quantum logics. It's usual to speak about classical quantum logics, but because of quantum logics are non-classical logics, speaking all the time of classical, non-classical logics, I think that it's harder than speak of strict quantum logics. So after that, I'm going to introduce one interesting way of expand the quantum mechanics formalism of Hilbert spaces beyond the physical contexts, and what consequences will have in the philosophical discussions. So, quantum logic, as a tag, is said in the logic contexts and in the philosophy of physics discussions in a lot of ways, more than the being in the Aristotle metaphysics. We have the informal way as saying, okay, here we have some results that are counterintuitive, that we don't really understand, so they're no logical at all, or they evoke some problems on our classical logic principles, just in a narrow sense, and don't clarifying what are those logical principles. There are also some interpretations on quantum mechanics that call itself quantum logics or new quantum logics, which are, I'm not going to say a word from that. And in the strict sense of quantum logic, with a syntax and a semantics and calculi associated, we have, as in every logical discussion, two main focuses. One oriented to the implementation in computational contexts with the quantum logical gates, and the application of quantum logics into the definition of some abstract algebras and structures employed in the quantum mechanics, I think. So the main project begins with the seminal paper of Birkhoff and von Neumann in 1936, and the same year they published this paper, everyone forgot it. For logicians was a really hard stuff to understand. Physicists really don't care at all about what was that. Von Neumann sent a letter to Birkhoff saying, okay, I was completely wrong and this makes no sense. So there was a silence during the 40s on the quantum logics projects until the end of 50s, when began the axiomatizations of quantum mechanics. And then, studying the possible actions of the quantum mechanics, some people said, okay, maybe we can use some logical approaches to determine what rules of on the mathematical perspective, on the algebraic perspective, we need to do that. And then we have a lot of different quantum logics. But the philosophers are not still here. It was 1968 when Putnam took these discussions and wrote a famous paper called with a question form, is logic empirical? And that was the boom in the philosophy of logic with the quantum logics. So the original project, as Birkhoff and von Neumann tell us, was this. One of the aspects of quantum theory, which has attracted the most general attention, is the novelty of the logical notions it presupposes. This is weird. What does it mean that a physical theory presupposes logical notions? And what does it mean that these logical notions are new? What is a new logical notion employed by a physical theory? That was strange, but it's von Neumann, so he must be right. The object of the present paper is to discover what logical structure one may hope to find in physical theories, in plural, which, like quantum mechanics, do not conform to classical logic. The discussion just was cut down in the case of quantum mechanics. But there are a lot of interesting things here in this introduction to the paper. So what Birkhoff and von Neumann tried to do and we spent a lot of years developing this, was something like this. But this is a toy model of what a quantum logic is. In classical mechanics, we have no problem at all, because we are working in a phase space with all the variables. We can read the phase space as a classical algebra, Boolean algebra, with the variables interacting with classical algebraic operations, and the Boolean algebra just corresponds to the classical logic in zero order. So we can jump from the logical perspective to the algebraic one and mix everything and nothing happens. If I write and set theoretical intersection and I made a mistake and write just a conjunction, nothing really happens. We understand what I'm doing. And we can change the operations from the set theoretical part to the algebraic part to the logical. And we have no loss of information. But in the quantum mechanics, does not happen. First of all, in the classical mechanics, we are dealing with the power set of the phase space, usually in the reals. Now we are not dealing with the power set. We are dealing with not even subsets, but subspaces. So the first notion in the definition of this quantum algebra is a geometrical operation. Then we have the classical set theoretical intersection. We want that because we need some starting point. But now we have two different levels, the geometrical level and the set theoretical level. And this is relevant. Then we don't know how to work in the Hilbert spaces with the classical set theoretical union. So we remove the union and include the span of the total Hilbert space instead of the union. And the top we maintain as the total space and the null space. Okay, but the negation, again, is not the negation. It's not neither the set theoretical complement. It's the ortho complement, reading again in the geometrical sense. So this, for someone studying logic, makes no sense at all, because we have some order set in which we include geometric operations in algebraic contexts, conserving some set theoretical operations and other that not. I didn't say anything about this. The subset relation, maybe this is a completely problem apart that we don't know how to interpret the quantum condition. So, our proposal, and this is what I'm doing in my PhD, is just to take to go to the 0 point and say, okay, what are we doing? We are defining some algebraic structures. So let's define this Hilbert space as an ortho-complement lattices, but from the explicit meta-language, in that case, first-order logic or second-order logic, some standard logic that allow us to define some standard set theory. And from this, we can move to use the standard axioms to define what is a Hilbert space and so on. And then clarify the level in which we are working. This is one of the first motivations, or one example of the motivations of construct these mixes of different levels. And this is the Putnam argument. Putnam said, this is interesting, I think, that, okay, I'm a logical monist. Today, nobody is, anyone is a logical monist because we have a lot of different non-classical logic. So said there's only one, the one big true logic that is weird and really hard. But Putnam says, and Putnam said, okay, from the logical monism perspective, makes sense that if we now are dealing with these strange algebraic interpretations of the geometrical operations in the Hilbert spaces, maybe we can modify our one classical logic with these results. But he couldn't. He couldn't do that. And so we maintain today the classical perspective of the standard logic as classical logic and the quantum developments in the algebraic approaches. So the discussion in the philosophy of logic as is logic empirical is not the thing, is not the argument saying, okay, I'm dealing with a lot of logics, but one special logic is the quantum mechanical logic, and now I reject all the classical developments just to reconstruct all the mathematics in a quantum logical way. This was not the point. So quantum logicians are focused on study the correct algebra, the beta algebra, that hope someday one physicist maybe will can use in something, and the correct semantical approach to develop inferences in this physical context. That's the canonical logic approach, and makes sense. But since few years ago, there is a program called the Quantum Cognition Program, which is now based on the idea that the brain or consciousness or mind or whatever is a quantum computer or device or system or something like that. No, it's just a case in where we're doing some experiments, asking questions to people. The probability distributions of the results can be explained better using the quantum probabilities than these ones. And this is interesting, because if we apply the Hilbert spaces and the probability developments from these strange algebras beyond physics, maybe we can ask ourselves if quantum logics are either quantum or not, or logics, maybe, I don't know. So I put the conclusions for the discussion on. Thank you.
Thank you. And our final speaker, I have no time for questions, I'm afraid we've used the whole session. Our final speaker is Jamie Gilchrist.
Hello, and yeah, thank you very much for the chance to speak this afternoon. I'm going to be talking about metaphysical accounts of quantum entanglement. And, well, why, you might ask, is, well, physics says that there's entanglement in the world, so metaphysics, it seems, should maybe say something about what it is for there to be entanglement in the world. In particular, I'm going to be looking at a proposal by Claudio Colosi and Matteo Morganti that metaphysical coherentism, which is the idea that the world may be structured in webs of mutual dependence, may provide a good account of entanglement. And the aim is going to be to raise some challenges for the coherentist account and look at the interactions they point to between metaphysical conjecture and the interpretation of quantum mechanics. So the structure is going to be something like this. I'm going to start just by introducing very briefly the entanglement case study. I'll then talk about three different metaphysical accounts of entanglement: the coherentist picture, which is the focus, and two with which it's contrasted. I'll then argue that coherentism faces some challenges if it's to be a substantive metaphysical account of entanglement, and then look at some interpretative steps that the coherentist may have to take. So, entanglement. I'm not going to explain entanglement or discuss it in front of a room of people who understand it a lot better than I do, but I'll just say that I'm going to take as our case study the state here, represented here, which describes the entanglement with respect to spin of two quantum systems, A and B. And this says that the values that these systems may take for spin are correlated and necessarily opposed. And the question is what metaphysics should we take to underlie this modal correlation? So I'm going to follow Colosi and Morganti in contrasting coherentism with two families, really, of metaphysical account of entanglement. So on the one hand, we have holist approaches, and holism suggests that we understand entanglement in terms of the whole AB, which is metaphysically prior to or more fundamental than the parts A and B, and it's to this whole that the state psi AB pertains, or just describes this whole. Now, this diagram is best understood as representing a variant of holism that maintains commitment to the parts as derivative entities, but the important thing here is the priority of the whole. On the other hand, we have structuralist approaches. So structuralism being very roughly the idea that structure or relations are physical and at least as fundamental as the relata that stand in them. So in this case, the state psi AB is the state of, or in some cases simply is, the structure or entanglement relation RAB. And here, this diagram is best understood as representing the eliminativist version, which makes no commitment to the relata, but the important thing is the prior physical relation. So moving on to metaphysical coherentism, which, as I mentioned, is the idea that at least some of reality may be structured not as orthodoxy would have it, in strict partial order hierarchies, but rather in webs or loops of symmetric dependence relations. So sometimes that's contrasted as being vertical hierarchies on the one hand to horizontal mutual dependence on the other. Why should we consider metaphysical coherentism at all here? Colosi and Morganti point to several arguments of explanatory power, but they're a little tricky to cover in any detail in a brief time, so that perhaps the most apparent appeal in a brief overview is their claim to maintain a more or less traditional ontology of objects that, or separate systems or entities that are more fundamental than any whole that they may or may not compose, in contrast to the structuralist and holist, respectively. But we might ask, looks like this is going to go off the screen. Well, I'll just say what's under that. We might ask if it's just too close to a simple restatement of the entanglement phenomenon. Right? We know that the state psi AB is not reducible to the states of the parts A and B, and yet Colosi, or the coherentist, claims to not need to posit anything in addition to A and B. So how do they capture the non-factorizability of the entangled state? They formulate coherentism in the following terms, which should be read as: A is essentially such that it depends for its existence and its properties, importantly, on the existence and properties of B, and vice versa. They say, however, that it's not a simple case of A depends on B and B depends on A, but rather the physical systems exhibit essential collective features that are not reducible to the properties of the parts. And this may be fine, and we can grant that this is what their claim of interdependence is designed to achieve, but what I want to suggest is that they need to say more in order that this is a sort of a substantive account, and in particular they need to say what it is about the existence and or properties of the parts that underwrites this irreducible relation. I'm not asking for a reduction. I just think that they need to give an account of why the particular modal correlation that we're interested in here holds in this case and between these entities. You know, presumably they don't want to say that it could hold as correlation or the entanglement relation could hold between any entities whatsoever. So in other words, they need to identify some properties that are relevant both to the domain, we might say, of the correlation spin and to its character, which I would say opposition. You might ask, do not the structuralist or holist accounts have to make a similar refinement? And it's here that they can be useful in contrast, because the answer I give is no. In both cases, the holist and the structuralist can be seen as purchasing or buying at the cost of their unorthodox metaphysics a single entity to which the state applies or that's described by the state. And so therefore a single entity that is in a superposition of states of complex properties assigning opposed spins to its derivative parts or relata. We're not setting out to solve the measurement problem here. That's not the goal. So superpositions of entities is a sort of allowed to all accounts as part of a uninterpreted quantum mechanics. So then you ask, well, can the coherentist not appeal to superposition of properties? And I say that even if we grant the coherentist that A and B are each in a superposition of spin, which is not clear that that's what the state says, but even if we grant them that, we're still left asking the question, what underwrites the opposition of spin that we note in the correlation? It's valueless superpositions don't seem to be the right sort of relata to stand in the relation of having opposite spin to. They ground the domain of the correlation spin, but not the character. So what can we say about the, what more could we say about the properties under coherentism? And it's at this point that we need to get to some interpretation of the quantum theory, or so I argue. And clearly I can't discuss in any great detail interpretations of quantum theory, so I'm just going to point to one interpretative principle of property attribution that's available that is the sort of step that the coherentist might have to take, or is representative of an interpretative step, and it shows some of the issues that they may run into. And the principle I'm going to discuss, which I know is will find some objection in the room, is the eigenstate-eigenvalue link. And I'm not trying to argue for it. I'm just saying that it's a likely first step in some cases. The eigenstate-eigenvalue link, or EEL for short, says that a quantum system has a value for a property if and only if it is in an eigenstate of the relevant operator. Now, if we apply this to the systems A and B, described as they are by the state psi AB, we can see that neither A or B is in an eigenstate of spin, and so by the lights of EEL, neither has a value for spin, that property with respect to which they're entangled. And I would like to suggest that this leaves the coherentist searching for a foundation, not to reduce to, but something to underwrite their irreducible relation. So that's just an example, and I'll just move on to some other examples of steps that the coherentist could take. The responses they might make, they might appeal to some sort of new primitive entanglement properties that, thank you, that underwrite the relation, but this could work, but it seems to undermine their claim to ontological conservatism. They could also, if we're thinking of the case where I allowed superposition of spin to each of the relata, they could introduce some sort of gnomic account of the opposition that's holding between the two. We might think of something like the Pauli exclusion principle, perhaps. I'm probably getting out of my depth with that, but the idea is that it would guarantee the opposition of spin, but the problem we find here is that that's, aside from being somewhat ad hoc, it also leaves cases other than the opposition of fermion spin requiring new laws or new laws to govern those situations. So another option would be to understand the superposition of spin in terms of metaphysical indeterminacy, and actually building a little some of the best accounts, or most sort of physically rigorous accounts, perhaps, of indeterminacy rely to some degree on a quantum logic interpretation of superposition states as meaning that it's neither true nor false that a system is spin up, say, in response to questions. So these sort of glutty metaphysical indeterminacy accounts could provide the coherentists with the positive property values that I'm suggesting they need. But last and perhaps most relevant to the current context, they could consider sort of more obviously alternative interpretations of quantum theory. They might consider interpretations that simply provide them with relevant valued properties, such as some hidden variable approaches, or they could look at accounts that revise the notion of property instantiation, such as relational quantum mechanics, for example. And in both of these cases, metaphysical coherentism, it's been suggested, could provide a good framework for understanding these interpretations. But what I'm suggesting is that these may be the only quantum waters in which coherentism can swim at all. And so these are really just sort of brief suggestions for response that they may make or consider. But what I want to suggest, and the purpose of this talk has been to suggest that metaphysical coherentism, while it is one promising metaphysical account, or shows some promise as a metaphysical account of entanglement, unlike the others, cannot remain neutral with respect to the interpretation of quantum theory if it wants to be substantive, a substantive and explanatory, if that's the right term, metaphysical account of entanglement. And the hope is that both metaphysicians and philosophers of physics may find something of interest in a point of tension like this. So that's all. Thank you.
Yeah,
Thank you very much.
I think we have time for one question.
Oh, yes, sorry.
So yeah, we have time for one question right up at the back there. We'll bring the mic up because otherwise the people on the screen can't hear.
Thanks. So, holism and structuralism have sort of motivations outside of quantum theory. They have, especially structuralism has many reasons why you might believe that, independent of anything about entanglement. I'm curious whether coherentism is similarly independently motivated outside of quantum theory, or is there something extremely specific to this domain?
Yeah, that's a really good question. There is independent motivation for coherentism. I mean, and it comes about pre its suggestion, at least in this form, as an account of entanglement. Basic motivation starts from the idea that there appear to be, again, contrary to the orthodoxy, cases that you could argue there exists examples of symmetric ontological dependence, and that the idea that it must be asymmetric such that it could form a strict partial order hierarchy have to do with our biases around wanting a foundation and a hierarchical approach to structure and reality. I'm not going to do a great job of coming up with those examples. Some examples that people point to are things like the apparent symmetry of dependence between mass, density, and volume, for example. Would be one. There are other more logical-based ones that the statement A is B is true, and the statement B is true. They seem to depend on it could be argued to depend on each other. The other thing that I might say in favor of coherentism is that some structures accounts, like a moderate structural realist account that maintains entities and relations or structure, and it says that they are perhaps symmetrically dependent on one another, that is possibly best construed in terms, as a coherentist proposition, or vice versa. It's not clear. It's not completely clear how to disentangle those two options. And then, as I mentioned, with on the more philosophy of physics side of things, there have been suggestions that, like, Bohmian or other hidden variable accounts are best understood as not necessarily due to entanglement, but as positing a sort of coherentist ontology of objects. It has the benefit of having an ontology of objects that are unified by a sort of holist interdependent structure that doesn't have the same commitment to physical structure that a structureless account does.
Okay, thanks very much.
Provocative. Even in Copenhagen, taken interpretation has hidden variables. What is superposition? It's evident that every interpretation needs hidden variables. Then quantum mechanics is not complete. Voila. And even what is problem, it can't be this hidden variable like superposition tested empirically. So it's even a scientific idea to be a hypothesis. And to be a scientific idea is necessary to overcome Heisenberg relation of uncertainty. That's all, that's the core. And here is the explanation what is reality, because there are some strange ideas about.
Why do you have two Schrödinger cats?
One is alive, and the second one is dead.
And there is nothing in between.
Yeah, there are infinite infinity, because it's time then. There are not only two states. It's enough. Stop.
I'm a bit scared of the video. Anyway, so okay, I'm trying to discuss the how the quantum principles can play a big role in explaining the conscious experiences and in cognitive processes. Conscious experiences here in this sense actually an awareness, not exactly consciousness. So because it's a kind of skeptical term right now, so we have to use. So, what are the difficulties in the classical paradigm, and what kind of advantages if we incorporate the quantum principles as a paradigm in explaining conscious experiences and the cognitive processes? So, what kind of benefits it might have actually. So, we have developed a kind of model, the comprehensive model. I have been talking about it actually. So, in discussing explaining the conscious experiences and what are the modules actually. So, involved in this actually emotions and cognitive process and context influences, and how the quantum principles are interconnected while explaining. We can able to see that actually. Normally, the problem with the every argument is that actually quantum principles appears to be uninterconnected. Not interconnected, but in the level actually they act parallelly, but at certain level actually they are interconnected. And there is an interaction between, the kind of, in every one, if you take one experience, then every experience actually have different kinds of states, and those states actually, for example, like take case of the fear, one emotional experience, okay, and how this fear is interconnected with the different kinds of mental states, and at the same time, what the context is playing a big role to elevate the fear or anxiety, and how this can be, and in the way, especially in the contextuality, if we say that actually, what kind of feedback we receive from every context, and whether the feedback coming from positive environment or negative environment, and how these states have been interconnected actually. The interconnected means I'm talking about here entanglement kind of thing. Each state is how it is entangled, especially between one mental state to another mental state. Okay, so those are how this fear is elevating and how this fear is being operated actually. So that's the whole model has been built based on that actually, how these quantum principles are being interconnected, and especially considering in experience. So totally. So yeah. So that's based on that actually we have defined that kind of quantum paradigm. So, and we're trying to say that actually it's a kind of, you should not just only leave about the classical paradigm to explain your experience. At the same time, you have to incorporate quantum paradigm to properly to exactly explain any experience, especially considered to conscious experiences or subconscious experiences. Every experience, it is required, but you cannot completely explain any experience with the reference to classical paradigms or traditional models. That's the whole idea.
Good. Hello, Gustav.
Hello.
Please explain your topic.
Okay, so my thesis, my poster is on my thesis, and my thesis was on a paper called Consciousness in a Space-Time World, which basically lines up this problem of, in different frames of reference, our conscious experiences will have different temporal orders. And if they have different temporal orders, then surely that would have an effect on how our phenomenal experiences would be. Because event A happening before event B surely feels different from event B happening before event A. But there's also only ever one way that we feel things. There's only ever one phenomenal experience. So how do you sort of overcome this apparent different possible phenomenologies that may have existed? Basically, what I argue is that these different frames of reference within describing are not objective facts, but rather they're thin descriptions of facts, but they are not robust in the sense that, like the fact that our phenomenology is in a certain way is a robust fact, but it being described as having different temporal orders is just a description. Description-dependent fact.
Something we discussed in different particles are going to talk to each other, coming from four corners. It's going to be projections are very interesting. That's very cool. Can you calculate this projection?
First of all, the unity of consciousness and the disunity of consciousness are somehow related. Would you agree? Okay. Unity of consciousness is a very strange thing. If you're interested in this business, a lot has been written about it, say by John Searle and people like that. This unity of consciousness has to do with the fact that we're almost like island universes, meaning that you're somehow unable to have any access to other people's consciousness, right? I think, unless you have some special abilities. So that's, and I think it was Gilbert Ryle who said that said something like the solitude of the soul. Solitude is the ineluctable destiny of the soul. Only bodies can meet. And then this is an expression of this solitude, okay? And if you're interested, Persian mystic writers, poets wrote a lot about this yearning to break away from the solitude, which, okay, anyway, let's go back to the... So we're talking about unity and disunity, right? And the fact also, okay, so on the one hand, it's very difficult to access consciousness from without, let's say with measuring instruments, right? You cannot measure it. And on the other hand, it has very peculiar internal temporal conditions. It is given to itself in some way, it's okay? And these two things must be related somehow. I can argue based on parsimony that they're related. It makes sense. So anyway, if you go through all this, begin by what I really want to talk about is cutting space in two and the disunity of consciousness. But in order to do that, first of all, I have to relate space to consciousness, meaning what's the relation between vacuum and the consciousness. And I gave a bunch of arguments about why they're related, okay? And you can have arguments from philosophy. If you're familiar with Patrick Leboeuf, where the hard problem of consciousness and the hard problem of space are similar. You can have eliminativist positions in both of them, or you can be substantivist Meaning, we can say vacuum is really substance. Some people say no, vacuum doesn't exist. So it can be limited to this, right? Use causal set theory, for example, to argue that it is just, it doesn't exist as a substance. Some people say it does, okay? So, anyway. So, there's this argument about the formal similarity between the problem of consciousness and the hard problem of, and problem of consciousness, hard problem of consciousness, and the problem of the vacuum. And then you have the argument from novel physics, argument from background independent physics, argument from complexity. There's a bunch of arguments. And then, so maybe 8 different arguments. And actually, they're interesting. You may want to photograph it. I'm not going to explain it from now. But then go to this page. Argument from the medium. This is, and then argument from future. And I got some more arguments, but really, what I want to talk about is this business, right? Yeah. Now it turns out that cutting space in two is a 300-year-old philosophical problem. Started with Descartes, on to Kant, then on to the British philosophers like Quinton, Abbott, Smart. Many philosophers were interested in it. Most thought it's impossible. It was only solved by a geometer by the name of Robert Garrock in 1978. Which is the solution was radical because it turns out you can only solve it in 4 dimensions. Then you're asking a question, can I cut space in 2? Let's say, take a 2-dimensional space and I want to cut a sheet of it out. Sheet of this, right? From can you imagine an infinite sheet space? Can you cut a piece out?
Well, not if it's point continuum.
Well, this is okay. So this was the question. Now, what Garrock says, yes, you can do it, and he knows space. Okay, he's the guy who proved that. I think, if I'm not mistaken, that on the average the curvature of space is positive. Something, he has some important things. What he says is, yes, it can be done, but there's a temporal price to pay, which is so fascinating. Okay? Meaning that you can do it, but then either the manifold that you get is going to be temporal, non-orientable, or it will contain closed time-like curves, which are very interesting. So this suggests then that if you just remember, I want to say that the same mechanism solves both problems. The problem of inaccessibility of consciousness and the problem of the internal unification or the unity and the very strange temporal architecture of the conscious mental state. The fact that it's reflexive, it's revelatory, it's unmediated, okay. So here you actually, the same mechanism, one step explains both things, right? It explains both. First of all, I'm creating an island universe, right? So it explains our existential loneliness, okay? I'm creating an island universe, and at the same time, I'm getting these closed time-like curves, which is a very peculiar internal architecture, which is extremely reflexive. And here you can use something called the David Deutsch consistency conditions, and talk about qubits that live there in a closed time-like curve. And then maybe you can have all kinds of interesting philosophical advantages. The physical scenario is extremely strange. I would agree with that. It's speculative. On the other hand, if there is anything like the physics of consciousness, it must be extremely strange. So the only question is it strange enough? Not is it too strange? Okay. And I'm trying to do something which is as strange as I can, but it does give me, and once you do this, anyway, it ties the whole story. I can, if you're curious, I can send you a paper or something that I have something published to you.
Okay.
I'm working on another paper.
Okay. Thank you very much.
Thank you.